Ah.
Welcome everybody to the first session today, and it's a pleasure to have Hitoshi with us. He's faculty at the Grad School of Information Sciences, Tohoku University. I'm sorry, and so he'll speak on recent developments in connective logic.
Okay, so thank you very much for the introduction. I need to thank a lot of people, so I made a list. First, my sincere thanks goes to Shankar, of course, for the very kind invitation. I got it at the end of March when I was in the middle of the moving process, so I got back to him a bit late, and then my correspondences since then was been a bit sketchy, but thanks for your patience and kindness. Also, my thanks goes to Pulak for all the superb arrangements. It's been wonderful since I arrived at the airport. There were some people picking me up. That's lovely. There should be a lot of people behind the organization. Thanks goes to all of them. Also to the principal of the college and the head of the research council meeting me. That's very kind of them. It's also good to meet old friends, Michiel, Shulav, Soma, and also meeting new friends. Very nice to meeting you all. So I've been very enjoying this stay, and hopefully I will not spoil my presence by giving a bad talk at this conference. Hopefully you'll pick up something. I'm very happy to pick up clarificatory questions in between, so feel free to interrupt me if something's completely crazy. And I chose the topic of connective logics because when Shankar wrote me, he requested me to give a technical talk. I'm not very good in technical talks, but I thought what I've been working on, connective logics, had some surprisingly interesting technical things that I want to share and have fresh minds join me and others to explore. So as I did here, it's a joint work with Andy Kapsner, who's also a great fan of India and a good friend of Michiel. That's what I was talking about. Accidentally, Tomasz was giving a talk about connective logic yesterday, and he said it's now, what did he say? It was not a catchy, but a hot topic, something like that. Maybe it is so, but at least this has been one of the topics that I've been working passionately over the past 6-7 years. So let's see where I'll be going. So the plan for the talk is like this. So first I'll just give you a little background. What's connective logic? Why I care about this? And then there's going to be two parts. The second part is going to be a little survey just to give you how one might get a connective logic. It's fairly simple thanks to Heinrich Wansing's work, who's been one of my friends, co-authors, co-editors. And that part, it's more like a little survey, not giving you terribly many new things. More of the recent things that I've been working with Andy comes on this third part. And I have a quick wrap-up conclusion section at the end. Okay, so first the background and aim. So we've already seen the connective thesis named after Aristotle and Boethius. And basically, connective logics are having a very simple characterization that Aristotle's thesis and Boethius' thesis need to be included. Now, although Tomasz didn't really mention it, it's very important that we make sure that this implication connective is not a biconditional. Because if you interpret these conditionals as biconditionals, then you get it in a classical logic as well. But that's not certain. That's not what you want. What you want is here some kind of implication conditional connective. Now, what that is a big problem, of course. But at least formally, we stipulate that we don't get this symmetry condition being satisfied. It's different. Yeah. Yes. Here.
In classical logic. Yeah. And that is one of the problems of material implication.
Wait. Hang on, Michiel. Wait. So this should not be included, right?
No.
And this is just meaning that it's not going to be a biconditional. So if this is a biconditional, you get this.
Okay.
Right? Because A equivalent B is going to be equivalent, even, not only implying that B is equivalent to A. And that's what we don't want. Because otherwise, this connective thesis would be very easy to be satisfied. But that's not what we want. Yeah? Good. Okay. So that's connective logic. And even though it's named after this ancient philosopher, Aristotle, the recent modern development is fairly, in some sense, recent. Started off around 1960s. Some people would trace back to the early 20th century. Some of the students of Lewis, the C.I. Lewis, were interested in this kind of things. But I'll just assume that it would be starting here. And basically, there's a lot of development in the 60s, 70s, 80s, and 90s. Well, I say lots of, but not that massively, but still. And then there was a very important work by Heinrich Wansing in 2005. And at this point, I would just focus on Angel McCall and Heinrich's work. Very roughly put, there's a stark difference between before Heinrich and after Heinrich. So before Heinrich, all the attempts can be seen as trying to change the truth condition for the conditional in one way or another to get the connective thesis as part of the system. That's what's been the case. I won't go into the details. If you're interested, I can send you some references. The idea by Heinrich is extremely simple in some sense. What he thought about is the falsity condition for the conditional. Now, in general, if you're working in a very classical context, fixing the truth condition would automatically fix the falsity condition. But here we are assuming something not along that line. We are assuming something that is called like FDE or Belknap-Dunn logic kind of context, where we need to specify both truth conditions and falsity conditions separately. So if you don't know about that, you can also shout at me later. But that's a rough idea. And then in that case, regardless of what kind of truth conditions you take, you can specify a separate falsity condition. And for that purpose, you can just do it in a sort of arbitrary way to some extent. And one of the options would be just to take this formula. As I will mention it to you later again, it has also a kind of drastic implication by following Heinrich's idea, namely the propositional logic is going to be proving a contradiction. So, for example, one of his systems called C would prove not only the conjunction elimination with the contradictory antecedent, but its negation of that very formula. Of course, the propositional logic is not trivial, so it's not going to prove everything, but there are going to be some instances of this formula and its negation being both valid or provable, whatever. And it's not only this kind. I mean, we can also rely on something without, we don't have to rely on conjunction specifically. We can have a purely negation implication formula. Again, having a formula and its negation being both valid. No. Yeah. Yeah.
By taking A on the after implication, it could be B also. Because
no, it cannot be B because we don't in this connective logic.
Oh, it is in connective
It's
logic.
in connective
it is not
logic, yeah.
classical.
No,
C
no.
for connective.
No, it's connective. Yeah, exactly. Yeah, exactly. Because if we have B, right, then that's a problem because then it would explode. So that's what we don't want to have. Good. Now, Peirce's law, it can vary. So some of them, I will show you one system that would include the Peirce's law, and there will be other ones that are much, much weaker, intuitionistic, even relevant, and so on. Yes, exactly, it's very independent. Okay, now, I mentioned connective logic, I mentioned a little history, I mentioned the main idea that I'll be following. Oh yeah, Ramakrishna. Yes.
Does it, in logic programming, there is this idea of negation as inconsistency.
Yes.
Right? That, from A, if I cannot derive B, then I conclude that, A implies B, I cannot derive, right?
Yes.
So, is there some connection with, Shepardson has this negation as inconsistency and all, to give semantics of logic programs, where
Yes.
again, success and failure is how you think about it in terms of
Yes.
truth and falsity.
Yes,
So
I think in that case, there's a question about how to relate the success and failure.
Yeah.
So if you let it sort of incompatible, then it's going to be a problem.
Okay.
Yeah.
Okay.
So because of this very dangerously
Okay.
contradictory
Okay.
flavor.
Okay.
Yeah, but that's an interesting thought because I'll be going towards somewhat different approach in the later half.
Okay.
So yeah. Okay. So you might press me, why on earth be bothered about connective logic? Fair enough. So as always, I rely on my favorite Grand Priest. So my personal reason, this is not a motivation shared in general, but my personal reason has been dialethism. So I learned that some of you are interested in dialethism, so that's good. And in particular, I was trying to face the objection by Grand Priest, who claimed that classical negation doesn't make any sense for dialetists. Now, as a person who loves classical negation, I wanted to see how I can overcome this criticism. And in fact, there is a way to keep the classical negation within the dialectic context without facing the trouble that Graham has been pointing out in this monograph. And what I started to think then is to think of a propositional logic in the following way. So namely, if you think of these formal theories, in some sense, arithmetic or set theory on all these theories are very concrete, right? And then the first order logic is somewhat more general in the sense that there's no theory-specific axioms included anymore, right? And then if you go up to the propositional logic, it's in some sense maximally abstract, in a sense that you just don't even look at the content of these propositions anymore. You just look at the status of those propositions being true or false or whatever, right? And if you're interested in dialethism, right, there's going to be propositions that are true, false, and also both, right? The both is the dialethia. Normally, if you look at paraconsistent logics like logic of paradox, you don't see these dialethia in the propositional language. Normally, you just get to see the dialethia only in the theorizing level. But I thought, okay, if propositional logic is going to be seen as an extreme abstract form of the target theories, maybe one might want to have that sort of structure represented already in the propositional logic. So for that purpose, I was starting to look at the functional complete expansion of the logic of paradox. And I had already added the classical negation. It was one step away. And then it turns out that this connective conditional would be an extremely elegant tool for my purposes. So namely, you can basically get a functionally complete logic that expands LP by having classical negation, the Morgan negation, and the connexive conditional. And that's it. So it's a bit like classical logic can be characterized by classical negation and a classical material implication. Similarly, we only need one more ingredient while we make this conditional into connexive one. So I thought, okay, that's surprisingly simple and beautiful. So that was my personal reason to get into this connexive enterprise. So if you're interested in power-consistent logic, if you're interested in dialethism, then there's going to be lots of interesting rooms to be played around with this connexive condition. Now, given all that, what do I want to do today? Well, first I'll just give you a very biased, because I also like Heinrich's work very much, and I've been working on it a lot. I will just give you a hint at how we are getting connexive logics. Muha already asked me about the strength of the conditional. That will be one of the things you will get to see. And this will be closely connected to my personal reason. And then later on, I will just turn to new instances of connexive logics that would somewhat surprisingly connect the modern founders, Angel and McCool, on the one hand, and Heinrich's work. So this part is less connected to my personal reasons, but it's not completely unrelated either. So we'll see eventually what I mean by that. And for this presentation, I'll just focus on propositional language, a very simple one with negation, conjunction, and a conditional. There are some work doing quantifiers for connexive logic. In a seminal paper by Heinrich in 2005, he even added some modalities on top of connexive logic. So that's possible, but for today, I'll just focus on this simple language. Okay, so hopefully I've not lost any of you yet. Okay. Now, connexive logic. So I'll first start with the original first system devised by Heinrich in 2005. And that system is a very simple variation of a power-consistent logic called N4. And if you don't know N4, N4 is an expansion of basically intuitionistic positive logic by something called the strong negation. So normally people would write it with this wiggly negation. Pseudo negation. For N? Oh, for N. N is for Nelson. Yes, because it was the Nelson's logic. Well, originally it was N3, so it was more like the power-complete version. So it's not only Nelson, but I always can't forget the name, but there's another person who worked with Nelson who turned the power-complete thing into also power-consistent. So, but yes, it's N3 is the original system, and N4 is this power-consistent version. How does it look like? Well, it's basically like an interpretation for intuitionistic logic, right? So there's going to be a non-empty set of worlds. There's going to be binary relation over W, which is reflexive and transitive. The valuation function is looking like a four-valued thing. It's a power set of 1 and 0. Intuitively, you can think of it as a two-valued relational semantics as well, with heredity, both not only for the verification, but also for the falsification. So if you forget about the 0 part, it's going to be basically the intuitionistic one, but you also do the falsity part as well. And then how are the connectives interpreted? Well, for the negation and conjunction, it's basically the FDE, or even classical, basically, right? So negation is true at the state, if and only if negated is false at that very state. Negation is false at the state, if and only if the negated is true at that state. Conjunction, very similar. No funny business. For the verification condition, for the conditional, it's the intuitionistic one. You look ahead where it's accessible. There, if it's verified, then the consequent needs to be also verified. Okay? You mean the intuitionistic one? Well, in this language, we can't define the Folsom constant, actually. So here it's a purely very positive thing. Yeah. And for the falsity condition, the conditional is going to be seen as false or falsified if and only if you don't move the state. And if the antecedent is verified and the consequent is falsified, then you conclude that, okay, the conditional is falsified. Yeah, Paul, go. Basically, there's also always the dialethic interpretation. So you can throw in the power consistent value, the both value, assign both values to all the atomic formulas, and that value will be closed. So you just can't really define the. Yeah, it's expressively weak. That's it. Yeah. So this is N4. So this is sort of there. And what we do is just to look at this falsity condition for the conditional, highlighted in red, and change it in this way. So you say the conditional is false with a bit of dynamic flavor as we have for the verification condition. Say, well, you look ahead, and if the antecedent is verified there, that's the same with the verification condition. Then if it turns out that the consequent is falsified at the very state, you would say it's going to be false, the whole condition. And once we do that, then the rest flows as always. So we can define the semantic consequence relation by looking at all the models and so on. And what we get is this drastic result, as I've already highlighted earlier. So both the conjunction elimination and its negation will be valid. Yeah. Yeah. So very, very intuitively put, right? You see this condition, and given the verification condition, right, you can rewrite this in terms of A arrow negation of B, because this is falsified here, negation of B being verified, right? And then the left-hand side is still having the 0 here. So in order to make it into a verification, you just add the negation, right? Then it's going to be the negation of A arrow B, if and only if A arrow negation B being verified there. And as a result, whenever there's an outer negation of a conditional, you can just push this negation in to the consequent, right? And what we will have is another instance of conjunction elimination, therefore we get this validity. Note that for this very reason, we can't add the ECQ, right? So it's going to be, it can't be like N3-ish flavored system. Another interesting thing is that the positive fragment is completely intuitionistic. And normally the law of exclumiddle would destroy the intuitionistic flavor. But here, by tweaking the falsity condition a little bit, as I've shown you,
what ECQ is.
Oh.
So this, yeah.
ECQ
and LEM
is
also, because it's a mixed audience.
yes.
So it's better.
That's always good. No, thank you, Michiel. So ECQ is this. Yeah. Thanks, Michiel. And normally, the law of exclumiddle is seen as a bad guy in the constructive context, messing up the constructive flavor. But in this case, actually, surprisingly enough, even if we add the law of exclumiddle, the positive fragment actually remains intuitionistic. So it's kind of interesting that the tweaking of the falsity condition of the conditional influences the positive behavior of the conditional in the presence of the law of exclumiddle. Yep. Yeah.
Spanning circle is not the negation of 0 belongs to
Sorry.
uh,
This condition?
one belongs to IWA or B, if
Yes.
and only if that condition is not the negation of the second condition for 0 belongs to.
No. No, it's not.
Not. No?
No, because if we negate this condition, it's going to be something like for some point at the future where the antecedent is verified and the consequent is not verified, right? But not verified and falsified is now going to be a separate issue. Yeah, it can be both. Yeah, exactly. Exactly. No, thanks for your question. Shankar.
Say that the positive fragment is still impressionistic.
Yes.
Do you mean that you cannot do an OR introduction? Is it?
Or introduction?
Yeah.
No, we can. We can.
You can?
Yes.
So in what sense is it?
In the sense that it doesn't prove the Peirce's law. So the, well, we didn't include the disjunction, but that's definable by conjunction and De Morgan. So this part is going to be completely identical to IPC plus. So in particular, the Peirce's law. This will remain invalid. So everything you have in the positive intuitionistic logic, you have. Nothing you don't have would sneak in. Yeah. Good. Okay. So that's the basically the system from 2005. And then we can do all sorts of variations. So for example, we can take the four-valid logic. So here the interpretation is just a four-valid valuation function, right? There's no worlds, whatever. The first clauses for negation and conjunction is exactly the same, like in C. For the truth and falsity condition, for the conditional, the truth condition is the classical material, right? No funny business. And then there is this four-valid logic called HPE by Arnon Avron, where you have the falsity condition like in N4, basically. So this is basically a system where you just look at the class of models with one point in the model, the classical extension. Then you get this one. And again, you do the same trick. You look at the falsity condition, and then you just change it a little bit, like the truth condition, right? And then what you get is another connexive logic, basically the classical extension. So if you add the Peirce's law to the previous system, then you get this four-valid logic. Now, if we write the truth table, then last night we had a discussion with Mua about the talk last night, yesterday, and then in particular, the truth table will start to be not closed under the classical values. So normally, even in four-valid logic, right? Normally, when the inputs are classical, so at these four corners, it would spit out the classical value, normally, right? But what happens in this case, in this MC, is that these are fine, but afterwards, it's going to be filled with B's everywhere. So in particular, with the classical inputs, the output would be non-classical. So that's very unusual. That's one way to see the contra-classicality that Tomasz mentioned yesterday. So it will be somewhat unusual, but you can write down the truth table like this. In the case of Nelson logic, these occurrences of B's will be replaced by T's. If you have just T's here, it's going to be the HBE, but by adding the connexive tweaking, you get this one. Right? Good. And then we can do also, because it can be paraconsistent only, you can kill one of the four values and get into a system called CLUNS or LFI1 or so on and so forth. And you do the same trick. You have the falsity conditions saying the conditional is false if and only if antecedent true, consequent false. Again, you do the same trick, and the resultant logic would now look like erasing this n value, basically. Then you get the 3-value logic, and still you have these non-classical outputs, even when the classical inputs are there. So this can be seen as a system that expands logic of paradox. And then we can also go to a much weaker system than the intuitionistic one, namely the relevant logic. So there's something called logic BD, explored by the relevant logicians. Especially, there's a paper by Graham Priest and Richard Sylvan from '92. And then, if you know, then you know. If you don't worry. But basically, the relevant logics are relying on a ternary relation rather than the binary relation in characterizing the truth condition for the conditional. And there's been a little open problem to deal with the falsity condition and to find the appropriate proof system. But it turns out that we can again apply the same trick to obtain connexive logic, and it works perfectly smoothly well. And you can see that this trick, therefore, is applicable regardless of the strength of the arrow. So it can be as weak as relevant arrow, it can be as strong as classical one, it doesn't really matter. Depending on what you look at for the truth condition, you just take that way of considering the truth of the conditional, and you sort of carefully apply it in the falsity condition, the only change being the consequence. And that's it. So it's seemingly too simple, but that would be one of the ways to get the connexive logics. Now, as I said, this can be seen as an open solution, partial solution to the open problem. It's also sort of interesting that depending on the way you treat negation, Aristotle's thesis is going to be very problematic. So if you know, there's something called relevant logic R in the literature, and normally you would treat the negation in a different way. So you don't do the truth and falsity conditions, you do it with the so-called star semantics. And if you do that, there's going to be some implicit strength being added to the negation, and that would already be a problem even with the relevant logic R. So R is weaker than the intuitionistic one. But if you treat it that way, Aristotle's thesis, if added, would trivialize, so everything will be provable. And this shows that, okay, if the negation is treated in a somewhat different way, then we can even have the material, so the classical arrow together with Aristotle's thesis. So the treatment of negation is quite crucial here. Okay. Now, here's a quick summary. How does Heinrich's approach work? It's basically you just modify the falsity condition in a careful way by looking at the truth condition for the conditional. I focused on the semantics, but you can also do various proof theories. So you can do secant calculus, you can do natural deduction, not only axiomatic proof systems, and you can do cut elimination and so on. So proof theoretic treatment was almost impossible with the earlier systems. But now, thanks to Heinrich's system, that's all possible. So that's quite a remarkable thing. And also, it's not only my opinion, but Graham Priest in the Blue Book. By the way, I recommended the librarians here to buy this book, the Blue Book. But anyway, Graham describes this Heinrich's idea being one of the simplest and most natural system of connexive logic. So there's lots of systems, but this is probably the case. That's the overview. Now, you might have a complaint. Hitoshi, thanks a lot, but contradictory propositional logic, that seems to be way too much. Fair enough, but I'm not going to be fully defending that here. But if you're interested, you can look at, check the website run by Heinrich Wansing, because he's now running a big project featuring the contradictory logics. So if you're curious, go and check. I'm not going to be defending that, but you might say, related to Ramanujan's question, you might say, whoa, hang on, negation shouldn't be treated that way. That was all wrong. We should deal with negation or define or understand it as arrow foursome. You know? Goodbye to power consistency. We need the good old explosive negation. Fair enough. And there can be more complaints. Tomasz might say, well, look, Hitoshi, this is not classical enough, and so on. All the complaints, very welcome. But I'll just focus on the second one. And this understanding of negation is sort of nicely echoed by a paper by Andy Kapsner, my co-author, because he required that. One more complaint, please. Yes. So there's going to be at least two ways to do the proof theory. So one way is to treat the formula and the negated formula separately, right? So there's going to be no negation introduction. Yes, exactly. So there's all sorts of ways to deal with that. You can complain that's a cheating. Fair enough. It's not going to be increasing in that way. Yeah, no. I think rather the earlier work, they won't even have a decent sequent calculus. So yeah. Okay. Yeah. So looking at Aristotle's thesis and Boy's thesis, I can just write down Aristotle's thesis just one more time, right? It was something like this, one of the theses. And earlier on, we've been interpreting this negation as something that can be contradictory, right? And you say, no, that's all wrong. This should be something much, much stronger. When we say no, not, right? It needs to be exclusive something, right? You might think. And this is what Andy nicely documented in this short paper from 2012. So he not only required the Aristotle and Boyce's thesis, but he said, no, we need more conditions. For example, this formula, the negated formula, should never be satisfiable in any model. That's what this Aristotle's thesis must be sort of trying to deliver. And likewise for the Boethius thesis, he required that A arrow B and A arrow not B should never be simultaneously satisfiable. That's what Boethius thesis is probably trying to say, if we, for example, write it in this form. From A arrow B, it should never be the case that A arrow not B is satisfiable. That's a fairly strong and maybe intuitively plausible looking condition. But this has been a pain. So there was one system from this Angel McCall that would satisfy this condition, but all the rest were not satisfying at all. In fact, my first visit to Kolkata was back in 2014 for the Power Consistency Conference, and I clearly remember that I was sitting in the balcony with Andy at ISI accommodation, talking about the strong connectivity, not getting anywhere. So it's been a pain for a long time, but finally, after a lot of discussions, we are getting something out of it. So that's what I'll be talking about. I'll just give you a little brief overview of what Angel and McCall did in their seminal work. So for Angel on the left, he was interested in the subjunctive conditionals and tried to formulate this principle of subjunctive contrariety and give some form of flavor to it. So that principle is something like, if P were true, then Q would be true, and if P were true, then Q would be false, must be incompatible for the subjunctive conditional. And this led him to formulate one system, that's the seminal paper that I mentioned earlier. For McCall, Stores McCall, he was interested in many things. He took up Angel's paper and explored that very well. But at some point, McCall was also interested in recovering the Aristotelian syllogistics in full. So if you just try to do the translation in the modern term with the classical logic, not all of them would be recovered, especially all A's B to some A's B isn't going to be recovered, but by going connexive, you do get it back. So that was one of the motivations for him. And given these motivations, Angel had a system, and in order to prove the consistency of his system, he made use of this four-valid logic. Now, don't try to read off the intuitive meaning of these values, because it's sort of made up just for the purpose of establishing consistency. But Stoss-McCall really took this as a serious option. So he later axiomatized this truth table and named the system as CC1. Now, if you look at Angel's paper, after establishing the consistency, he says there's going to be all sorts of desirable looking properties being lost, invalidated by this truth table. And so, for example, the conjunction elimination goes, its contrapositive form goes, importation exportation goes, permutation goes, introduction of conjunction goes, and so on and so forth. Now, I was looking at this result with this strong connectivity obsession in my mind, and then realized that there's always one value doing all the harm, invalidating everything. So what I did was to look at this truth table, right, and then eliminate the value 2, right? So you look at the submatrix, but it's not quite the submatrix, because if you look at it carefully in the negation, which is taken as more like a Boolean complementation, even after eliminating the value 2, the output of the negation of 3 will be still 2. So then Andy and I thought, okay, maybe we can just turn it into a different value 4 by thinking that negation is arrow foursome, right? So there's going to be an arrow here, and then the foursome value would be understood as value 4, and so a arrow foursome would just give rise to that. In particular, 3 arrow 4 would be 4. So you get that truth table. That's how we got this little logic. It was a big surprise for us that it turned out that we were not the first one to look at this. So in a paper by Sangapanova, actually he's one of the invited speakers this time again, in a paper from 2007, where he was writing about the semi-Heiting algebra, he was making use of this basically a three-element algebra. It also turned out that Davide Fazio, Antonio Leda, and Francesco Paoli, in their work on connexive logic, they boldly claim that intuitionistic logic is a connexive logic. If you're curious, I can just explain a bit more about that means later. They also came up with this truth table as well independently. So it's always sort of nice to see that what you found can be also reached from another perspective. So therefore, it doesn't seem to be a complete garbage. So my sincere thanks goes to Francesco for putting this together, information to me. Okay, now what happens is that CC1 was one of the seminal systems, but then it has a lot of problems, loses all sorts of nice properties, but this M3 turns out to be extremely nice. So for example, Aristotle's thesis is going to be fine. The strong connectivity, this onsite 1 and 2, so those are going to be fine anyway, but that would be kept. So connexive thesis, connexive flavors are going to be all kept, basically. Now, note that the negation is understood as arrow foursome, right? So it's really like, when I write the Aristotle's thesis, the outer negation is really like an exclusive device, you know? There's no room for dialethia. For the implication, it's been always kind of problematic. So for example, the CC1 wouldn't have the permutation. But if we look at this new three-valued system, we actually get at least BC and I. And that's good. Because BCI is basically a linear logic, a fragment of a linear logic. So yesterday we had a talk, lovely talk, about the linear logic. But that's what we get. So if one is convinced that BCI is one of the reasonable pointers to start and look at the conditional, then this is perfect. Note that there's a little bit of a peculiarity that if you look at the truth table carefully, then whatever formula, implication of a formula that is valid in this system, would also have the version with the biconditional instead of the conditional being also valid in classical logic. So in particular, all the implicational formulas in this M3 would have even number of occurrences of the variables. Okay. For conjunction, conjunction is also a mess in connexive logic, but what we have is that exploitation, importation is going to be kept, as well as the adjunction. So that's also good news. Some people would see the conjunction elimination as crucial for conjunction, but the linear logic, relevant logic people have been working on this so-called intentional conjunction, the fusion connective. So there is a sense in which this conjunction is a conjunction, it's bunching together the premises. So that's quite nice, and we can still safely claim that, yes, look, this is a conjunction connective, given these properties. So that's quite nice. And then there are some other theses discussed in the literature of connexive logic, known as Abelard's thesis and Aristotle's second thesis. Abelard's thesis really look like the principle of subjunctive contrariety formulated by Angel. Aristotle's second thesis will have the negation in the antecedent rather than the consequent. And these get sort of discussed in the conditional literature, and we'll get those things as well. And for the purely negation-related principles, we do lose one thing from CC1, namely the double negation elimination. But this is partly because we are taking this more intuitionistic-like definition of negation. So we are sort of bound to lose that. Note also that there's an interesting subtlety when it comes to this explosion ECQ thing. That, for example, this ECQ1 with the consequent being B, arbitrary formula, and here being the Folsom constant, would make a difference. So we can't have the arbitrary one, but we do have the one with the Folsom constant. And we also get the rule form ECQ. So there's going to be a subtlety, interesting subtlety, when it comes to the ECQ thing. And finally, these systems are consistent, unlike Wansing style systems where you have a formula and its negation being valid. We don't get that. Yes? Yes?
More than one values given, attached to a formula,
Yeah.
not just one value, then what will be the semantics of Folsom?
Well, in this case, it's just a standard 3-value logic, Michiel. So it is standard 3-value logic.
Oh, okay.
So in this case,
logic. Okay, yeah.
it's like this.
So
you know?
it is the
So the Folsom constant is 4. This is the false-like value.
okay.
Yeah.
Okay, just one value.
Yeah. Just one value. Yeah. Exactly.
Okay.
Yeah.
Okay. But what in general, Moa's question, as far as I understand, why is it that Folsom cannot be taken? You mentioned that Folsom cannot be taken in.
So that depends on the system. So in Heinrich's system,
Yeah.
that's expressively weak. That it's a bit like logic of paradox, where you don't get the Folsom constant being definable. And it's a similar phenomena there. So basically, I can just use this one. When you just assign the value B to all the atoms, right? In particular, implicational formula would receive the B values as inputs, and it would still output the B value. So it's closed under the B value with respect to all the truth functions: negation, conjunction, disjunction, conditional. So therefore, we will never have anything like F here, because this, whatever you input, output is always going to be the value B, never anything else. That's the reason why it's too weak. It's a bit like LP, basically. Yeah.
Okay.
Yeah. Okay. Where were I? Yes. Okay, so it's quite interesting, but the system CC1 has been criticized quite heavily by Routley and Montgomery soon after Storrs-McCall produced a lot of work. And those sort of weird features would carry over to M3. So that's not good. In particular, given the three values, right? In the case of FDE or LP, we can have a very intuitively plausible reading of the values. Regardless of you agreed with the system or not, you can still understand it. But in the case of M3, it's extremely difficult. It works technically, but less technically, it's very hard to make sense of those values. So that's a problem. So what we do then is to propose a subsystem that seems to be sort of the important bone of this system. And to this end, we change the language a little bit, so we start to take the Folsom constant as primitive rather than defined, and take the negation as defined. So that's a little change from the discussion so far. We take the BCI as the arrow, and then we take the importation exploitation to make sense of the conjunction properly, right? And then we add these additional two axioms that's related to the way how conjunction and the conditional is related when it's put in the antecedent of a formula where the consequent is Folsom. Now this looks a little bit ad hoc, but this is basically the way to recover all the connexive flavor. So in some sense, this would document nicely the basic features of the system, and we add modus ponens. Okay? And if we have this, then we can define the negation as arrow of Folsom, and then have contraposition. We can have double negation introduction, because we have the BCI strength. And then we get all the connexive theses as expected, right? So it's a fully connexive logic without any compromise. And we can get the strong connectivity. So far, I didn't add any specific axiom for the Folsom constant. So it's a bit more like a minimal logic at this point. But you can adjust the strength of the Folsom constant, and then you can ensure that it's going to be satisfying the strong connectivity as well. So that's quite nice. But the story ends here because we just don't know anything about the system AMW. So that would be the reason why I came here to share this system and see if someone would be happy to join us. So let me just quickly summarize the talk. So what I did was to try to explain the connectivity can be, for one thing, achieved by this very simple idea by Heinrich. You look at the false-state condition and you tweak it nicely, you get connectivity. But that might be a problem. You might not want to go on that line of thought. So we wanted to look at this more exclusive way of reading negation. And to this end, I looked at the CC1, and then by killing one of the values, we got the system M3. This is substantially better than the system CC1, but still it has some problems. So we formulated this little expansion of BCI that would nicely capture connectivity. And it also can be seen as a bridge between this Angel-Merkel tradition and Heinrich's tradition, because we will get the biconditional. So the negation of B being negated is going to be equivalent to A arrow negation of B. Here it's going to be the very standard one for the MW and M3, so that it's yes. Lots of open problems. So Andy and I formulated this system AMW with the hope that we will get deeper understanding of connectivity, but we have loads of questions that are naturally arising. Algebraic semantics for this system. So it's a BCI system, right? So the BCI is fairly well understood. The question is, how can we top up this connexive flavored axioms, and how can we capture that in algebraic terms? Maybe there's going to be other semantics, interesting semantics for MW that would shed some interesting light on connectivity, in particular from the linear logic literature, combinatorial logic literature. That's all widely open. Maybe there's going to be an interest in formulating sequence calculus. Again, for BCI, there's a nice sequence calculus already. So it's a matter of seeing how we can accommodate the additional axioms that we've added here. There's going to be also interesting a question concerning extensions of AMW. So you can think of systems between AMW and AM3, and then explore what might be the systems in between that are worth highlighting and exploring further. If none, maybe that's also a nice result. How many systems are there going to be? Is there going to be a continuum many intermediate systems or not? And finally, we can also ask the question, do we want a disjunction? If so, then how should we add that? And also, we have the intentional conjunction, not the extensional conjunction. Would there be any reasons to add that or not? If not, why not? If so, why so? So there's wildly many questions being open with this system, but hopefully this will be a system that would, by exploring, giving us a lot of new insights to our understanding of connectivity, and also some kind of interesting connection to linear logic, combinatory logic, and so on and so forth. So that's what I wanted to say, and given that I'm in Kolkata, I say to you, Dhanyabad. Thanks a lot.
Thank you, Joshi, for that very, very nice presentation. So this is open for questions. He's finished well within time, so welcome.
Will you please show me the some of your slides? I mean, the ending slides.
Yeah.
Just
This one.
before conclusion.
Yeah.
Just before conclusion.
Yes.
Yeah. No. Just before that. Yeah. Because where? Yeah. This one.
Yeah.
So the last two are the syntactic properties of false sum. Is it?
Well, in some sense, yes, but in some sense, no, in the sense that it doesn't really tell us, for example, what follows from the Folsom constant, right?
It doesn't say.
But in some sense, it is.
But
Yes, you're right.
Folsom, I think you have taken Folsom in your language.
Yes.
This is a constant, right?
Yes.
Okay,
Yes.
so it's a propositional constant.
Yes.
That way.
Yes.
And we expect some properties of Folsom.
Yes.
And
So
these are the only properties that you have taken.
at this point, yes. But we can, for example, we cannot add this one. This we
Yeah,
cannot add.
You cannot add, yeah.
But we can add the rule form one. This we can add.
Okay.
Yes.
But this will follow. These will follow.
No, this we need to add. This system won't prove this. Because this is a bit like a minimal logic bottom.
Sorry, I don't get you. Are you going to add also this last one as a rule?
We can add it, but we didn't.
You didn't.
Yes, but we
So
can.
in this system,
Yes,
by Folsom,
yes,
the only syntactic properties are these two.
yes, that's right.
Nothing else.
That's right.
That's what I mean to say.
Yes, that's right.
But when you add that,
Yes.
I mean this one, yeah. Oh, what happens then?
The most crucially, the negation would start to be obeying the explosion. That's the crucial difference, right? In minimal logic, we don't get that.
Yeah.
So this will not hold in AMW,
Yeah. Okay.
but
yeah.
we would start to get this if we add this one. So if you really want to make sure that it's like an exclusive device,
But still, it will be different from classical.
yes, it would be different from classical logic. Yes,
Okay.
yes. The extreme extension would be the M3.
What
the
is
early.
the algebra here ultimately?
It's this one. So
No, abstract in the abstract case. Oh, semi-hating.
yes,
Semi-hating.
it
okay.
can be seen as something related to that.
Well,
Yes.
all right. So this is all right. And now another point is this.
Yes,
Beyond this logical part and the algebraic part,
yes.
what could be other consequences of this system. We know that paraconsistency
Yes.
emerged with at least one hope there from physics, that is to address the quantum issue.
Yes.
That was, Da Costa's original
Yes.
idea,
Yes.
and
Yes.
which continued for some time,
Yes.
where both yes and no has to be treated in some sense. I mean, it's just a question to you. Have you ever thought of it? I mean, how to get some of your, at least philosophically, these things beyond technical logic and algebra?
Yes, good. I mean, so I think if I can answer your question, not specifically focusing on this new system, but something else, I think one of the interesting applications would be of connective logic. I mean, right? Would be the discussion of how to negate the conditionals. And there's been surprisingly many discussions where, with some conditions being imposed, this would be something like this. Right? But there's going to be all sorts of variations, because some people will say, well, there's going to be two conditional connectives, the main one being the material, and this the connective, right? Or if you look at the Stoneacre seminal paper, then there is this biconditional with the condition that the antecedent is possible, for example, and so on. So there's all sorts of different ways. And another thing is to say the negating the conditional would involve a modality here. So A arrow B is false, if and only if A is going to be possibly entailing the negation of B would be sufficient, and so on. And then all of these cases would be interestingly close to connective logic. So I think, given all these discussions about how to negate the conditionals, I think connective logic can be really offer a firm, formal reasons why all of those somewhat less formal-looking discussions can be having some formal grounds. About the quantum things and so on, that's super interesting, but I don't know what I can say. I mean, I can add that for this earlier part, given this contradictory flavor, negation inconsistency, Heinrich Wansing started to talk not dialethism, because he doesn't want to talk about metaphysical ontological issues, but he coined the term sorry, I forgot. But something that he wants to talk about the true contradictions in a very informational terminology. Now, what that information means and so on is not so clear, but there might be some reasons to be interested in that as well. But about that, you have to. There's a paper by Heinrich in Erkenntnis where he tries to talk about this dimathematism. So, mathematia is supposed to be something not ontologically committing, not metaphysically committing, something somewhat neutral. Yeah, but thanks for your wonderful question. Yeah.
Last one, AMW. You're stipulating that the negation, the conditional is negation of the condition, right? Yeah, can you
Yes.
say that?
Good, Moa. So there's a lot of trick. Let's see. So I've assumed that this guy is going to be equivalent to this, and this is basically, by definition, is going to be like this, right? Now, if you look at this one, we have the exportation, importation, so the trick is that this will be equivalent to this. which is basically the negation of the thing, right? So it's quite crucial that it's going to be in this form with the exportation importation. Note also that if you look at the connexive thesis, right? And I emphasized earlier that this shouldn't be a biconditional, right? But if this is a conjunction, then this is something we all love and familiar with, right? It's a law of non-contradiction. And you see the way also Heinrich is changing the falsity condition, right? So this used to be in classical logic something like this, and we are replacing this conjunction by a conditional. So there's a sort of flavor of bending the conditional towards conjunction, you know. And you can see by this axiom also, right? You're basically saying, whoa, if the conjunction, the conditional is in the premise antecedent of a conditional where the consequent is a falsum, you say, yeah, it's basically the same thing. So in some sense, you're just sort of making these two connectives somewhat close. Well, so I think for the connexive thesis, you only need this. So you only need this direction. So I think you only need the this direction. So we only need the importation, I think, for the Boethius, right? And then the exportation will be for the converse of Boethius. So there might be some reasons to say no. Or you can just reject one of the axioms as well, right? Yeah, I think I prefer to have exportation importation just to make the conditional and the conjunction lining up very well and keep their meaning quite clearly. So there can be an option to just throw away the second one for the purpose of removing the converse of Boethius as well. Indeed, yeah.
Sorry, anyway.
Hi, Tashi. It's a very wonderful talk. Thank you so much. Like regarding Mihit's question, you were mentioning some possibilistic application of negation, and that led me wondering, what about kind of modal operator connections? Modal connections, modal logic connections.
Yeah.
With this kind of sieve logic.
So if you look at the original C, Heinrich did a modality on top of it. So basically what happens, well, I mean, intuitionistic modal logic is a mess, as we all know. But what he did in part is that you can take this system and add another accessibility relation and make use of that to characterize the box and diamonds. So if you want, you can do it with two additional accessibility relations. I think he did only did it with no, maybe he added two of them. Now I'm mixing things up a little bit, but you can do that, and then especially, well, at this point you don't have the Folsom constant yet, so it's going to be like a positive intuitionistic logic with a modality. You can add the Folsom constant as well, and then it's going to be proper expansion of intuitionistic logic with strong negation and the modal connectives as well. There is a question why, but technically that's possible. But I just find this issue of modality in intuitionistic logic in general very difficult. It's so wildly different from one to another. But yes, that's definitely possible. There might be some good reasons to add modalities. And then also for the embeddings and stuff like that, you can embed it into positive intuitionistic logic. So basically you push in all the negation in front of the atoms when necessary, and then these negated atoms would be embedded into fresh atoms, and then thereby you can just embed it into positive intuitionistic logic. So that way you can also see the modal connections as well.
I do have some questions. Maybe there are not time or
Regarding model logic, if audible, yeah, regarding model logic, you said that we can add accessibility relation and model operator, and we can proceed. But we would like to have a situation where this arrow and model operator also interact, some kind of interaction. For example,
Yes.
a rough inclusion Anirban presented. So arrow is related with the model operator. Some kind of connection is there.
Right.
So I think possible.
Yes, yes, there's definitely, and yes. So when we were talking last night, we were talking about for example, the for valid context, right? And then if it's in the for valid context, then it's going to be easier to do the modal logic because it's going to be somewhat more standard. You know, you just add the worlds and the relation and stuff like that, or you can just look at the for valid case like this, and then you have all the things, and on top of that, right? So we were talking about this Tetler valent modal logic, right? So on top of this, you can add a for valid box operator of the form something like this, and after adding this would essentially expand the strength of the expression because we didn't have the opportunity to have other values than b when the b is the input, right? So this would properly strengthen the system and so on. So that's definitely a possibility. So we can do either in a truth functional way on top of for valid logic, or you can just add the worlds and do all the other kinds of modality as well. So that's both options are possible. Yeah.
So thank you Hitoshi once again. Yeah.
Thank you very much.
Thank you very much. They're setting it up, Sujata. So we are ready for the second talk. Yeah. So we have Dr. Saurabh Dar from St. Xavier's College, and he'll be speaking on basic mathematics beyond classical.
Thank you, Mohadi, and good morning, everybody. Today, actually, I'm not going to talk about any brand new result of my work. So basically many of you have heard the mathematical portion, which I'll say at the end. The results you have heard before. But what I actually want to do today is that for the first time, like I want to give, like for the first time in a presentation, like I want to say that what is my motivation of doing that work till date. So before starting this, like I want to mention that today I'm really missing Ranjan sir, like who's like in whose memory we are conducting this conference this time, because like I know that since for the maximum time, like in this presentation, for the like I'm going to talk about my motivations, so that means that it is possible that I'll be very much criticized at the end of the talk. But that is probably the reason why I'm missing him. So because like he encouraged me like in all the aspects besides sir, like all the other members of Logic Circle and the other logicians in India, like he encouraged me so much that today really I'm missing him. So I believe that he is listening from somewhere. So Ranjan sir. Okay, so well, so and then I'm taking the opportunity to start with the dialogue, the famous dialogue of Arundu Didi yesterday. Arundu Didi, wife of Ranjan sir, she said that tomorrow I'm not going to come, I'm not going to listen to your talk because you are going to say something very much mathematical. So I'm assuring you that this talk is not going to be mathematical. At the end, I will touch a few. Then what is this? Like, in this talk, I will try to first give a notion from myself itself. So as I've said that I might be criticized a lot, that a notion of basic mathematics and this thing like that is the case that the classical set theory like is the only place where we can talk about this basic mathematics. That will be the main motto of my talk today. Okay. And then at the end, if I have some time, I'll go to some results on the some results of the non-classical mathematics which I'm doing well. So, what do we mean by non-classical set theory? Here, what I have just written that by a non-classical set theory, we mean a set theory having non-classical underlying logic, whereas the set theoretic axiom system is a fragment of ZFC. But we are open to the other things as well. Like, so saying that we may discuss about, like, if things goes like that, we may discuss about the logic, the basic logic which is classical, but then some other logical system other than the ZFC, or maybe the non-classical and then ZFC or more than ZFC. So we are open to that thing as well, but mainly I'll focus on the thing written in the black ink. Okay. Now, that means the basic logic will be non-classical, and on the top of that, the set theoretic axioms will be a fragment of ZFC. Okay. Classical set theory. Well, today, actually, I'm going to compare this classical and non-classical set theory in the glasses of mathematics. So, what I'm saying that, as I've said that I might be criticized too much, that of course, it's true that talking about the comparison of classical and non-classical set theories or the classical or non-classical logics definitely doesn't depend on only the mathematical perspective. But of course, it is also true that this is a very important point, right? That talk about the validity of two logical systems or two logical set theories, like to set theories, one classical, one non-classical, only depending on mathematics is not a good thing to do, but of course it's important that we cannot like we cannot say that, well, so we just like refute this part and then talk about these things in some other aspect. Of course we can do it, but today I am taking this thing to discuss about or to talking about the comparison between classical and non-classical things through the glasses of mathematics. Okay. Now, the title, you see that, is it mathematics or basic mathematics? Which one we are talking about? Then, here I'm going to quote something here. You see that It's a debatable issue how much of abstract mathematics is needed in the development of science and technology. There are examples of different branches of mathematics which had no practical use at the time of invention, but eventually they were used to develop modern technologies. Like number theory can be considered as one such important example. And then G.H. Hardy, it might be a book, I think, so of G.H. Hardy, which is like this. So Hardy is writing, the theory of numbers has always been regarded as one of the most obviously useless branches of pure mathematics. Useless branches, he is mentioning. Then, the accusation is one against which there is no valid defense, and it is never more just than when directed against the parts of the theory which are more particularly concerned with primes. A science is said to be useful if its development tends to accentuate these existing inequalities in the distribution of wealth, or more directly promotes the destruction of human life. The theory of prime numbers satisfies no such criteria. Those who pursue it will, if they are wise, make no attempt to justify their interest in a subject so trivial and so remote, and will console themselves with the thought that the greatest mathematicians of all ages have found in it a mysterious attraction impossible to resist. But then what happened after a few years? We saw the applications of number theory in many different fields. One is like cryptography, then computer science, and many more, like in music as well. Like we are like nowadays number theory is used like to have some like apps like of music, I think. Okay, now for the layman, abstract mathematical problems may appear inconsequential, regardless of their significance within the field of mathematics. In the book A Mathematician's Apology, Hardy pointed that a pure mathematician generally does not create a new theory to apply it into the technology. The beauty of mathematics lies in itself, independent of its application. And now I am quoting from the book like Amimamsar Alo Adhare, written by Professor Mihir Chakraborty here, that this quotation is like, I like this quotation, and then that's why in this talk I have just quoted this one. It says that he wrote that usability is not an essential attribute of mathematics. Rather, it is like a side effect. So that is the word why I like this quote very much. The corner of beauty is its ultimate home. In this sense, mathematics is much closer to art or poetry. If there is any truth in beauty, then this truth is acquired by mathematics. Okay? Well, so, but it is also true that the presence of mathematics in our everyday life is invincible, right? So, no one of us can say that, look, I'm not doing mathematics from the point when I'm waking up and then till the time I'm going to the bed. So we are doing mathematics in everyday life in like numerous ways, like maybe knowing it or unknowingly. That mathematics which we are doing every day, knowing it or unknowing it, I'm referring that thing as basic mathematics. I'm coming to the formal definition here. But by the basic mathematics, what we are meaning is this, that the mathematics which actually we are doing every day in our day-to-day life, maybe knowing it or maybe not knowing it. But when we are going to the market, we are using it. We are doing something else, we are using it. Whatever we are doing, that thing is considered here as the basic mathematics, what I am considering. But then, if I take that thing as the basic mathematics, then you see that here I have written that the presence of mathematics in our daily lives is undeniable. The relentless incorporations of mathematics into everyday activities primarily centers around fundamental concepts, which is referred as basic mathematics in this presentation. This encompasses the fundamental arithmetic operations necessary for our routine tasks, right? But then the next slide says that what will be the domain of these arithmetic operations? Suppose we are taking arithmetic operations, we know that, as I have said, that whenever we are going to the market, we are using mathematics. But so in many places we are using mathematics, but then the mathematics is on which domain? That is the next question, right? Then I have just written this, that see, so we are taking addition, multiplication, exponentiations. Suppose we are taking these things, the operations, but then we know that these are the binary operations, the arithmetic, like the addition, multiplication. But then if I take the domain as S cross S for the binary operation, then what this S will be? The point is that we could take it as the real number. But you think about it, that in our daily life, do we really use irrational number? I don't know, like in measuring something or something else, like maybe we are using, but I'm saying that the day-to-day life we are using mathematics, that I'm talking about now. Are you using rational numbers? Yes, of course we are using rational numbers, but then how many decimal places? Like, is it like that it is not never ending, like going 1 by 3, like 0.3333 is going, like are we using this kind of stuffs? I don't know. Like for this thing, I'm keeping the possibility of S open, but for this presentation, I'm just taking the minimum which is required for our daily life mathematics is the set of natural numbers. So S is considered as a set of natural numbers for the time being. Okay? Well, but then here is the definition formally of the basic mathematics, that the mathematics consisting of the basic arithmetic operations, additions, multiplication and exponentiation, similar as the classical set theory, restricted over the set of all natural numbers, is called the basic mathematics. I could write here the operations I am trying, but that would be lengthier. That's why, like, I've just taken this thing as simple as that. Like what I'm saying, that the basic mathematics is what? Like a mathematics on which I don't know, but a mathematics where it is similar to the classical set theory when we are taking the restriction over the natural numbers. Okay? Because why we are doing that? I'm coming to that thing in the next slides. Through the basic logic of basic mathematics, the ground logic of the basic mathematics, I'm going to give the answer that why I have taken it like this. That underlying logic of basic mathematics will be taken by what? You see that whenever we do mathematics in our school level, like we are studying the mathematics, like we are studying addition, multiplication, and then we are going slowly. In our school, do we ever think that, or is this the case that our teacher says that, look, you are doing this mathematics, but there exists something behind it, who is also actioning from the disguise? No, right? That we do mathematics just by the sake of mathematics. Like we are learning all these things, and then addition, multiplication, and then in algebra we are going, then we are learning equations and so on, we are going. But we never think that there exists some logical system behind it in disguise. Did we? We never thought that, right? But then after some time, like if we are interested in logic, or in our like master degree, or maybe in undergraduation in some university or institute, teachers come and say that, look, behind it there is something which is called the classical logic, and we accept it. Why? Because without questioning that whether it is a classical logic or something else, without questioning, because all what we have learned, that matches if we take the classical logic, right, as a background logic. So there is no contradiction will arise. Like if that happens, that if that would happen, that we learn that suppose 2 plus 2 is equal to 4, and then like suppose, okay, so suppose we have learned that the addition is commutative. That means m plus n is equal to n plus m. We have learned it in our school level. We have saw that, yes, actually it is happening. M plus n is what? N plus m is what? They are same. But if that happened, that someone came later and said, some professor, that look, this logic actually act behind it, but if you take this logic, that property m plus n is equal to n plus m is questionable, then we would ask him that then why we are taking that logic behind it. But we are never asking why, because that kind of phenomena is not happening. So whatever we have learned, that are actually very much falling into the domain of the classical logic, right? That's what I have written here, that what should be the foundational logic for this basic mathematics, widely acknowledged as classical logic. And the reason what I have said, just written it here. Well, then this leads us to a crucial inquiry. Which aspect hold greater fundamentally? Basic mathematics or classical logic? You may find that, okay, so these two things are two different things, right? How we can compare. But my point is this. To be more precise, should we adopt classical logic as the foundational logic and then deduce the essential mathematical properties from it, utilizing them in our daily lives when needed? Alternatively, should we endeavor to comprehend the fundamental mathematics required for survival first and then develop a logical system to support it? Which one? Like, we learn mathematics from the beginning, right? And then at the end, we see that some classical logic system is acting behind it. But what happens if some other logical system which is not classical, this basic mathematics falls exactly same as what is following with the classical logic? Then what will happen? Which one will you take? Right? Well, so, is it expected or unexpected? Yes. So, my talk today is on this, that there exist non-classical set theories which coincide with the classical set theory when basic mathematics is concerned, but differ in the abstract level. That means that the daily life mathematics, the basic mathematics we are talking about, if that happens, that there exists, well, I'm saying that it actually is true that there exist non-classical logics on which, if you build set theory to talk about mathematics, because I am talking about mathematics, I'm saying. So if you talk about mathematics, and then in that mathematics, you just check that what is the basic mathematics, our daily life mathematics, that is exactly same as the classical one, what we are doing, what we have learned in our school level. Then going back, which one to take? This classical logic or non-classical logic? This one or this one? If we refute this one, why? Okay? So, this leads to the question, are we justified in considering classical mathematics as the only foundation of science and technology? Well, so, other than a few branches like quantum mechanics, where we already know that the classical set theory doesn't work. Achha. So, now I'll just come to the second half of my lecture, that 5 minutes is so enough. So, what is that? Like, here I have said few things that technically, that how we can find those kind of models. So you do not have to go into these things. What I'm saying is very simple, that the technicalities are written here, but what I'm saying is this. Suppose you have taken an algebra A and a set theoretic model V of ZF, and then what you do? By something you make this thing. This is a class of elements containing some functions. Okay, so you forget that what kind of functions are they. But with an algebra and a ground model of set theory, you have found some other collection, VA. Okay, and then what you have just written here, that after this, what do we do? That the language we extend, the language of ZFL is extended by putting the constants corresponding to every element here. We are just including it here, and suppose the new language is named as LA, then what we do is very simple, that we just say, suppose sigma is a sentence, a set theoretic sentence, then what we do? We say that look, for every set theoretic sentence, I am assigning a value of this algebra. That's all. You take any sentence and by this thing, whatever it is, forget about it. We are assigning a value to that sentence, a value of the algebra to that sentence. Okay. Then what do we say? That when we say that a sentence is valid, before going to that, we are now doing this. Suppose this is the algebra A. Then we say that, look, there you take a subset of A, which is called a filter. There is a definition of filter, which is also called the designated set. Forget about the definition, but you think that this is a subset of this algebra. Now we say that this sentence sigma is valid if this A belongs to here. Whatever the value of this sentence, if that value belongs to this particularly assigned subset, then we say that this sentence is true. That's all. Okay. That means giving an algebra A and a subset of this, we of course know that some sentence value belongs here, sometimes the sentence value doesn't belong here. The sentence whose values are belonging here will be called true, whose value will not be here will be called false. Okay. Now the point is that it is well known that if this A, you see here, it is well known that if this A is a Boolean algebra, then this makes all the classical set theoretic axioms true. We know that if this A is a Heyting algebra, then this thing makes all the intuitionistic set theoretic axioms true. Okay? Then what we did, you see that I have written it here, with the designated set is taken as only the top element of the Boolean algebra and the Heyting algebra. Okay? Then it is already a well-known thing. And we have exploited this result to have that kind of non-classical models. By what? By taking an algebra which is defined like this. It is just a linear algebra. I should not say the linear algebra because linear algebra has some different definition, but I am saying that this is an ordinal number you take, okay, well-ordered set you take, and then what you do, you just define like this is the algebra where this is bounded lattice having top and bottom elements 1 and 0 respectively, and this is a well-ordered relation on A, and you define the implication like this, that like when A is not equal to 0 and B is 0, then the implication is 0, and then when it is 1, otherwise. Okay. If an algebra looks like that, then it is called a PS algebra. It's a very simple, like that means a linear kind of thing you take, and then you know the meet and join, right? Meet is the minimum, join is the maximum, and then you know the less than equal to, which is in the lower step, that is less than the upper steps, right? And then you have just defined the implication like this. Only that much is something which is like counterintuitive. But then what happens? We can prove that if you take an algebra like this, that means now you take an algebra like this. Suppose this is our A, which is a PS algebra. If you take an algebra like that, then by taking an algebra like this and choosing a particular designated set to that, we can prove that that algebra can be a non-classical, like its logic can be non-classical. We can make that algebra such a way that you take algebra, you define your designated set such a way that it becomes non-classical. And also we can prove that if you take that algebra, then this thing, if you replace that algebra here A, then this thing becomes a model. This thing becomes a model of a fragment of set theory, which we started with, right? We said, what is a non-classical set theory? That the logic, underlying logic is non-classical, and the set theory it is satisfying is a fragment of ZF, right? Is happening, you see, for that algebra, that its logic is non-classical, and the set theory is a fragment of ZF. Then we have these theorems. We proved that you forget about the zero-like element, you think it as 0 in that model. What we have is this. For any PS algebra A in this model VA, all these things happen. That 0 is the additive identity, which matches with the classical basic mathematics, right? Basic arithmetic things. then associativity, commutativity, and the less than or equal to thing here, correct? Then this one, the multiplication, also satisfying the basic classical mathematics, right? Basic mathematics we are talking about here, and the exponentiation, the same thing. You just take all these things as a 1, 0 like that for the timing. Okay, so these are basic things, and you see that. So ultimately, you can conclude that there exist non-classical set theories, like which are by taking an A like that, making the model like this, which are such that it satisfies basic mathematics, right? If you want to get the technical results, you can find it here, which was published in 2022. So all the technical results like can be found here. So they look easy, but the proofs are not easy. So you can find, if you want, you can find it here. So I want to end with the same question again that leads us ponder an essential question: if a non-classical mathematical framework adheres to the fundamental principles of basic mathematics while deviating in abstraction from a classical norm, could we not afford it equal significance as classical mathematics? Thank you.
Thank you very much for this.
Okay, so as you have said that the mathematics what we have practiced is based on the classical logic. You have so
No, I did not say that. I said that the basic mathematics which we practiced in our school, that lies like happily with classical mathematics.
okay, and
My question is that if classical mathematics is changed, and if we found that that is not contradicting with the basic things, then what? That is my question.
so my question is, so there are non-classical logics, and you said that there are math based on non-classical. You have shown that there are results classical. My that do you have any results does not do you have any results like Pythagoras theorem or this kind of result mathematics and
Oh, not belonging to the classical mathematics. So you are saying that do I have something which is contradictory with the classical mathematics
not
in this
really a
framework?
contradiction, the domain of
So
classical mathematics.
whether I'm getting something new,
yeah
that is your question.
Yeah.
Well, so before going to that, like let me tell you that not only these things, in these models, I have found many interesting results. For example, Schroeder-Bernstein theorem is proved. It is proved that action of choice, generalized continuum hypothesis, all are independent like the classical one. So I have proved all these things in this paper on these models. But then for the new thing, in this paper, we do not have any new thing. But let me tell you that already I have found something very interesting new things which doesn't matches with the classical mathematics. But I did not have time till now to write that. So at some time I will publish it. So it is on Peano's axiom. So probably, if I am not wrong, then probably I have found two non-elementary equivalent models of Peano axiom. So in this kind of models. So if I get some time, then probably I'll write it at some point.
Thank you, Saurabh, for the fine presentation. I have one comment and one query. Comment is that in one of the earlier slides, you have posed two questions: whether mathematics is the basic one, or
Yes.
or whether that means with mathematics is the basic one, and we have developed logic later on, or the other way around. It may be answered in this way that when Russell and Whitehead wrote Principia Mathematica, they wanted to say that logic is at the basic place. Logic
Right,
has a basic place, but in the order of our knowledge, it comes later. Because we develop means it is already there. It is in the laws of thought, but we find it later on. That may be one. And the second one is that, as you said, that the classical set theory and the non-classical set theory, they may coincide in some up to some level.
Basic
So
mathematics.
do you
level,
mean
at
to
least.
say that non-classical set theory is simply an extension, or there is any there is no deviation?
Like
Whether it is a deviant
it could-
system or
it could be
extended.
incomparable actually. So definitely it is, no, I should not say definitely, but it might be an extension. So what I have in my mind is this. Somewhere here is the basic mathematics. Is a classical CFC, and I should not write non-classical because it contains too many, but some. Yes. Includes, okay, by the way, this PS algebra, we have taken the logic of this PS algebra, in maximum cases, it becomes a paraconsistent logic. Okay, so yes. So that could be the case. Or it might be an extension, it might be in few cases. Okay. And according to your first comment, like I had that thing in my mind when I was writing it. So yes, so thank you for the comment.
Yeah, thank you, Saurabh. I was just wondering the classification that you made between basic mathematics. That originates from the structural mathematics that is taught at school level, right? Addition, multiplication. I just wonder what your motivation was to kind of extract another category of basic mathematics. Was it just because of its use? I mean, just because it's used on a regular basis? And that's the reason you mean that it's essential mathematics in a way?
So actually, I don't know how it started, or at the beginning what was my, like, whether even I can understand like what actually I want to do even now, that I also don't know. Like it's modifying day by day. But what I can say that from the very beginning, when Professor Mir Kumar Chakraborty took our classes in our master degree level, like his words, like we're doing something inside, like where all these things started, and then this question started from those classes itself, that what happens if I get something non-classical, but our, like what I've said, that the basic needs are actually fulfilled, then what happens? Like I asked this question, like I can remember that one day, like in Amsterdam, when I was there as a visiting PhD student, I was traveling with Benedict, and then in the train, like we were discussing, and then you know that Benedict generally doesn't like non-classical set theory, right? And then we were discussing, and then he were saying that why he doesn't like it, and then it was my turn to say that why I like it, why I want to do it. So I asked the same question to him, that what if this happens, that the basic things we actually want to know, there are plenty of abstract results of mathematics, right? It might be that the non-classical things are not matching with that in the abstraction level, but what happens that the basic things, like where the mathematics started, like we think it like that, and then like of course these are needed to develop the calculus, right? That whenever you are talking about the differentiation or like the integration, what is integration? Like it's a continuous addition, right? So we are talking about the discrete addition here, but who knows that what will be the case in the continuous addition? So, but the things are starting with the basic mathematics applications here, right? So that was my question. But at that time, probably like Benedict had the question, but at that time he probably did not have any answer to that. He was thinking something, he has some answer. He did not say anything to me. This did not discourage me, but encouraged that, okay, you go ahead and try to see that whether you can find something. So I have a longer motto, right? I want to develop a mathematical world in this non-classical setup. So all kind of like topologies, algebras, geometry, I want to see that this is my bigger project, that what actually will happen.
Thank you. Thank you. Let's thank Saurabh again. I think we have come at a time where either we cancel tea or my talk. Obviously, the second one is preferable at least. He's waiting out. What time do we start? I can give a 10 minutes. 10 minutes. হ্যালো তো পড়ে যাবে না, পড়ে যাবে না তো ধূপ করে। হ্যালো 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 হ্যাঁ right here.
So welcome to the big session of the day, a somewhat violent session. We're going to involve rough stuff. Starting with rough truth.
Sure.
So we don't know how rough it's going to get, but let's start with Mahua.
Anything non-classical is rough, so that's fine. Okay, thanks, Jam. It's a pleasure to be here. I thank the Ramakrishna Mission, Narendrapur College, for giving us this venue, and Pulak in particular for making all these efforts to make this such a wonderful gathering. Okay, so since I kind of chaired incompetently, I'll cut my talk short. So let's see. So this again will not be anything new. It may be old hat for some of you. It's primarily intended as a precursor to the next talk, which will be given by Bidhan. And it'll kind of be a recap about some work that a few of us did several years ago, around 90s and 2008 and so on. So that's where the story kind of had ended. But then very recently it got resurrected, so to speak, by our student Bidhan, and it was used to get some exciting stuff, especially in the direction of paraconsistency. So it'll be meant as a recap, really. So I will not spend much time on the basics of rough sets. Anirban has already snatched some slides out of mine yesterday. So I'll just give a brief view of the basic notions there, come straight on to the modal connection, and then move to these alternate, so to speak, semantics and syntax that were proposed way back in the late 1980s and the beginning of 1990s, and tell you where it all went from there and where it stands now. Will be taken up by Bidhan. All right, so basic notions. So what Pavlak started with, so this was proposed, rough set theory was proposed in 1982 by Zdzisław Pawlak, a Polish computer scientist, and where he essentially talks of a kind of a granularity on the domain, and mathematically that was very simply represented as a non-empty set U along with a partition on it. So R is an equivalence relation there. But as many of us know that lot of water has flown, as they say, and we have several generalizations of rough sets where generalized approximation spaces are considered, where you've deviated from equivalence relations and considered several other kinds of binary relations. Anyway, that's a completely different story. For this talk, we will restrict ourselves to Pavlak's original, as it's referred to as Pavlakian rough set or Pavlakian approximation space, where we have a simple partition. Actually, that in itself has given rise to such rich exercises in mathematics that I mean, it's very fascinating in itself. So that's where one begins with just a simple set with a partition on it, and then you take any. So the pointer doesn't work anyway. So if you take any subset of the domain, you talk of its lower approximation. So I will keep this very typical view that all of us take of the domain U with the partition, and then you take any subset of it, let's say X, and so this is U comma R, and so you will have certain equivalence classes, that is blocks of the partition, which will lie completely within X, and some which will lie completely outside, and some which will lie in what could be termed as an ambiguous region or what's called the boundary region. So the first one, the one that is completely inside, that's called the positive region or the lower approximation, mathematically as the union of all classes which are contained in the set X. The union of all classes which properly intersect X, so that's this along with this ambiguous region that I mentioned, and that's called the boundary, the difference between the upper approximation and the lower approximation. And some terminology, so these basic building blocks or units of granules, if you like, are called the elementary sets, and the subsets which are very special in this scenario, namely the ones which are exactly the unions of equivalence classes. So for example, this one, right? So there is no ambiguous region as far as the partition is concerned, right? So those are called definable, or so definable in terms of the elementary sets, because they're just unions of those sets. And it's very clear that the lower approximation, the upper approximation, the boundary regions are all, unions of such blocks. And it's also an interesting, easy observation that if you consider a singleton elementary set, that certainly cannot be a constituent or cannot inhabit the boundary. That's a very simple mathematical exercise, set theory exercise. Okay. So some elementary properties that immediately come up are that there's a duality between the lower and the upper approximations in terms of the complementation operation. So you have the second one giving the duality. Then the lower approximation distributes over the intersection, the upper distributes over the union. You don't have the other it the other way around, and you have a kind of a monotonicity, and that the lower approximation is so that's kind of an involution on the lower and upper approximations. All right. Then we come up with these. Very naturally, one comes up with these two very basic. Operations on sets, which, because you are now looking at sets in the perspective of this partitioned domain. Let's be clear about that. So when you have a set X like this and another set, let's say like this, so whose lower approximations and the upper approximations are identical, then there is no way, given this information, that you can distinguish between the two. So you call them roughly equal, to be roughly equal, while rough inclusion is again a very natural generalization of inclusion, where they define in terms of the lower and upper approximations, right? So so that's another immediate observation, that the rough equality operation actually is just another partition on the power set. So you could refer to it as an indiscernibility at the concept level, as opposed to the original partition that gave us an indiscernibility at the object level. All right. So let's directly move on to the modal connections. I think those of you who are hearing this for the first time would have sensed it already, that we are really talking of the lower and upper approximations as reflecting the possibility and the necessity and possibility operators in modal logic, in particular of S5, because any Kripke model or Kripke frame of S5 is nothing but what we have called an approximation space. And further, if you just look at a valuation function, then what it does is, in terms of rough sets, on any S5 model, it takes, so I've been using the Hughes and Creswell notation of L and M as opposed to the box and the diamond. So any valuation function will then map or interpret L alpha to be nothing but the lower approximation of the interpretation of alpha, and similarly for M. So M corresponds to the upper approximation. So it's no surprise that with this definition of the truth that we have classically, that alpha is true in a Kripke model, provided alpha is true at every object of the domain. You can now look at these two formulae, modal formulae, which would translate as the interpretations of alpha and beta being roughly equal in whatever model you are taking, right? Because you just take the first part, so that's L alpha by implication L beta, which would, given the above translations or interpretations, just be translated as the lower approximation of the interpretation of alpha is equal to that of beta, and similarly for the upper approximation, right? So whenever in any Kripke model. So similarly for the rough inclusion. And interestingly, just as an aside, I'd like to, all right, so before I go to that aside, just a recap for what are the axioms that define, and axioms and rules that define the model system S5. So you have the first three as the classical propositional axioms, logic axioms, and the next three are the modal axioms that define S5. And apart from the modus ponens rule, you have this very special rule of necessitation that gives us any, that's the defining rule in any normal model system, right? Which one? Where? Yeah, what about it? Oh, I'm sorry. Yes, of course. Thank you. Yeah, so so we have this necessitation rule that defines any normal modal system, that if you can conclude alpha legitimately, then you can conclude L alpha as well. So as I was saying, that as an aside, since we have defined these new formulae representing rough equality and rough inclusion, can we have, so this was just an exercise we had done about what could be some theorems, S5 theorems regarding or involving those formulae. So if you just look at this, this is again just a set theoretic exercise translated into a logical one. So if you just look at it carefully, so I'm talking of alpha, let's take any set X as the interpretation of alpha. What is happening on the right hand side of that rough equality symbol? So you're taking the lower approximation of the set, adding to it the upper approximation, and intersect it with the complement of X, which is basically this portion. Because this entire thing was M of the upper approximation of the set, but then you intersect it with the complement of X, so that means you're not here, but you're just taking this part. So now if you just look at it, what is the new set that we have? You have taken the lower approximation, and you have picked up just these portions from the boundary. So if you look at the lower and upper approximations of this new set, that has to, the lower approximation remains the same as the original ones, while the upper approximation also remains the same, right? So it was just a tweaking of the set, the set theoretic picture and writing it down there, and of course you can prove this as well, okay? So similarly, I'll leave for those of you who've got any interest, as the second and third ones also can be derived. All right, so let's return to the main part of this recap, which is this fascinating notion of rough truth that was proposed by Pavlak in 1987. That was soon after his original paper in 1982. It was titled Rough Logic, where he stipulated that given our partial knowledge on which this entire theory is based, absolute truth or absolute falsity really are the limiting notions. In general, we just have rough truth and rough falsity. So how do you formalize those two? So if you look at our Kripke model scenario, you can, so it's basically, rough truth is supposed to be saying that you cannot rule out the truth, but you cannot also with certainty say it's true. So it's essentially what you're saying is it's possibly true. So if classically you would say true is, as I mentioned earlier, that if X lies within the interpretation of alpha. But here we are saying, okay, it may or may not, but it certainly lies within the possible region of interpretation of alpha. All right, so the upper approximation of V alpha. So that's what possible truth is, and so on every object, if you take that, that's when you get the notion of rough truth. So possible truth at every object of the domain. So in other words, if the upper approximation coincides with the whole set, you say that this is rough truth, as opposed to the interpretation itself coinciding with the whole set. So this was very naturally then extended by us soon after, that was during my PhD work, that you extend it to the notion of rough validity. That is, if you have rough truth in every Kripke model, then you say that it is roughly, the formula is roughly valid, right? So once you have this kind of an alternate semantics, so it was very natural to search for or formulate a system, a logical system, which would be, so to speak, sound and complete with respect to this semantics. So obviously S5 will not do. And also one was clear about the fact that we did not want to lose the S5 theorems. So those should continue to be there. So it was this rule, and since this upper approximation was playing a crucial role in the definition of the rough truth notion, so it was also natural to think of this kind of a rule, which is where the first so-called rough modus ponens rule comes up, which is saying that if you have concluded alpha somehow, and if you have a relation between alpha and beta in this manner, that think of it said theoretically that the upper approximation, that is when alpha is possibly true, so is beta, and from beta you have concluded something. So given this perspective, so you have alpha and you have some relation between alpha and beta, and then from beta you are concluding something. So it's classically, what would you have had? You would have not had this step. You would have had alpha implies beta, and then you would have concluded beta, right? So here one is adding this layer in between, saying that in this kind of a granular scenario, you may not be able to directly see alpha here, but maybe some reflection of it through this notion of utilizing this notion of upper approximation, and then you have from that beta you get a conclusion. So it appeared reasonable to conclude gamma directly from there. So this was posed as a rule, and one could see later that it is equivalent to syntactically equivalent to this very simpler version, and it was not really a surprise that one could, so I haven't formally defined it here, so the consequence relation is that you allow all the S5 theorems and you allow new consequences which will be obtained using this rule, this new rule, all right? So that's the Twiggle turnstile that you can see out there, and the right hand side is the notion of rough validity, and you could easily see that these matched. But then one could also show that strong completeness does not happen here. So you have examples there which will show that if you allow a non-empty set of premises to be there, then you do not have this to and fro. So one continued this exercise, and in 2006 one could see, so I have here formally written up the consequence relation. so apart from the previous rule, one added a needed to add a kind of an adjunction, but adjunction in terms of the possibility operator. So this gave us the strong completeness, and one could see that here was this relation, the single turnstile, the normal turnstile represents the S5 consequence, and one could see that again this was not really a big surprise, because one is really focusing on the possibility operator and kind of making it a basis for this entire exercise, that in terms of the S5 consequence, this is the relation between that new consequence relation and this one, all right? But so this already led to a kind of a, direction. First conclusion was that this is going to be paraconsistent. You can easily show this, and also this relation with this very well studied logic of Yashkovsky, which was proposed in a absolutely different context, no roughness at the time, that you have a discourse or a debate taking place, and you have participants who may be voicing opinions contrary to each other, but then you allow deductions there, even in such a scenario, or there may be different meanings in the assertions being made by the participants. So Yashkovsky, later on Da Costa, I mean, you'll find this formalism later also, that you have this world-based semantics being accepted, and the formalism is basically giving us the fact that this logic J and the logic for rough truth that one arrived at are really equivalent. And also, as I observed a little while ago, that the first logic that we had, which did not give us a strong completeness, is actually strictly embedded within the, so by that less equal to sign I mean, and before that, by the equivalent sign I mean that whatever is a theorem here, whatever is provable here, so if you have gamma turnstile alpha here, then you have the same on the other side, and vice versa. But for the second one, I mean that whatever is provable here is provable there, but you have examples of the other side not happening. And so, of course, since you have that less than, it's strictly less than, because as I observed earlier, you do not have strong completeness for LR. Same example will suffice to show this one. And then, of course, since L capital R or J, whichever way you like it, is paraconsistent, so is the other system, right? So the next part, how much time? 5. Or I'm done. 5 minutes, all right. Okay. So this was an extension of the what we said here about the first this rule that I showed here. So it actually would make more sense. So this happened because we had the rough truth, so-called capturing rough truth in mind specifically, but it would make much more sense if we talked of this notion of rough equality and posed a version of modus ponens in that scenario, because you may just say that, okay, I have concluded alpha, and now alpha is roughly equal to beta. So for all practical purposes, I'm not able to discern between alpha and beta. Then if you give me gamma, I mean, you can conclude gamma from beta, I should very much be able to conclude gamma. So this was the kind of thing which would probably make more sense in this scenario of rough equality. So this was the rough modus ponens that we originally called it, is exactly what I just said. So you've concluded alpha, you have this relation between alpha and beta, that is of rough equality, and beta gives us gamma, then I should be able to conclude gamma. And just syntactically, if you just throw out this, so this is the S5 consequence, all right? The Twiggle one is the new one. So if you, the second one is just devoid of that set of premises, all right? So that's a variation of the first one. Right, so this began, this led us to this new exercise where Martin Bunder joined us in investigating that, okay, you gave us that first rule which we called RMP1, which gave us a logic for a rough truth. You also have now posed this RMP, but then why stick to, rough equality there, can we just play around with so this became a purely syntactic exercise. Can we play around with the L and the M beside the implications and replace it there in that rough modus ponens rule. So if you write down, you have the implication operation and you just the various possibilities of L, M being there and not being there. So you have this, and then if you carry out this exercise of if one of them is a theorem, is the other one also a theorem? And so in other words, what we are exploring is, do some of them become equivalent? Well, in fact, they do, and you can actually show that this 2, 4, 6, and 7 will be thrown out of the picture, and you are left with these 5. So you see what's happened? So we have retained these, but here we are replacing the S5 consequence by those which remain of those 9 that we had, of those 9 possibilities, right? So you have these 5 so-called modus ponens rules, all right? And you're now in a position to, you just define these new systems LRI, so LR1 to 5, where the definition is the same, that you have the S5 forming the base, and you allow new consequences using those MP rules, the different MP rules. Another slight syntactic variation is that you allow now a non-empty premise before the S5 implication. So those were termed as the plus rules. So you have again 5 MP rules, MP plus rules. And so if you come back to, so of course then we were well into searching for a relation between all these various logics. So what did you have this, jungle of logic? So what do you do with all the LRI, LRI plus, and the original one? So what happens there? So so while we were doing that, we already know that the logics for rough truth are paraconsistent. So coming back to this issue of paraconsistency, one observed that this one with M alpha rho beta in the S5 consequence happens to be strictly less than our discursive logic, and since discursive logic is paraconsistent, you have this fact. So basically one got one more paraconsistent system. What about the others? So now we have we move to another interesting fact, and which is that I showed you the S5 axioms, and in particular the rule of necessitation, which is which stipulates that when alpha is legitimately derived, that is, it's a theorem, then only you can conclude L alpha also legitimately. But if you generalize that to putting, to allowing non-empty set of premises, then let's call that NG. Then you have several interesting facts. Of course, if you restrict to theoremhood, they're just the same. However, you get these new consequences, and DT fails, but you have DT in this form. So notice that the L operator is now playing a role out here. And in fact, we could observe that the RMP rule, this is the one with the rough equality, and the earlier one, are actually equivalent to this generalized form of S5. In fact, so this is where I would finish, is this entire thing was kind of thrashed out, and we have this relationship. So unfortunately, as far as paraconsistency is concerned, one ends up with just this portion being paraconsistent, but then the relation is very, very clear that these explosive logics sitting here, to which, so that's the trivial system, to which the remaining kind of become equivalent. So yeah, and then the LR1, which had that M alpha rho M beta S5 implication, actually is strictly stronger than J, because in fact you have modus ponens holding there, but modus ponens, our classical modus ponens holding there, but that doesn't hold in J. So this is really the scenario we ended up with. So we ended up with an as far as semantics were concerned, because again that was the other natural question that we had, that so these are then known, those we have worked out the semantics for. So this LR4 still remains, I mean, one simply didn't work on it. We do not know what semantics it has. And so, as I said, the story had ended out there, but then it was kind of revived very recently because we were interested, along with Shoma, for Bidhan's work, we were interested in what are the paraconsistent systems that we could get using the rough set. So we had that diagram with us, but then, as I said, you only have those, the left branch, which gives us, the others are all really collapsing into explosive systems. So, however, it turns out that with a little tweaking, I will not erase the suspense. You do get, a number of paraconsistent systems just following this approach. So that Bidhan will tell you about. So, thank you. Yeah, so these were the... Sure. Just load your talk. Have you mailed it? Is it already loaded? Huh? So you can just get out of this screen and just... That's mine. So where is yours? Out of bar call? No, no. Okay. Yes, Akhil. Yeah. Right. Yeah. Actually, that no. Well, I mean, from the motivation point of view, I'm not sure that, but I don't think it leads to anything new, because we had actually posed a parallel rule which had the L component, but then that became derivable. So if you throw out the M completely and have just this L portion, I'm not sure. But of course, from the point of view of the truth and rough truth, that will not, well, you will just say, okay, it's definitely true, kind of thing. Yeah, I don't know, really. Yeah, one will have to see. But I have a feeling that it may just not lead to anything new as such. So, but we'll check. Tell me. Thank you.
Right? Okay. So, good morning, everyone. So, title of my presentation is doing paraconsistent logic based on notion of rough sets. Yeah. So, it's the outline of my presentations. First, I will recall some basic preliminaries that I am using in these presentations. Then I showing a tree diagram where I will show that different approaches to construct paraconsistent logic, and then I quickly recall, which is ma'am shared some explosive logics with the notion of rough mode exponents. Then I will talk some new paraconsistent logic with the notion of rough mode exponents, and finally, and I will stop my presentation with some future directions. Okay. So a logic is considered as a ordered pair whose first component is a non-empty set, which is called FOR. For the time being, we will call the set of formula, and the second component is a relation between power set of formula and formula. I mean power set of FOR and FOR, and which may be called maybe written as syntactically or semantically. And if a subset gamma is of FOR is related to an element alpha, as it is written in this expression gamma translated alpha, which is read as alpha derivable from gamma, or alpha is gamma is alpha. Now, if this relation, consequence relation, is said to be explosive, if it satisfies the condition tells us that if for any subset gamma, and if we choose any two formulas alpha and beta, beta is derivable from the premise set gamma, alpha and not alpha. And this property of consequence relation is very well known, is known as the X contradiction Corley-Butt, or in short we can say it is a ECQ. And the logic associated with this consequence relation is said to be explosive, and otherwise we will call paraconsistent logic. Okay, so can I zoom it? No. Okay. Okay. So this diagram is basically presents various kind of approaches or techniques to construct a paraconsistent logic. Here I used two kind of nodes here, rectangular and circular. The rectangular nodes, except this root 1, represent the various kind of techniques to construct paraconsistent logics. And the circular nodes below the rectangular nodes represents corresponding paraconsistent logic, which are based on the respective techniques. And today we will focus on the rough set approaches here. And the logics below these approaches are obtained or based on the various kind of modus ponens rules, which are weakening by the rough modus ponens already ma'am presented. Okay. So yeah, so I not repeat this one again, but I try to mention it that this modus, this MPI rules are obtained by weakening rough modus ponens by changing this part. So here this is known as the S5 consequence, and here this S5 consequence of MPI rules are obtained from this one by relaxing premise part gamma, and this part alpha equivalent, roughly equivalent to beta is changed by various kind of implication between alpha and beta, which is written over here. Okay, and ma'am already mentioned that all of this logic based on this MPI rules are explosive logics, except LR4. Okay, so but then we thought that if we if we weakening this logic further by relaxing this part also, then what will happen? Then we will see that this logic based on the new generated MPI rule is paraconsistent. We will see. This is nothing but the way ma'am define the logic LRI. I want to skip it. Okay. So it was our MPI rule, and weakening this MPI rule, we propose the new one, and we show that showed that this rule is equivalent to this new form for I equal to 1 up to 5, and as well rough implications. But for I equal to rough equivalence, it's not equivalent, but it holds for one directions. So I mean this implies this one, but here we adopt this form of expression for I equal to implication for taking the same scenarios. Okay, and the way LRI defined, we defined LRI bar logic as same way based on this MPI bar rules and with additional two rules, this 1 and 2. S5 based on S5. The language are same as S5 rule. Okay. So now, okay, so we define the logics LRI bar. So now what will happen? So now we will show that this all these logics are paraconsistent. I mean explosive does not satisfy in this logic. So first we will show that LR1 bar, LR2 bar, LR3 bar are paraconsistent. So for that we need a I would like to state a theorem, and this theorem tells us that for I equal to 1 to 3, if alpha is a derivable from gamma in LRI logic, LRI bar logic, if and only if either delta I alpha is S5 theorem or this expression, I mean delta I beta imply delta I alpha is S5 theorem, where delta I is a modal operator for I, delta 1 is same as M, L2 is same as L, and L3 is 1. So written over here. So using this theorem, one can easily check that if we choose two distinct propositional variables P and Q, then Q does not follow, I mean Q does not derivable from the premise that P and not P. So it is obvious thing from using this theorem. So that means these three logics, all of these three logics are violate ECQ. I mean they are all paraconsistent logics. Okay. Okay, next we will show LR4 bar is paraconsistent. So for that we need, ma'am already stated this relation. So suppose two logics L1 and L2 with the same language, and L2 is just stronger than L1, which is written by this expression. If it satisfies the condition state that if a formula alpha is derivable from gamma in L1 logic, then alpha is derivable in gamma in L2 as well. So and this, okay, and one can show that MPI bar rule is derivable in LR3 bar system. That means if an element, I mean if a formula alpha is derivable from gamma in LR4 bar, then it can also derivable from gamma in LR3 bar. That means LR3 bar logic is more stronger than LR4 one. And as I already said that LR3 bar is paraconsistent, then this one also paraconsistent. Okay, so next, okay. So for these two logics, LRI rough implication bar and LRI rough equivalent bar. So for as like LR1 to 3 bar, we there is a theorem which help us to violate ECQ. So this theorem states the for one, if alpha is a derivable from gamma in LRI implication bar, if and only if either alpha is a S5 theorem or this expression, I mean M beta imply M alpha and L beta imply L alpha are S5 theorem. So similar theorems holds for LR implication here. And similarly, we can show that for two distinct propositional variable P and Q, Q is not derivable from P and not P. We can easily show from this theorem. And therefore, these two these logics are also paraconsistent. Okay. So next, we will show LR5 bar are paraconsistent logic. So for that, we need a translation between the language of S5 and language of CPL, I mean classical propositional logic. And these translations satisfy these conditions. And this is our Boolean cases. This and the last two condition tells us that this translation transfer a formula alpha, I mean modal formula, to a classical one by omitting all the modal operators in alpha, right? And this and the image of any alpha under this translation, I mean star of alpha, is known as PC transformation, which is mentioned in this paper. And in this paper, we can argue that if if a S5 formula is a S5 theorem, then its translation is also is a CPL theorem. I mean, if we omit this all modal operators in alpha, then it will get a CPL theorem. And based on that, we can prove another lemma. The lemma states that if alpha is S5 theorem, I mean if alpha is derivable from gamma in S5 LR5 bar, then the image of alpha under this translation is also derivable from the translation of gamma, where the translation of gamma means the collection of all translation elements of gamma in capital Gamma. And again we using this lemma, we can show that for any two distinct proportional variable as like a similar way, that Q is not derivable from P and not P, and then we show that this is a paragon system. So up to here we showed that all the logics we derived based on LR MPI bar rules are all paragon system logics. And there are some future directions that I have mentioned here. That so as I earlier said that LR3 bar is stronger than LR4 bar. Then what is the relation for other LRI bar logics? And this is one of our upcoming task, and as well what is the relation between the LRI. So next is related to our sound and completeness for our LRI bar logics. So to propose the suitable semantics for this our new systems to become their sound and complete. And the third one is based on in this paper. Actually, in this paper, the authors already proposed some new logics which are replace this modal logic S5 by another weakening modal logic. So as a similar way, so can we replace this S5 by another weakening modal logic, I mean S4, S3, like that. So then what will happen for this new systems? So this is our last future directions. Okay, so there is some references that I am using in this presentation. The first one is related to the LRI logics and their interrelationship. The next one is modal logic. I mean the third for this related to this future directions. And the last one is related to our translation, PC translation, that I used to prove LRI for bar logics. Okay. Yeah, this finished my talk. Thank you.
Thank you. It's very interesting. Do you have any idea about the strength of these differences? Are they relation like some of them being?
Yeah, those, there is not entire sketch, but we can draw some the relationship between these LRI bar logics. Like it's look like the LR4 is set on at the bottom line.
Okay.
LR4 bar. This one is, I think, 3 bar. So here the arrow means, so yeah, this one. So the strictly arrow, this type of arrow means strictly weaker. This is strictly weaker than this. The double arrow means they are equal, but we have to find some, I mean, LR4 bar less equal to LR3 bar, but we have to find some example to show this is strict one.
Okay.
And the dotted line is presented for independence, neither less equal to or greater equal to, like that. So this is the scenario we have till now show, but we have to draw the relationship for LRI logic also. So this is.
And where does the L presented, LR?
Yeah,
Does the
so
LR
this one, sorry,
Yeah.
this one is the LR actually.
Ah, okay.
Okay. I see.
Mm.
Thanks. That's extremely interesting.
Thank you.
Other questions? I had one. When you talked about systems weaker than S5,
Yes.
you were talking about S4. S4 is quite drastic.
Uh,
But what about KD45 or
So,
something which
yeah,
is
no, we can
almost,
use using this kind of logic. We can construct what we did not see till now.
Oh. I see.
Uh,
S4, but S4 is more drastic, like I said. But KD45 is almost there, right? So, and some of those things seem very close to KD45. So,
yeah, thank you.
okay.
I don't see them. The men, I would like to see maybe later the exact definition of this bar series. So, এখন দেখেও না মানে পরে I will see because does it make much difference? Just one. No, is it a very significant difference? That, yeah, okay. You get the para consistency of a special kind only. Okay, from semantic angle, actually, we should, because yeah, we should check I mean, what is the significance from the semantic angle? That will be really more important things. Okay, thank you.
Thank you.
Thank you very much. Thank you. Okay. So we come to the last talk before lunch. If you thought all this was rough and explosive, this is going to get really violent. This is generalized explosion principles. So Shankha is here to give us the ultimate word for explosion.
Yeah, so I promise there is no violence involved. Although I have been asked by my then 8-year-old whether I'm building a bomb. And I'm very scared while traveling on an airplane if there's some immigration officers who chance upon this kind of titles. I might have to face some repercussions, but for now there is no violence. Yes, absolutely. So let's see. So first of all, thank you for to the Ramakrishna Mission College for providing this space and this resources. Today I'm going to talk about, well, enough about the title already. So here's the idea. So I'm going to talk about paraconsistency. So we have been talking about paraconsistency in the morning. Hitoshi didn't really go into that, but there were things about paraconsistency there. We were listening to the last two talks, clearly had paraconsistency in it. Now in this talk, I would like to question the route to paraconsistency. So explosion is, so somehow we have to stop explosion. So we'll be thinking about what is explosion actually. Can we generalize explosion? Can we talk about explosion without a negation? So does it even make sense to talk about paraconsistency without negation in it? So these are the questions. This is a recent work which can also land us inside universal logic, wherein it's a general setup, no connectives, it's just a structure, abstract structure, and so on. So before going in there, let's talk about standard pair consistency. So we understand this ECQ principle that if you have any alpha, then alpha and negation alpha will explode, or equivalently we can write it with the consequence operation. Now, if we want to get rid of the negation, we first have to think about why even we bother to do this. So the reason is over here. There are alternative principles of explosion in literature. So here's an article that I was reading, and this had this list and some more of principles of explosion. Now, as you can clearly see, if you have certain laws inside your logic which will allow you to move from one to the other, then of course all of these are going to be. But what if you don't have these rules? So for example, if you have a logic without modus ponens, or let's say and introduction or elimination, then these could be different. You can even think about non-Tarskian logics, wherein you do not have certain structural rules. So can we even talk about paraconsistency in those systems? And how? And is negation really that important for paraconsistency? So we can do it in two ways. One is, if negation is really, really that important, then we will clearly end up somewhere. If we drop negation, we are somewhere where there is no paraconsistency. And if it is that important, then if you can turn the gun around and you can look at negation from the point of view of paraconsistency. So can you define negation using paraconsistency defined in a certain way? So that was the goal. Now, there is one slightly different explosion rule, which is the explosion from Folsom. So here we just want to make it very clear that what we mean by Folsom is a nullity operator or a constant in the language from which everything follows. We are going to call this constant the falsity constant, and that rule bot ECQ. That rule is also known as ex falso, by the way. So we are just using bot ECQ just to keep the continuation. Now, the falsity constant in itself is a bit problematic. So it is understood in multiple ways. With some understandings, the bot ECQ is essentially, the bot paraconsistency is essentially the same as paraconsistency. Under some other understandings, that might not be the case. So you might have different notions of paraconsistency depending on how you understand the Folsom. Let's go into the first of these generalized principles of explosion. So we did the most obvious thing that could be done. Instead of mentioning a negation, we say that for each alpha, there exists some beta such that alpha beta explodes. And this is called GECQ. If you break that, then you have negation-free paraconsistency. I might keep writing these principles. There are more explosion principles to come. So GECQ is the first of these generalized ones. So it says for all alpha, there exists beta such that alpha beta explodes. Oh, by the way, I should also mention that I should warn rather, that many of the examples that we will take of a logic is really, they are really logical structures in the sense that L is not really a set of formulas. Whether you want to call the turnstile consequence relation or not, that depends on how you want to look at it. Some examples are really that general. So anyway, so this is NF paraconsistency where GECQ fails. Now the question obviously that comes is, are there examples? Because without examples, this is going to be just an empty definition. But before going into examples, let's look at how we can compare the standard notions of paraconsistency with NF paraconsistency. So if you see, if it's easy to see that if you have a negation in the language that and there is an ECQ that fails in the logic, that is if it's paraconsistent. If it's NF paraconsistent, then it's paraconsistent in the standard sense, which means failing of ECQ. Then if you have a monotonic logic, so we could not get rid of this monotonicity condition here. If you have a monotonic logic and if this is NF paraconsistent, then there does not exist any single element from which you can have explosion. So if S is NF paraconsistent, S is monotonic, then there does not exist any phi from which it explodes. So this clearly implies that if S is NF paraconsistent, then it must be bot paraconsistent. Monotonicity given. Minimal logic is an example which is monotonic, not bot paraconsistent. It is not NF paraconsistent. So far it goes as we had expected, no examples. Right? So now this is the first example, one of those weird examples. We constructed a purely reflexive logic. So this L is any set, and the turnstile is defined in this way, that gamma will entail alpha if and only if I can call this entail. Gamma entails alpha if and only if alpha is given. This is NF paraconsistent as long as you have 3 distinct elements. Not very hard to prove. It's a Tarskian logic, in fact. Monotonicity and transitivity will also appear. Here's another example. You have a poset. 3 elements. 2 is an incomparable element to both 0 and 1. And we define turnstile in this way. Gamma entails alpha if and only if alpha is bigger or equal to every element of gamma. It's a finite set, fine, no problem, it's easy to see. It can be generalized. You see that 1 doesn't explode with either 0 or 2, and hence this becomes NF paraconsistent. We can in fact generalize. You take any poset with 2 incomparable elements, alpha, beta, and you define turnstile in that way. This is NF paraconsistent. Okay. Now you can still generalize this. You can add another layer that the poset is at it's a set of values. You have a language, or I should not call it a language. You have an L, and then there are sets of valuations. You define a semantic consequence as you would, and then you just have to hit the incomparable elements in the poset, and then you will see that you have NF paraconsistent. So I want to skip this because I want to go into some other things. And here's an example from Carneal's article on LFIs, where he was also trying to generalize paraconsistency. Again, let's not focus on this. And here's an example with Q consequence. Again, I want to skip that because I want to get into this logics of variable inclusion, which will give us a better example. So first of all, left variable inclusion. So there are 2 kinds of variable inclusion that are defined now, left and right. Within the left, there are 2 kinds. There is the left and the pure left. So what is the idea? So for these logics, we go back to our usual understanding. So L is the set of formulas defined inductively. The formulas are defined inductively on a set of variables, which will almost always be assumed to be denumerable. And there are finitely many connectives, which we are going to call the signature or the type. Now, suppose you are given a logic, L turnstile, which is like this. And then the left variable inclusion companion of S is another logic, which is defined in this way. So we just have to define the new turnstile L. So we will say that gamma entails alpha in this new logic, that is the left variable inclusion companion, if and only if there is a subset of this gamma such that the variables in that subset are included in the variables in alpha, and alpha follows from this subset in the original logic. Okay? So we just want to ensure that all the variables in this delta are contained inside alpha. That's the only thing. Now, the difference between left variable and pure left is that, see, in left variable, what will happen is all the theorems will get transferred. So if you have something that is a theorem in the original logic, it will also be there in the left variable inclusion. The pure left stops that. So you require that this delta be non-empty in the pure left. That is the only difference. Yes.
That's the intentional.
Yes, yes. So in the left variable, all the theorems will get, yeah. Pure left is just there to stop the theorems. That's the difference. So there are various examples. In fact, now there is a book by Pauli and his colleagues, Prabaldi and Bonzio, on the variable inclusion companion logics. And PWK, or the paraconsistent weak linear logic, is an example of a logic which is, I mean, that's where it all started. It's the left variable inclusion companion of classical propositional logic. And Sir and I, we worked on the left variable inclusion companion of intuitionistic propositional logic. So we have IPWK. So both of these are examples of left variable inclusion companion logic. Here's our first result, that if you have a falsity constant in the original logic, then your left variable and pure left variable companions cannot be NF paraconsistent. Now, if you remember the theorem that I showed earlier, there was a requirement of monotonicity. That requirement is no longer there, because no matter what your logic is, once you do the left variable or pure left variable, these inclusion companions become monotonic. So therefore, monotonicity is already, there. These are the left variable and pure left variable inclusion companions are always paraconsistent. And we see that PWK and IPWK are examples of logics which are paraconsistent but not NF paraconsistent, because they have this bot and they're monotonic. So still no examples. So we were trying to see if we can somehow stop the falsity constant. If there is no falsity constant, can we ensure that the companions are NF paraconsistent? So here's the first result. You may just ignore the lemma, it's a technical thing. So if you have no constants, so variables of every element, variable content of every formula in L is non-empty, so which means there are no constants, then you have that the pure left variable companion is NF paraconsistent. In addition to that, if you have this very minimal requirement that there is at least a variable which doesn't follow from the empty set, then the left variable inclusion companion is also NF paraconsistent. But this is an overkill, right? So you want to say that there is no falsity constant. You don't want to say that there are no constants. So we were looking for what conditions do we need to ensure that we can just get the actual converse, that there is no falsity constant. So it turns out structurality is one of the answers. So structurality means that it's just substitution invariance. If you have the property of substitution invariance, then you can say that if there is no falsity constant, the pure left variable companion of any logic is going to be NF paraconsistent. Given that very small requirement that not everything is a theorem, the left variable inclusion companion is also NF paraconsistent. Structurality was one answer. Transitivity also gives us a full converse. If your original logic is transitive, then if there is no falsity constant, SPL is NF paraconsistent. For the SL, the left variable inclusion companion, we need both monotonicity and transitivity. But if you study the proof, we found out that we don't need the full power of monotonicity or transitivity. These weaker forms of monotonicity and transitivity would do. So this is as close to the complete reversal that we, or converse that we went. All right, so that's the story about left variable. Now let's come to the right variable. So right variable is supposed to be the dual of left variable. So here the idea is the variable inclusion is reversed. Okay, so gamma entails alpha in this right variable inclusion companion if either variables in alpha are contained in variables of gamma and gamma entails alpha, or gamma contains an S antitheorem. So what is an antitheorem? An antitheorem is a set which explodes for every substitution instance. Okay, so not only that gamma explodes or sigma explodes here. Sigma is an S antitheorem if it not only sigma explodes, but for every substitution, sigma of capital sigma also explodes. The pure right, so here what happens is in the right variable inclusion, so if you remember in the left variable inclusion, all the theorems could travel through to the new logic. Here, all the anti-theorems would travel. Just to stop the anti-theorems, we have the pure right. So in the pure right, this condition has been removed. So you have just the second condition. Okay, so NF paraconsistency, we can see it's it's not at all hard to prove that the pure right inclusion companions are going to be NF paraconsistent. Very easy proof. They're paraconsistent and also NF paraconsistent. But the right variable inclusion companions are not in general paraconsistent. So the example is the Boschvar logic B3, which is the right variable inclusion companion of classical propositional logic. It is not paraconsistent. So it cannot be NF paraconsistent. So again, the question is, can we do something to get NF paraconsistent? Here, so we have this property, monotonicity for trivial sets. So which means basically that if any set explodes, any superset of that will also explode. So if you have this property, and then we see that if S is NF paraconsistent, then the right variable inclusion companion of it is also NF paraconsistent. This is as close as we can get. So this is the story with NF to the variable inclusion companion logics. I'm afraid you cannot get any closer. At least, I mean, we don't know whether you can. All right, so that's where the examples of NF paraconsistency stop. Now I want to talk a little bit about the other question we had. So can we look at negation from the point of view of paraconsistency? So this is that. So a quasi-negation. So we defined a quasi-negation like this. So first of all, a little bit of motivation. So if you have alpha, once you put beta with alpha, if it explodes, then beta is kind of a negation of alpha. So you can think of beta like that. However, this beta might not be unique because alpha may be exploding with many such betas. So we might want to call every such beta a kind of a negation of this alpha. The problem will be that this negation will no longer be an operator. So this is exactly what we get over here. The quasi-negation of alpha is any beta with which it explodes. And now we will have a set Qn alpha of all these quasi-negations. We wanted to, for just psychological benefits, we wanted to write this negation alpha there. But just to make it clear, it's not a connective in the language. It's not a symbol of the language. It's just a notation. Every member of Qn alpha is a tilde alpha. Okay. Properties of quasi-negation. So we were able to prove this kind of double negation, quasi-contraposition, and this property for Tarskian logics. So which is very much like the negation operator. See, alpha is, so we can't say alpha is equivalent to not alpha. We have to say that alpha is a not quasi-negation of a quasi-negation of alpha. And then contraposition, similarly, you have to read it like that is a instead of equivalent or something like that. So the Tarskian, if you have a Tarskian logic, then if alpha entails beta, then a quasi-negation of a beta is a quasi-negation of alpha. Quasi-negation and paraconsistencies, you can, again, try to turn back to paraconsistency from quasi-negation. So you can see that if S is paraconsistent if and only if the regular negation of alpha is not in Qn alpha for some alpha. NF paraconsistency, similarly, there must exist an alpha for which there is no quasi-negation. It doesn't explode with any beta. And if you have monotonicity, then you can link it with Bott paraconsistency. Okay, so quasi-negation can also be used, can also be studied in known logics. So we could study quasi-negation, properties of quasi-negation in classical or intuitionistic logics as well, but I'm not going to go into that. I will look into, because I think I'm almost out of time, so 6 minutes, okay. So I want to mention the further generalizations of GECQ. GECQ is, by the way, written over here. Let's look into some more principles of explosion. But first of all, what is a principle of explosion? If we ask this question, a principle of explosion might be described as something, some rule, which lets us go from a proper subset of L to L. Okay? So if we see it like that, then here is our first generalization. So for each alpha, there exists a set gamma, which is a proper subset of L, such that alpha is in gamma and gamma explodes. So you can see immediately that this is a generalization of GECQ. Okay, S is set-based because we are using a set here. Okay, so I'm going to skip all this because later on I can summarize this in a good way. So there are examples. There are nice examples of logics where SECQ is satisfied, but ECQ is not. So for example, this logic P1 is set-is logic. It's an LFI where SECQ holds, but ECQ fails. Its set-is logic is part of a hierarchy of logics, and also it's a member of the class of gently paraconsistent logics. What is a gently paraconsistent logic? So these logics satisfy this principle of gentle explosion, that alpha negation alpha does not explode, but alpha negation alpha negation negation alpha will explode. So there also we can see that SECQ holds, but ECQ fails. All of these are examples where GECQ holds, by the way. So we have a separation there. Now we have another variant of SECQ where we say that instead of saying that there exists a gamma which contains alpha and explodes, we have that there exists a gamma to which if you add alpha, then it explodes. But these two are actually equivalent. SECQ and SECQ prime are turned out to be equivalent. Then we went further. We said that for all gamma, now we turn this around. Okay, so we start with a set instead of alpha. We say that for all gamma, proper subset of L, there exists an alpha, which if you add to this gamma, then it will explode. So that's SPECQ. SP stands for set point. Then we started comparing what is happening, the connections. The examples, the counter examples that we constructed looked somewhat like this, which many people will say these are not logics, but these are examples. I mean, whether you like it or not, they are there. Then we went for completely point-free explosion. So these 3 point-free explosion principles were written down. So the first one says that for all gamma, there exists a delta which explodes. Okay, there exists a delta which contains this gamma that explodes. The second one says that if you union it with gamma, gamma union delta explodes. The third one says that for every non-empty subset delta prime of this delta, if you add this delta prime to gamma, then it explodes. Okay, so these 3 are variants. Okay, by the way, so the first 2, whether you have a delta superset of gamma or whether you union it with gamma, doesn't make any difference. These 2 are equivalent. The third one is different. So we have all these theorems. We have proved the dependence, independence. Wherever we needed independence, we constructed an example like this. So the insights into universal logic really helped. And finally, we arrived in this, so ECQ, still we have to find out the connections with ECQ. The problem with ECQ is you have to rely on the language. You have to have a negation in order to talk about ECQ. But anyway, if you have negation, then you can talk about these interconnections with ECQ. And finally, we ended up with this diagram. So all these principles of explosion, so here is ECQ, here's GCQ, which is written over here. SECQ is the one that I talked at the very beginning, where we started talking about these principles of explosion. And the point-free explosions are over here. This is the set point for all gamma that exists in alpha, which if you add to gamma, it explodes and so on. So we have this interconnection. Any arrow that you cannot see is not there. We have completely checked this diagram. So there are counter examples in our paper which will say that there is no arrow. Okay, so this is it. I think I will have to skip the logics of formal inconsistency. This is a rich class of, this is a rich class of logics which provided us with a lot of motivation to study these principles. But anyway, I'll skip that because I want to talk about partial explosion, and I'll stop there. 2 minutes. Yeah, 2 minutes are enough for this. So partial explosion. So what if, now the question is, what if we said in ECQ that for every alpha, alpha negation alpha explodes. With GECQ, we said that for every alpha, there exists a beta with which it explodes. What if this doesn't happen for every alpha, but for some alpha? Okay, so that's why the word partial. What will, this partial explosion is also important because it might lead us to, we might be able to partition the entire L into two disjoint sets wherein each set is consistent, so that we can have local consistency. But if we mix from the two sets, there will be explosion. Okay? So there are two principles of partial explosion that we have studied so far, formulated and studied. So you can say there exists gamma delta subset of L such that this gamma is not empty, and for every alpha in gamma there exists a beta in delta so that alpha beta will explode. And then the second one says that it's just that for every alpha beta there is an explosion. Instead of there exists, for every alpha there exists a beta, we are saying that for every alpha beta there is. Well, surprise, these two are actually equivalent. These two are equivalent. If you have the first one holding, then the second one holds, and so on and so on. So we started comparing partial explosion with total explosion. So here are the results, that if you have GECQ, ECQ, or the set point ECQ, then you have partial ECQ. It's not very hard to prove. But partial ECQ does not imply GECQ. And here's an example to instantiate that. And then this is all technical, so I won't go into this. So we defined two kinds of pairs of sets, weakly complementary and complementary. And based on that, we proved this. We had this huge partial order. So we took the set of all weakly complementary pairs of sets, and we constructed a partial order. And then we finally came to this theorem, which was the end of our paper. And here you see that it basically says, let me go into the remark bit. We have achieved this goal of partitioning L into two parts, gamma delta, in such a way that we have such a maximal pair, pi and lambda. Their union is L, okay? And if GECQ holds, then we have this maximal element. So in a way, this pi lambda, what it does, it partitions L into two parts, and then we can say that L is locally consistent, or the logic is locally consistent. By the way, these two, pi and lambda, they are also disjoint, so it offers a very nice partition. And this local consistency is witnessed by this pi. So I end my talk here. Thank you.
Since he's the program chair, he'll be allowed a couple of questions before we won't get lunch otherwise. So
Yeah, so let's go.
He's
for
the
lunch.
chair,
It's more
so-
important than explosion.
no, any yeah, sure.
Okay, so I'm asking that the last you said about the local consistency, right? But we know that there are notions of formal inconsistencies, like where we say that some element is acting as inconsistent and the others are not. Here also you are saying that some portion is like that and the others are consistent. So are these two things similar or why they are different?
In logics of formal inconsistency, you have to do something with the language.
Right.
Either you introduce the
Yes.
small circle, but even if you don't introduce the small circle, you have to deal with the big circle.
Right.
So big circle of alpha is a set which is basically giving you the classicality conditions of alpha. If you have that along with alpha and negation alpha, then there is explosion.
Right.
Otherwise, there is none. Here, there is no such assumption. Nothing is being assumed. So there are connections. I mean, this is partial explosion is kind of a generalization of GECQ. This principle that for all alpha, instead of for all alpha, for all alpha in some subset of L. That's what we are saying essentially. The logics of formal inconsistency offer a good class of examples for some of these explosion principles that we have, total explosion principles. So yes, I think there are connections, but it's still to be investigated.
Okay. So that means that you are saying that you have some properties, or it might be explored, or might be found some properties which will not match with the logic of formal inconsistency. Like we cannot explain it through that study.
No, actually, we thought that logics of formal inconsistency will offer examples from a different point of view also. Like we will see whether some of these general principles fail. But it turned out a bit disappointing because most of the general principles actually will hold in logics of formal inconsistency. But it's still to be seen because there is this property of finite trivializability that I skipped. Finite trivializable is when there is a finite subset of the L that explodes. If it is not there, then certain things happen. But most of the literature on logics of formal inconsistency have this property of finite trivializability because when you are doing the small circle alpha, that means it is finitely trivial. But we need to look at an infinite set of classicality conditions for LFI. Sure.
Okay, this was part early on. You assumption about some at least one right? That's not really much of an assumption or some such. Isn't that kind of already some kind of a non-explosion being embedded? That is it, at least for empty set. So why should that?
Yeah. So
small assumption. I'm just.
The condition was that there is at least one variable. So in at least most of the theorems, it was at least one variable which is not a theorem. Okay, and in one theorem, it was at least one formula which is not a theorem. I mean, we can replace it with a variable as well. So the ask is that not all variables are theorems. So there is some non-explosion there assumed for the empty set. But think about, do you really want to look into logics where everything is a theorem? Again, it's a bad argument, but okay.
This is a great talk, huh? I really liked it. So one question is, would you be able to characterize logics that are consistent, but not NF par consistent, kind of general way? Because PWK is one example, right? You said.
Yes.
And I have the gut feeling that that sort of makes sense from a less technical perspective. I'd be very interested if it's going to be possible. So you're doing it in a universal logic-like environment. Therefore, it doesn't really depend on the language. So I would like to really see if it's possible or not to characterize this class where it's par consistent but not NF par consistent, or more in general, like these kind of combinations.
That's an excellent question, but we keep stumbling on new, old examples of these new notion of paraconsistency.
Yeah.
So, for example, towards the end of the paper, we found out that LP is not finitely trivializable.
Right.
And if it's not finitely trivializable, neither ECQ nor GECQ can hold in it.
Right.
And in fact, SPECQ is also going to fail.
Yeah, sure.
So
that's right.
Even if you add, let's say, a material implication to LP to get RM3 with the implication, that's another example. It's still not finitely trivializable.
Yeah, that's right.
So I don't know, how to characterize, because we are finding more and more examples almost every day.
Yeah. You have to live forever then.
Yeah.
And finally,
or find out the conditions before.
And finally, the general comment or suggestion is, are you thinking of doing the paracomplete case?
Yes.
I think that would be also super interesting. Then you can talk about FTE kind of thing in this extremely
exactly
universal thing, right? So
yeah. Paracomplete is a question that is hovering for a long time.
It has to be multiple conclusion probably, right?
Mm-hmm. Yeah.
So that'd be super interesting. Looking forward to more.
Thank you.
That seems like a good note for lunch on. Thank you very much. Yeah.
ওই যে CLC 2 দেখি না এটা হ্যাঁ হ্যাঁ হুম
So, good afternoon. Let us now start the session. We have two talks in this session. First talk, Masiu Rahman
not
Sharda.
doctor.
Okay, it's not doctor yet. Okay, submitted, right?
Yes.
Oh. So we have 30 minutes for your talk. Maybe I will remind you after 25 minutes. Okay.
Okay, thank you. And good afternoon to all of you. The title of my talk is A Comparative Study Between Boolean and Quasi-Boolean Based Upset Theory. This is a joint work with Professor Chakraborty, and slide is not working. Okay. Thank you. Okay, in this talk, I will first describe the basic idea of Boolean algebra and quasi-Boolean algebra. After that, I will discuss Upset theory and Boolean-based Upset algebra. And in section 3, quasi-Boolean-based Upset theory and algebra will be discussed. And this work is totally done by us, that is Professor Chakraborty and myself. And section 4, I will discuss the logic of quasi-Boolean based upset algebras. So what is Boolean algebra? Here Boolean algebra is the bounded distributive lattice with complementation, and this is a quasi-Boolean algebra. Instead of complementation, there is one unary operation called quasi-negation. So basic difference between these two structures, both are bounded distributive lattice, but here in Boolean algebra, this is complementation, and quasi-Boolean algebra, this is quasi-negation. Complementation is defined by these two properties. First one is law of contradiction, and second one is law of excluded middle. But quasi-complementation, quasi-negation, which is defined by two properties again. First one is double quasi-negation of any element is that element, and second is De Morgan's. And it is interesting that this complementation satisfies the properties of quasi-complementation, whereas quasi-negation and quasi-negation does not satisfy the properties of complementation. And therefore, we can say that every Boolean algebra is quasi-Boolean algebra, but quasi-Boolean algebra may not be a Boolean algebra. In other words, we can say that Boolean algebra is more stronger structure than quasi-Boolean algebra. And these are two set models of Boolean algebra, abstract Boolean algebra and abstract quasi-Boolean algebra. The first one, it is power set Boolean algebra, and second one, it is power set quasi-Boolean algebra. See here that only difference is that again there is set theory complementation in power set Boolean algebra, whereas in power set quasi-Boolean algebra there is quasi-complementation. So what is quasi-complementation? Quasi-complementation is defined in this way. It is just like GA complementation, where G is an involution defined by GGX equal to X. And if we take G's identity, then quasi-complementation and complementation coincide.
And basic property of this this involution is that it should be bijective, and it rotates two elements. That means if gx equal to y, then gy should be x. And this is a Stone representation theorem of Boolean algebra. It was developed by Stone in 1936. It says that every Boolean algebra is isomorphic to field of sets. So what is field of sets? Field of sets means it is subalgebra of power set Boolean algebra. In other words, we can say that every Boolean algebra is isomorphic to a subalgebra of power set Boolean algebra. And this is the representation theorem for quasi-Boolean algebra. It was developed by Birula and Rashowa in 1957. It says that every quasi-Boolean algebra is isomorphic to a quasi-field of sets. So quasi-field of set, it is again the subalgebra of the power set quasi-Boolean algebra. And similarly, we can say that every quasi-Boolean algebra is isomorphic to a subalgebra of power set quasi-Boolean algebra. And now we come into the area of rough set theory. It was proposed by Pavlov in 1982. It starts with an approximation space UR, where U is non-empty set of objects and R is equivalence relation. And therefore, the whole set is partitioned by distinct equivalence classes. And if we consider any set, then lower approximation is defined in this way. It contains all those elements whose class are included in A. That is, all these elements class are included in A, and therefore this green portion is the lower approximation of A. And upper approximation contains all those elements whose class intersect A, and therefore this green and yellow portion, all these elements here, class of all these elements intersect A, and therefore yellow and green portion is the upper approximation of A. Interesting fact, these two operators, that is lower and upper approximation, these two approximations are dual with respect to complementation. And since these are dual operator with respect to complementation, so one can define any one operator, that is, if we consider say lower operator, that case upper operator can be defined by this duality property. And then if we consider this Boolean based rough set algebra, this is Boolean based rough set algebra means we take the power set Boolean algebra with this lower approximation operator. And it has been proved that this system is topological Boolean algebra plus modal axiom, algebraic counterpart modal axiom is 5. So what is topological Boolean algebra? It is topological Boolean algebra. It is Boolean algebra with interior operator I satisfying these four properties. And S5, counterpart of S5 is this Cia equal to Ia. C and I, these are dual with respect to complementation. It is not set theory abstract complementation. Yes, and main tasks that we have done, like this Boolean based rough set algebra, can we construct a quasi-Boolean based rough set algebra? And for that case, we have to construct a pair of lower upper approximation, so that this lower upper approximation can be dual with respect to quasi-complementation, not with respect to complementation. We have done some work in this direction, and for this we come back to involution and quasi-complementation, because these are the vital things to develop such lower upper approximations. So this is result on involution and quasi-complementation. If we have a involution G, and for that involution we have these 8 results. So first says that G is a bijective mapping. Second, it says that double G image of any set is the same set. And third, fourth, it says that G distribute over union and intersection. And fifth, it says that complementation of any set can be defined in this way. It is a G image of complementation of the set. And six, it says that double quasi complementation of A is A. 7 and 8, it implies that this complementation is satisfy De Morgan's. And this is important notion on quasi complementation and complementation. It says that if I already told that if G is identity, that case the notion of complementation and quasi complementation coincide. But if G is non-identity involution, that case we can find a subset of U whose complementation and quasi complementation are different. And we can prove it easily if we consider a set U and G, and since G is non-identity involution, so there exists an element X whose image is not X. Let us assume that image is Y, and we consider the singleton set X. And we know that X complement, X is not there, X complement, but X is there in the quasi complementation of X, because quasi complementation of X, it is the Y complement. And therefore, these two, quasi complementation of X and complementation of X, these are different. In other words, we can say that two notions, that is quasi complementation and complementation, coincide if and only if G is identity. Okay, now we construct a relation from an approximation space and involution G. Consider an approximation space UR. U is a non-empty set of object and R is equivalent relation on U. And from this relation, we construct a new relation RG in this way. Two elements are related in RG if and only if their G images are related in R. And we have shown that this relation is again equivalence, and therefore we have two approximation space. One is original UR, and from this original UR approximation space UR, we construct another approximation space URG, and we call it G approximation space. And in this G approximation space, that is URG, we define lower and upper approximations, which are denoted here GR lower and GR upper approximation. GR lower is exactly Paulokian one in the approximation space URG. And it is to be noted that we make them as dual with respect to quasi complementation. That is why we define upper approximation in this way. It is collection of those elements whose G image class intersect the G image of the set A. And after simplification, we have shown that this is exactly lower approximation of the set A in the approximation space UR, that is in original approximation space. So here our lower and upper always belong, one in URG space and another is UR space. That is, one is Paulokian space and another one is our new space, which is called G approximation space. Yes, these are dual with respect to quasi complementation. So we can make this quasi Boolean based rough set algebra. That means it is quasi Boolean power set algebra, quasi Boolean algebra with our lower approximation, because our upper approximation can be defined by this quasi complementation. Now question, what would be the nature of this algebra? Yes, so we see this property. This is the Paulokian lower upper approximations, and this is our lower upper approximations. And this property, normality, conormality, monotone, multiplication and addition, all these holds in both cases. now we consider modal axiom, and you see here again this is Paulokian lower upper approximations, and this is our lower upper approximations, and this is modal axiom K. If we consider Paulokian, that case it is complementation, but when we consider our case, then it is quasi complementation, and we have shown that in our case K does not hold, but D, T, S4 hold, and B and S5 do not hold. So what is the nature of this algebra? So you see here, if we consider I interior operator as lower approximation, then it is I1 equal to 1. This is I distributes over mid, and this is T, and this is S4, that is IA less equal to A, and T is there, and therefore IA equal to IIA, and therefore this becomes TQBA, topological quasi-Boolean algebra, which was developed by Banerjee and Chakraborty in 1993. So okay, so here we see that B and S5, these do not hold in our system. So then we try to find out conditions so that B and S5 hold in our system. So that case we have this result. B and S5 hold if and only if Rg equal to R. So there is a question, when Rg equal to R, that case lower approximation, lower upper approximation, Paulokian lower upper approximation, and our lower upper approximation are the same. But one gain is that these lower upper approximation are dual with respect to complementation as well as quasi-complementation, though these two notions do not coincide. This is the remark. So this is an example. Here R and Rg are same, and therefore B S4 hold, but still complementation and quasi-complementation do not coincide because G is here non-identity involution. Here 1, 4, these are pair elements because 1 goes to 4 and 4 goes to 1. 2, 6, these are pair element, 2 goes to 6 and 6 goes to 2. 3 pairs with 3, that is 3 goes to 3, and 5 pairs with itself, that is 5 goes to 5. Here G is non-identity, and partition equivalence relation is partition the set into the subset 1, 4, 2, 6, 3 and 5, and therefore R equal to Rg. And since this is non-identity involution, by earlier result, it says that notion of complementation and quasi-complementation do not coincide. But still I have taken one subset A 1 to 4. Complementation, quasi-complementation of this set is 2, 3, 5, and complementation is 3, 5, 6. So these are the different. Okay, so I have already mentioned that if we consider power set Boolean algebra with Paulokian lower approximation operator, then it is topological Boolean algebra plus S5. Okay, plus S5. But when R equal to Rg, that case Paulokian lower upper approximation and our lower upper approximation identical, and so we consider that lower approximation. So if we consider power set quasi-Boolean algebra and that lower approximation, then it is topological quasi-Boolean algebra plus S5. That is, it is TQBA5. And we also test the quasi-Boolean based modal axiom. You see here, quasi-Boolean based modal axiom, and therefore it is not complementation, it is quasi-complementation, and it holds if R equal to Rg. But whether this condition is necessary, it is unsolved. And this is one example. Here we have shown that if R not equal to Rg, that case Paulokian lower approximation and our lower approximation, there is no subset inclusion relation. So we consider the same set U that is containing 6 elements and G as earlier. If we consider R is this, that case if we consider A equal to 2, 4, then Paulokian lower approximation is 4, our lower approximation is 2, and therefore they have no common intersection. But if we consider Paulokian, if we consider the set 1 to 5, that case Paulokian lower approximation is 1, 5, our lower approximation is 1, 2, and therefore they have a non-void intersection. And if we consider the set 1, 3, 5, that case Paulokian lower approximation is 1, 5, and our lower approximation is 1, and therefore our lower approximation is included or is a proper subset of Paulokian lower approximation. And here Paulokian lower approximation is a proper subset of our lower approximation. Then we generalize the idea on arbitrary relation. Just take an generalized approximation space U rho and any involution G on U, and then we define, as like earlier, we define rho G in the same way that two elements are related in rho G if and only if their G images are related in rho. And then we define the successor neighborhood as in the usual way, and we define the lower approximation, which is again it contains all those elements whose successor neighborhood is included in A, and upper approximation is defined in this way: those elements whose G image successor intersect G image of A. And we have shown that this is again Paulokian, not Paulokian, standard 1 upper approximations. And we have shown these are the dual with respect to complementation. And again these properties, here is a standard lower upper approximation, and here our lower upper approximation, and all these properties hold. In case of modal axiom, this is standard lower upper approximation, this is our lower upper approximation, and modal axiom K holds for any relation, but in case our case when rho G equal to rho. So again question, rho G equal to rho, that means standard lower upper approximation and our lower upper approximation are the same. Okay. Okay. So this is with help of nature of the relation, we have developed these algebras, and we have shown that these become models of these algebra with respect to the nature of the relation rho G. And then we develop the logic corresponding to these algebras, and we have shown that these algebras sound and complete. Okay.
off, right?
Okay, good afternoon, everybody. So first of all, I would like to thank Ramakrishna Mission and Bulagda and his team for giving me this opportunity to give a talk here. So this is not a new work again. It is it's a kind of a survey work which was done in last a few years. So basically, if you remember in our learning to model logic, we start with a basic model language, which is an extension of propositional logic and semantics based on Kripke frame. So we will see that apart from that semantics, there are many other semantics one can have for this basic model language. And and we are going to present some of those which are based on mathematical structures obtained from rough set theory. So I assume that all of us have some basic knowledge about the model logic that we will require. But anyway, I will present some basic things as well. So let us recall what is a basic model language. It is an extension of propositional logic, that is, we have Boolean connective negation and OR, and along with that we have one unary model operator, box. And of course we can define some other connectives like OR, arrow and diamond. And semantics is based on Kripke frame, which is a relation over some non-empty subset, and model is extension of frame with a valuation function. And the domain objects or elements of this domain has various names like objects, time points, depending on what kind of application or what kind of situation or in what kind of area we are dealing with. So we have the satisfiability relation, the usual one, and the box operator is defined in such a way that box alpha is true at a world if all the world accessible from W from the relation R, alpha is true over there. So let us see this example. So we have three states, W1, W2 and W3, and this propositional variable PQ are true over here, P and Q is not true over here, and both P and Q are false over W3. Then box P is true over here because the from W1 we can move to W2 and W1, and both the places P is true over here. So box P holds over at W1. On the other hand, box Q doesn't hold true because this W2 is accessible from W1 and Q is false. So box Q is not true over there. So what we are next, we are going to present an equivalent way to define the semantics. So let us recall that extension of a well-formed formula consists of all those states where alpha is true. Now using this notation, one can define we have this proposition giving us an equivalent way to define the satisfiability condition that we have just presented in the previous slide. And from this definition, the interpretation of these operators are more visible. So negation captures the complementation of a set, and this disjunct captures the union of the set, and this box actually captures this operator. What is this operator? This operator is an operator from power set of W to power set of W, which map a set to all those objects such that RW, that is all world related with W, is going to be contained in the case in subset X. So if one is familiar with the rough set theory, this is nothing but the lower approximation operator. It is already discussed in today's previous lectures. So this box captures this lower approximation. It is visible from here. Now this is the first point. Second point, if you see, if we replace this operator here and take some other operator on W, that is a map from PW to PW, what we will obtain is another semantics of basic model language. By taking different operator, we will get different semantics. This is the main idea. So what we will do, in literature one can find various semantics based on this simple idea. Both in even in epistemic logic we have some, and rough set context we also have a few more. So based on this simple idea, we are going to present some of the semantics. Before that, we just recall some standard notion of validity of a formula. Validity means this at all, extension of alpha is going to be the whole set. And valid in a frame means it's valid in all model based on the frame. And valid in a class of frame means it's valid in the all frame belonging to the class of the frame. These are all standard, nothing new. So the first one is semantics based on MSAS, multiple source approximation systems. So let us see. First recall what we mean by MSAS. So MSAS is actually, one can view a collection of approximation spaces, generalized approximation space. In other words, over the same domain. That is, we have a domain and a collection of binary relation over R. So number of relation, we don't impose any restriction. It can be finite, infinite, incountably infinite. Only thing we require is going to be countable. That's all. Two types of approximation were defined on these. The first one is strong lower approximation and the second one is weak lower approximation. So strong lower approximation is actually the intersection of all the approximation operator, and the weak one is union of all approximation operator, where the approximation operator in an approximation space I have already defined. And the dual of two operators are strong and weak upper approximation. So we have now this operator, and as I said earlier, if you remember, this box alpha, through set of this box alpha, I replaced earlier lower approximation with this LS. So first I am going to present the semantic corresponding to strong lower approximation. So here instead of LR we take LS and we obtain a semantics. And if we want a Kripke style semantics, this one we can define it like this, that is box alpha will be true if all world accessible from W by any relation, there alpha is going to be true. So our semantics is now this one, where this box captures strong lower approximation. So at this point, a natural question is about the axiomatization, definability, other things. So definability, invariance result, those things I am not going to touch, but we will just talk about the axiomatization issue. Before that, just one example to explain the semantics. So let us consider this example. So at W1, box P holds true. Why? Because from W1, I can take any relation to go only W2. So W1 and W2 are reachable by relations, and at both the places P holds true. So box P holds true. But box Q is not true because I can take relation either R1 or R2 to go this one, and here Q is false. So axiomatization result, the first one is this result. So let us, we denote by this lambda set of all formula which is valid, and we will index it with R, S and T depending on what kind of relation we are taking. So R means reflexive relation, S means symmetric, T for transitivity, RT means reflexive and transitivity, and so on. So we will use these notations. So as we can see that we have this axiomatization for all frame all MSA with respect to class of all MSAs, with respect to class of transitive MSAs, reflexive, transitive and symmetric. But we have problem with symmetric and transitive. We don't know exactly what will be the logic for this one. Further, it is done. I mean, I'm not going in detail to provide the proof, but I will just give an outline. So we actually the idea is that in this proof what we have done is that suppose we want to obtain a completeness for a class of MSS frame. So we lifted the semantics to corresponding model system relative to a semantics, known semantics, and then the completeness with respect to known semantics is used to obtain the completeness theorem. So in this case, we consider this mapping from the class of all MSS to Kripke frame, and one can show that it preserves satisfiability in the sense that alpha is true in the frame, in the model based on this frame, if and only if alpha is true in the model based on this frame. So here it is Kripke semantics, and here the semantics, the introduced semantics. So different semantics are there. And using these simple results, we obtain completeness for all reflexive and symmetric classes of MSS. In fact, we have used the fact that if we have an MSS consisting of only one relation, that is an instance of a approximation space as well, is a Kripke frame. So using this simple result, we obtain completeness and of course soundness for all these classes. But we have the problem when we have this transitive case. The reason is that this axiom for transitivity is not valid in the class of MSS. So completeness will come, but this will soundness, we will have trouble in soundness because this is not going to be valid over there. So what's the idea then? Then I will have to consider model system after removing this one. But if we do that, then this simple mapping is not going to work. So in other words, we will have to modify the mapping. So what we did, we are able to do it because we had the finite model property for the model system with respect to Kripke semantics. Using that finite model property, we are able to provide these theorems, and which lead us to the completeness of a transitive relations case as well. But this the construction what we have done here again fails when we also have symmetric property there. So if we have symmetric and transitive, then the construction that we have given is not going to work even for finite case. Okay. So next is W semantics. So in this case, we take this operator LW, and the semantics one can define in this way as well. So box alpha is true if there exists at least one relation such that alpha will be hold true at all world accessible from W with respect to that relation. So this is one example. Box P holds true because if we take say R1, so R1 we can go W1 and W3 only, and both the places P holds true. So box P is true. On the other hand, box Q is not true here because if we take R1, then we can go here and here Q false. Similarly, if we take R2 again, W3 is accessible and Q is false over there. So there is no relation such that with respect to that relation all accessible world Q holds true. It is not going to happen. So box Q is false. And this is the result that we have obtained with respect to W semantics. Similar notation we have used here. Now in this case, we have proved it by constructing canonical model. So just give you an idea how we did it. We will do it for these two classes first. So if you remember, the standard canonical relation is defined like this. And this one is the standard one when we prove completeness with respect to Kripke frame. So what we did, we consider an enumeration of set of all well-formed formulas. And then for each I take the same condition here, but now here formula was varying over all well-formed formula, but now for the relation I, we consider only the formula alpha, the ith element of that sequence. The ith element of that sequence. With this idea, we define Ri relation for all I. And natural question is how this relation and this relation is related. Then this is the answer. This is nothing but the intersection of all these Ri. So with this way, we define the canonical relation, and then the standard theorem, truth lemma, everything holds true, and we obtain the completeness one. Now, can we extend this one for a transitive case? The problem is that this relation is not transitive. So it means this way of defining canonical relation is not going to work. So in this case, what we do, again we return back to the standard canonical relation, and we note that it can also again be defined in this way as well, equivalently. So this one is equivalent to this one. And then now for this one, we again considered an enumeration of the set of all well-formed formulas, and we define Rwi by taking ith element of the sequence of this enumeration. Once we have this one, then this one is going to be a transitive, and we obtain the completeness theorem. So as we have seen, we are able to obtain completeness and soundness completeness for the classes of MSS involving non-symmetric relation. But when we have symmetric relation, again we have trouble. We are not able to obtain complete axiomatization. In fact, we have this result only for symmetric case. So this one was semantics based on MSAs. Second is covering systems. 5 minutes. Okay. Yeah. So second, covering. So just let us recall what we mean by covering. Covering of a set is 7 minutes. Okay. So what we mean by covering of a set means it's a collection of subsets of W such that union cover is equal to W. And covering along with the domain is called covering space, and a covering system is covering space along with a pair of operator, that is from power set of domain to power set of domain. So that one is called covering system, and these pair of operator may or may not be dual. Accordingly, if it is dual, we call it dual covering system, otherwise non-dual covering system. So these are the few examples of dual and non-dual covering systems. I'm not going to define all of these, but if anyone is interested, I would like to refer to this article by Pulakda and Sir. All the definitions are available over there. But since we are going to talk about these three coverings, I have just written the difference. So these two are dual, and this one is non-dual covering systems. So in the standard way, as I had explained, we define the semantics. So now the truth set is going to be lower approximation with respect to, we use the lower approximation. So if we take any covering system, dual covering system, we can define the truth set for the box operator like this, and we obtain a semantics. So each of the covering system, dual covering system, we obtain this semantics. In fact, for non-dual system, I will have to define it for box as well as for diamond using the two. But since it's a dual, the diamonds can be defined dually. And if we, this semantics can be written in this way as well. And this is the theorem that is proved in Minguma and Chakravarti MK, and some result is proved by us as well. So the approach what Minguma has taken is that, I have just used in previous slide, that in order to present a logic for a covering system, they lifted the semantics to a known semantics of the corresponding model system, and then the soundness and completeness of that semantics is used to obtain the required soundness and completeness theorem. In this article, we have taken a little different approach again, and we have provided an independent proof providing the canonical model. So here the canonical covering is defined like this. So we again take an enumeration, and for each I we define Ci to consist of all those maximal consistent sets which contains alpha I and box alpha I. And that way we obtain the canonical covering, and we will have to prove this to existence lemma. Using this, we obtain the completeness theorem. For this one. Okay. So for dual covering system that we have written here, only the axiomatization results for these systems are available. For other system, it is still open. As far as non-dual systems are concerned, situation is not that good. In fact, we have axiomatization for the system CT only. This is the only system for which we have the axiomatization consisting of these axioms. So basically, for each axioms, we take the box part and diamond part as well, because the operators are not dual. And yeah, it is done in this work. So last one is boundary operators. So can I have 3 minutes more? So last one, I will end it here. Boundary operator. So whole day we have talked about lower and upper approximation, but there is one another operator in rough set, which is boundary operator, which maps a set to its boundary region. And the dual is this one, which is also known as knowledge operator. And this boundary operator can be defined using a lower and upper, of course, like this. What about the converse? That is, can we define lower approximation operator using the boundary? Answer is yes, but only in the reflexive case. Other cases we will not be able to define. So again, we define semantics by taking a boundary operator here. And for this axiomatization, we have Fan, Wang and Dittmarsh, all they have a detailed study of this kind of semantics, but it was not motivated by rough set theory. In fact, they wanted to study the contingency logic, but it is related to the boundary operator. So this was completely studied. So the notion of this boundary operator can be naturally lifted to covering system as well, for dual covering systems using this one. And this system, this operator, boundary operator, can be used to define lower and upper approximation operator as shown here, but for the system C2, C5, P1. For other systems, and there are many systems for which it cannot be defined. And this is the, for this boundary operator, we have this result. So we are able to prove the result for C2, C5 and P1 systems. For other system, it is still open. And I have not listed axioms, so this is the list of axioms, whatever is used throughout this presentation. These were the model systems. So if any of the model system is not clear, one can check it here. Okay, thank you.
What is the problem with symmetry? I mean, why weren't you getting?
Which
the
system?
Earlier one you said for symmetry you could not get, right?
Which system?
Transitive they still managed, but not
MSS,
here, before the covering. Before the covering, yeah. Not here. So here you were not.
First, the axiom doesn't hold true. These two axioms doesn't hold true. And then canonical relation we are not able to, I mean the canonical relation whatever we thought about, it doesn't work. And we are not able to find a canonical relation. Moreover, we are also not able to find the transformation lifting of that one. So it is not like we are not able to do it. It is not possible to do it, but at the moment we are not able to do it.
Anyone else?
I'm just interested, we're completely ignorant, but can you do some systems weaker than the Kripke semantics, like the neighborhood semantic systems in this style?
Neighborhood. Actually, what that semantics I have not put in part here because it's a part of my PhD student thesis. We are working on that one. But it is weaker than the neighborhood semantics become a special case of that model. But since it is not published, not communicated, so I have excluded it from this slide.
Okay, that's interesting. Okay, thank you.
Okay.
In covering based approaches, the semantics is except those done with Ma. In Ma's case, there can be transformed into Kripke type semantics, but other cases, yeah, they are really covering based, I mean, neighborhood based semantics.
So, my case, all systems were normal, I think. Huh?
Yeah.
Okay. So if there is no more questions, so we can thank Akil once again, especially from me because I have imposed a little bit of time.
এটা জয়েন করো, মাইকটা কাজ করছে নাকি দেখবে।
হ্যালো
হ্যালো, হ্যাঁ শোনা যাচ্ছে?
হ্যাঁ
হ্যালো,
হ্যাঁ শোনা যাচ্ছে, হ্যাঁ শোনা যাচ্ছে।
ঠিক ঠিক আছে।
Hello.
Hello, can you hear me?
Yes.
Oh, good. I think we can hear you. You want to check your presentation?
Yes. Let me. Just give me a moment, please.
Are you able to share slides?
I think so. Let's say. Do you see them?
Okay. Yeah. Very good. We can see it now. So.
Okay.
Excellent. It's fine now. I think you just have to wait for a couple of minutes. So.
Okay.
People are still coming in.
Okay. So do you see them changing?
Yeah. You can see it changing. Okay. See the book. Yeah.
Okay.
Excellent.
Cool.
Yeah. Okay.
I don't see you, but it's fine. I mean.
You're not able to see. That's because it's. I think.
No. It's. I mean, it's no problem. Then
okay.
If you have some questions.
Yeah.
Maybe
I think.
I stopped.
I think now you can see us, right? Oh. Okay. Can you see now?
Yes.
Okay.
Yes.
Great.
That's perfect. Thank you. So you see the slides again now, right?
Hello. Hi, Stefano. Can you hear me?
Yes.
Okay. So this is Sujata. I am supposed to chair this session.
Okay. Thank you.
Can you see me? No? Yeah. Can.
Well, I'm seeing my slides, but maybe if I stop sharing, then. Well, yes. Now I see you. Then. I mean, when I'm going to start, then I'm sharing my slides. Again,
Yeah.
Okay?
No. Please, we are about to start in about a minute or two.
Hi, Hitoshi. Yes. So okay.
Yeah. Please
I'm
share.
sharing again. Do you see them now?
Yes. You see your slides. Okay. Maybe. Yeah. Into. Good. Get. Okay. Welcome to the last session of today. So our first speaker is Stefano Bonzio from University of Cagliari, and we are very happy to have you here at the Calcutta Logic Circle Annual Conference. It's over to you now, Stefano. Thank you.
Thank you very much for inviting me, and my apologies for not being there, but it was difficult actually to fly there in this period, and so thanks also for giving me this opportunity to give the talk online. It's not the same, but I hope you can enjoy or at least understand something of what I want to tell you. I'm talking about actually of, well, let's go through the outline. Maybe it's better than the title. So basically my talk is divided into parts. Apparently parts seem disconnected, but I'll try to find a common path. Them. So part one is about logics of variable inclusion. It's something I've been working on quite a lot in the past. Well, let me give also the credits to my co-authors, this, who are Francesco Paoli and Michele Prabaldi. And we published this paper, this book last year on topic, and I'm going to basically talk about some parts contained in the book. And then in the second part, I would like to talk about external clean logics. And let me say this is more my recent research, and this is in collaboration again with Michele Prabaldi. Actually, there is a connection between the two parts, and in my view, the connection is the use of the technique of Plonka sums. All this talk will be based on Plonka sums. So let me start by giving you the definition of logics of variable inclusion. I'm sure that some of you is already familiar with this, but some may not, so I'm going through all the definitions. So given a logic Vudash over some formula algebra, well, for a logic I understand just a substitution invariant consequent relation on a formula algebra. So V' can be your favorite logic. Then you can consider two new logics associated to Vudash. And the first is defined like this. So is Vudash L, and the formula phi follows from gamma in Vudash L, if and only if there is a subset of gamma, delta, such that the variables of delta are included in the variables of phi, and phi follows from delta. Actually, we call this the left variable inclusion companion, because you see, what is going on here is a variable inclusion, a sort of variable inclusion from the premises into the conclusion. So somehow from the left to the right. Similarly, in the same spirit, but just taking the opposite direction, one can define another logic, V'(R), where phi follows from gamma in this new logic, if and only if either phi follows from gamma and the variables of phi are included in the variables of gamma, of the set gamma, or the set gamma contains a subset which is an anti-theorem for the logic V'. What is an anti-theorem is just an explosive set of formulas. So it is a set of formulas which, for every substitution, derives any formula in the starting logic. And again, we call this the right variable inclusion companion, in the sense that there is, you see, there is a variable inclusion constraints going on from the conclusion into the premises. So ideally, from the right to the left. So these definitions might sound strange. For instance, this requirement of existence of a subset, or this requirement about the anti-theorem. But in the next slide, you will see the reason why we require this in the definition. And the reason is that we want to generalize some known logics. For instance, if you start from classical logic, then the left variable inclusion companion is paraconsistent with Kleene, and the right variable inclusion companion is Bochvar logic. So basically, all this theory is thought to generalize what happens for weak Kleene logics. But there are also other examples, maybe less known. So if you start from the logic from Priest logic of paradox, well, then the left companion is known, is a logic studied by Smuts. And then the right variable companion is known. It has been studied independently by Deutsch and Ferguson. If you start, for instance, from Belknap-Dan, then you get what is called FDE phi, and it's a logic that you can find in many papers, for instance, Daniels, Priest, and Ferguson. There might be other examples, but these are just let me say, the most famous that come to my mind. So our question, well, we normally work in algebraic logic, so our first question was how to construct an algebraic semantics for these logics of variable inclusion, starting from an algebraic semantics of the original logic Kudash. And here is where the theory of Plonka sums comes to help. So, as all of my talks, I have to introduce what Plonka sums are. I try to be as clear as I can. So, Plonka sum is an algebraic construction starting from semi-lattice direct systems of algebra. So, a semi-lattice direct system of algebra is just a triple where you have some algebras. So, AI is a family of algebras of the same type, so you can choose your favorite algebras. They might be, I don't know, Heyting algebras, Boolean algebra, groups, whatever you want. The index set is a semi-lattice with least element, okay? So here I'm indicating the semi-lattice just referring to the order and not to the operation, but just my apology for this abuse of notation. And then whenever an index I is less or equal than an index I prime, in the semi-lattice direct system there is a homomorphism from the algebra AI into the algebra AI prime. So from the algebra with the lowest index into the other algebra. And this homomorphism satisfies some very natural constraints. So for instance, PII is the identity. And these homomorphisms behave well with respect to composition. So if I is less or equal than I prime and I prime is less or equal than I second, then the compositions of the two homomorphisms is equal to the homomorphism on PI from the algebra AI to the algebra AI second. If you are familiar with directed systems, this is exactly the same. I mean, except for the fact that we are requiring the index set not just to be a directed preorder, but to be a semi-lattice with least element. So whenever you have this kind of object, so semi-lattice direct system, you can construct a new algebra, which is called the Plonka sum. And this construction is due to a Polish mathematician called Plonka. Actually, well, the correct pronunciation should be Płonka, but you know, I'm a lazy Italian, so I'm using the Italian pronunciation from now on. So my apologies. So I'm going to say Plonka anytime. So given a direct system of algebras of a certain type, the Plonka sum is the new algebra constructed in this way. So you have a system of algebras. So as universe, you just take the disjoint union of all these algebras, or the union. Here I'm actually assuming that all these algebras are disjoint. And then operations on the union are defined in this way. So take an arbitrary n-ary operation in your type and take elements a1, an belonging to the union. So how to define this operation in the Plonka sum? So basically what you can do, well, is looking where these elements belong. For sure, let's say A1 belongs to a certain algebra AI1 and so on. Now look at the indexes, which are in red now. So we have said that the index set is a semi-lattice. So what you can do is computing the join of these indexes and call it J. Then, of course, the join of all the indexes is greater than the indexes. So you can use the homomorphism in the direct system to take all these elements into the algebra whose index is the join of the indexes. Now, all these guys are elements of the same algebra, AJ, and what you can do is just computing the G operation in this concrete algebra in the system. So basically, you are taking all the elements up and then computing the operation there. In case your type contains constants, then the constants are computing in the algebras whose index is the lower bound in the semi-lattice. This is just a technical requirement. So if your type does not contain constants, then you can also forget about a lower bound in the semi-lattice, which is something that I'm going to do at some point. So maybe this construction is very abstract, but an example can help. So consider a very simple example of semi-lattice direct system of two 4 elements Boolean algebras. So these guys are the algebras. And then I'm just fixing that the index I is less than the index j. And this blue arrow is just the homomorphism from the lowest algebra into the other one. So this homomorphism is sending A prime to 0 and of course A to 1, to 1j. So how operations are computing in this Plonka sum? Well, for instance, if you want to compute A meet A prime, then these elements belong to the same algebra. So you just use the operation in the algebra where they live. So this is going to be A meets A prime in the algebra AI, so this is going to be 0i. Differently, if you want to compute the meet, for instance, between A prime and B, these guys are living in different algebras. So you take AI into the algebra AJ by the homomorphism, and then you compute the operation in AJ. So this is going to be 0j meet B, where the meet is computing here. So this is going to be 0j. The constants in this Plonka sum are just the constants in the lowest algebra. So this one, and so 0i and 1i. The theory, well, the theory of Plonka sums is fascinating in my opinion, and it is connected to many things, but in particular to what are called regular identities. An identity is regular, so an identity epsilon equal tau is regular if the same variables occur in the terms epsilon and tau. So for instance, associativity, commutativity, idempotence, these are examples of regular identities. And the variety of algebras is called regular if it satisfies regular identities only. If you want to, the simple example of a regular variety is, for instance, the variety of semi-lattices. The connection between regular identities and regular varieties and Plonka sum is the following. So it is a theorem by Plonka that states that if you have a direct system of algebras containing at least 2 algebras, then when you construct the Plonka sums, all the regular identities satisfied in the starting algebras are true in the Plonka sum, and every other equation is false. So all the equations that are not regular are false in the Plonka sum. Think, for instance, about absorption, which is a typical example of non-regular identity. It is falsified in any non-trivial Plonka sum. So, given a variety V, so pick your favorite variety, the regularization of this variety, which I indicate here as RV, is the variety which satisfies only the regular identity holding in V. In particular, a variety is strongly irregular if it is irregular, so if it satisfies at least an irregular identity, and it possesses also a binary term operation, f x x y, such that the variety satisfies that f of x and y is equal to x. So actually, you have in a strongly irregular variety, you have a term definable operation which gives you a projection on the first component. Actually, almost all irregular varieties are also strongly irregular. Examples are, for instance, lattices, but also any variety having a lattice redux, so Boolean algebras, Eyting algebras, but also groups, even so it's easy to check that also groups are strongly regular, rings are strongly regular, rings with unit, and so on. Another theorem by Plonka states that if you have V to be a strongly irregular variety, then any element in the regularization of V is isomorphic to a Plonka sum over a certain direct system of algebras in V. So regularizations of strongly irregular variety are particularly interesting because they admit always a representation in terms of Plonka sums. Just to mention an important example of a Plonka sum, consider an algebra of a certain type and consider an element infinity which does not belong to the universe of this algebra. Then consider the new universe given by the union between the universe A and this new element, and define operations on this universe as follows. So a generic operation on this algebra gives you infinity if infinity is one of the arguments. Differently, it gives you the operation computed in the algebra A between the elements, or all the elements A1, AN belonging to A. So basically, what I'm constructing here is a very simple Plonka sum between an algebra A and a trivial algebra, so a one-element algebra. Why this construction is, why this example is important? Well, from one side, because infectious logics are constructed in this way. So, for instance, the truth tables of Kleene logics are constructed in exactly in this way by starting from the two-element Boolean algebras and adding a third element, a third truth value, logically speaking. Algebraically, this example is very important because Laxer, Padmanabhan, and Platt proved that this gives you the subdirectly reducible elements of the regularization of the strongly irregular variety. So here is just Plonka sums. Where is the connection between logics of variable inclusion and Plonka sum? Well, in our first work on this topic, we found out that the regularization of the variety of Boolean algebras that we call involutive bisemilattices, IBSL, is an algebraic semantics for paraconsistent with Kleene logic. And, well, why am I writing an algebraic semantics and not the algebraic semantics? The reason is very simple, because IBSL is not the equivalent algebraic semantics of PWK, simply because PWK is a logic which is not algebraizable in the sense of Bloch and Pigozzi. So, in this old paper, well, it's a paper from some years ago, we first saw a connection between Plonka sums and a logic satisfying a certain variable inclusion constraint, as I told you. So from there, we started to wonder how to treat logics of variable inclusion using Plonka sums. And the idea that came to our mind was to extend the construction of Plonka sums from algebras to logical matrices, so to provide the semantics to logics of variable inclusion. The extension of the construction from algebras to matrices has been done in two different ways, taking into account that we have logic of left variable inclusion and logic of right variable inclusion. So, well, from now on, just for simplicity, consider types of algebras containing no constants. Well, we call an L direct system of matrices simply a joint semilattice and a family of logical matrices. So what we are doing here is basically substituting algebras with logical matrices. And the family of homomorphisms satisfying all the conditions which have been shown for semilattice direct system, plus a certain condition on filters saying that the image of a filter Fi should be included into the filter fj, of course, whenever I is less or equal than j in the semi-lattice of index. Similarly, we have also generalized the notion of this notion to the right case. So we have introduced also R-direct system of matrices, which are essentially the same. So you have again a semi-lattice. You have a family of matrices satisfying certain conditions. They are very technical. So, well, I'm just showing you so there are some conditions again on filters, but just for simplicity, let me go through this. I think that these technicalities are not very important. And then given an L or R system of matrices, we define the Plonka sum of matrices just by taking the Plonka sums of the algebras in the way that I have explained you before, and as a filter, the union of all the filters of the considered matrices. Actually, this allows to provide algebraic soundness and algebraic completeness for logic of left and right variable inclusions. In detail, if V' is a logic and X is an L-direct system of models of this starting logic, then the Plonka sum of these matrices is a model of the left variable inclusion companion. Just a matter of notation, given a class of matrices, we denote by Plonka PL of M the class of all Plonka sum of L or R or R direct system of matrices in M. And completeness is this. So if you start from a logic V' and you have a class of matrices containing the trivial matrix, so the a matrix whose algebra is the trivial algebra and the filter is the same, I mean, is the set of it. Then if the starting logic is complete with respect to this class of matrices, then the left variable inclusion companion is complete with respect to this with respect to this Plonka sum. Similarly, this works also for right variable inclusion logics. Well, you have just to assume that you start from a finitary logic, and what you get is also that the right companion is finitary. So again, you have soundness just by computing the Plonka sum of models. And you have completeness, so if you start from V' a logic which is complete with respect to a class of non-trivial matrices, then the right variable inclusion companion is complete with respect to the Plonka sum over the class M, to which you have to add a specific metric given by a model of the starting logic and with the empty filter. So somehow we could generalize and observe that Plonka sum are the suitable candidate to study algebraically the logics of variable inclusion. Well, so our study was algebraic, but this logic have a very weak relation with their algebraic counterparts. In particular, the logics of variable inclusion are not proto-algebraic. This implies that they are not algebraizable in the sense of Bloch and Pigozzi. Being not proto-algebraic is something stronger than not being algebraizable, and it means basically that there is no set of formulas, let me say, roughly speaking, satisfying modus ponens, the rule, a generalized rule of modus ponens. Then the left variable inclusion companion is truth equational. This means that somehow truth, so the belonging to a filter, can be equationally definable. But this is false. This is false, for instance, for the right variable inclusion companion. Moreover, Regular variety, it is true that regular varieties cannot be the equivalent algebraic semantics of any algebraizable logics. You see, this is just the generalization of what I've told you before for involutive bisimilarity. Okay, then what is interesting is that the technique of Blanc-Assam can be also used for other scopes in logic, in particular for providing Hilbert-style axiomatizations to logics of variable inclusions, to study also reduced models of these logics. Well, but I decided not to include this stuff in today's talk. You can find them in the book if you're interested in. And so I would like to close. This is the closure of the first part. And let me say that this is some essential bibliography on what I've just explained to you. In particular, if you are new to Blanc-Assams and you are interested to study a little bit this theory, then the paper, this review paper by Plonk and Romanowska is, I mean, it's a good starting point, but also the second chapter of our book maybe is more logically oriented. Well, if there is no question, maybe I go on with the second part.
Stefano, just can you please wait a minute?
Okay, I take it as a yes. In the second part, I want, as I told you before, I want to talk about external
Stefano?
logics. Yes?
Can you hear me now?
Yes?
Yeah.
Yes?
Okay. Before you move on to the second part, there has been some questions from the online participants. So let me just read them out for you. So the first question is that, is Blanc-Assam filtered colimit of algebras?
No, it's something, it's something, so yes, so let me go back. It's something very close to the limit, to the direct limit, no, not the colimit, to the direct limit, but it's not the same. It's not the same for two reasons. Well, first of all, because the index set is a semi-lattice, it's not just a preorder, and not just a directed preorder, but this is, while here, so operations are defined as in quotients, and while in Blanc-Assams, operations are defined in this way. So for instance, varieties are closed with respect to the direct limits, of course, by definition of direct limits, but varieties are not closed under the construction of Blanc-Assams. Because, I mean, because of this theorem, this tells you that not all equations are satisfied by Blanc-Assam.
Thank you, Stefano. Is there any way to get the reaction from? Yeah, okay. So the second question that Partho Pratim Ghosh, who was also gave you the first question, is as follows. Is there a connection between regular identities and regular epimorphisms?
I don't know, actually, because I don't know what a regular epimorphism is. So,
sorry?
I don't know. I don't know what a regular epimorphism is.
Okay.
So maybe there is, but I cannot say because I'm ignorant. So I'm sorry, but I don't know.
Okay, okay, no problem. Before continuing, I just want to ask if there are any question here. Okay, since there are no question, please, Stefano, please continue.
Okay, so let me go on. So what goes through from the first part to the second is just the construction of Blanc-Assam. So maybe you just remember, it's important to remember this. Okay, so let me start from, okay, so the logics of variable inclusions are defined in the same algebraic language of the starting logic. And this is somehow particularly relevant for weak-linear logics in the sense that weak-linear logics normally are defined in the same language of classical logic. Or at least this is the way that we understand now weak-linear logics. Because actually, if we go back to read the paper by Bochvar, who introduced weak-linear logics, he aimed to introduce them in a richer language, which he called the external language. And in my view, he had several aims in mind. I might be wrong with this, but at least this is the way I understood Bochvar. So, for instance, he wanted to speak about truthfulness of formulas at the propositional level. Okay, so he wanted to talk about a formula and the fact that a formula is true. Then somehow he wanted to limit the infectious behavior of the third truth value, which is, particularly strange in weak-linear. And then especially he wanted to recover classical logic inside the formalism of weak-linear. So to have a logic with 3 values with inside also classical logic. So in this second part, I want to tell you something about what we discovered about Bochvar external logic. Okay, so first of all, Bochvar external logic is defined in this algebraic language. So negation, disjunction, conjunction, and then 3 unary operations, J1, J0, J1, J2, and then the constants. So basically, it's the language of classical logic plus some external connectives, J0, J1, J2. The logic is defined using these truth tables. So negation, disjunction, and conjunction is just like weak-linear. So WK stands for the tables of weak-linear. And then these operators works in this way. Let's start looking at J2. So you see J2 takes value 1 if the formula is true, and take value 0 in all other cases. So somehow J2 of phi is saying that phi is true. And J1 of phi is true when phi takes 1/2 and false in all the other cases. J0 is true when phi is false and false in only the other cases. So basically you see that these operators takes only classical values. Okay, so in this sense, Bochvar called them external. Okay, Bochvar logic is the logic induced by this matrix, so the truth tables with the singleton of 1 as, so only 1 as designated value. And in this logic, some formulas are external in the sense that they can be evaluated into classical values only. So formulas that can be evaluated into 0, 1 only are what somehow they behave as in classical logic. So this is what I said before, you have classical logic inside. This logic, we proved that this logic is algebraizable with respect to the quasi-varieties of Bochvar algebras as its equivalent algebraic semantics. I'm going to introduce Bochvar algebras in a while, but you see that going from weak-linear to external weak-linear, or well, from Bochvar logic to external Bochvar logic, there is something, there is a mathematical gain. So you start from a non-algebraizable logic and you get something that is algebraizable. This is very interesting for us. And then for Bochvar logic, it holds this strange form of deduction theorem. So a formula phi follows from gamma and psi if and only if this implication follows from gamma. So basically, it's just like in classical logic, but you have to plug in J2. Now, Bochvar algebras were introduced by Finn and Grigolia in a very long paper of 30 years ago. The definition is quite complicated. So a Bochvar algebra is an algebra in the same language of Bochvar logic, and it satisfies all these equation and quasi-equation. Actually, I don't want you to go through, I mean, it's too long to try to explain what's going on here, but well, these two operations of conjunction and disjunction, they are associative, commutative, and idempotent. You have double negation, you have De Morgan, and then you have many things going on the external operations actually. And then notice that condition 19 is is a quasi-identity. Okay. Examples of Bochvar algebras. Well, the algebra of truth tables of Bochvar logic is a Bochvar algebra, and then every non-trivial Boolean algebra is an example of Bochvar algebra. You have just to set J2 to be the identity, J1 to be the constant into 0, and J0 the map, the negation. The class of Bochvar algebra is a proper quasi-variety. It means that it is a quasi-variety which is not a variety. This was proved by Finn and Grigoglia. And it is the quasi-variety generated by the algebra WKE of the truth tables. Okay, just remember that involutive by semilattice is the variety whose members are Plonka sums of Boolean algebras. Interestingly, every Bochvar algebra has a reduct which is an involutive by semilattice. If you take the JI free reduct, so the reduct without the external operation, this is an involutive by semilattice with the additional property of having at most one trivial fiber in the Plonka sum representation. So this suggests that Plonka sums can be used can be used also for Bochvar algebras. And I briefly explain you why through an example. So consider the algebra of WK of truth tables. This is just the Plonka sum of the two-element Boolean algebra with another element. Then this algebra WKE is not a Plonka sum, strictly speaking, because the operations J0, J1, and J2 are not computed. These operations, when applied to 1 alpha, are not computed in this algebra, but are computed down. So what you can do basically is to look at this guy as a Plonka sum, and then to add to this Plonka sum additional operations, which are basically maps from the highest algebra into the lower one. This observation actually holds for all Bochvar algebras, because it's easy to see that from the axioms that the operation J0, J1, and J2 are not computed in the same fiber. But anyway, Bochvar algebras has a reduct, which is the Plonka sum of Boolean algebra. So thanks to this, we could provide a Plonka sum representation for Bochvar algebras. The Plonka sum representation works in this way. So take a Bochvar algebra, look at its involutive by semilattice reduct. This is a Plonka sum of Boolean algebras. So consider this Plonka sum. And then on this is a special Plonka sums in which all the homomorphisms Pij with I less than j, all these homomorphisms are surjective but not injective. Moreover, for each index in the Plonka sum, there is an element in the lowest Boolean algebra such that the algebra AI is isomorphic to the algebra 0 AI, where 0 AI is the interval Boolean algebra. Okay? And this isomorphism is given by the map J2. And this decomposition as a spatial Plonka sum, let me say, is unique up to isomorphism.
Stefano, hi, sorry.
Yes?
You have 5 more minutes. Okay?
Okay.
Thank you.
So, okay. Also, the converse of this theorem holds. The converse means that, well, if you have an involutive by semilattice with a certain Plonka sum representation, and you impose that all homomorphisms are surjective, not injective, and you impose this, this game, and you impose that these maps are isomorphism, then there is a way, so I'm skipping a lot of details here because, then, well, there is a way to define maps J0, J1, J2 in such a way to get a Bosphore algebra. What is important here is that we are pushing, well, at least in my view, is that we are, the technique of Plonka-Sams was used in the past only to study regular varieties, and in recent years we are seeing works, not only these, but also works from Peter Gibbs and Jose Gil Ferres and other authors, trying to use this technique to push this Plonka-Sam beyond the limit of regular varieties. So what is important here is that thanks to this representation, I'm skipping the details, but thanks to this representation, we could study the lattice of subvarieties of Bosphore algebras, which is just a three-element lattice. I'm just skipping the details, so maybe I leave this for questions. Yeah, so I'm skipping this, and also we could also prove that the quasi-variety of Bosphore algebra and also NBCA, which is the other subvarieties, have the amalgamation property, and the Plonka-Sam representation is essential in order to get this. Sorry for being late. Well, just some. Here I have some bibliography on the second half. Then, well, what's for the future? For future work, so let me say that I just won a project called Developing Clean Logics and Their Applications. And within this project, I would like to study modal logic based on all clean external logics. Maybe try to generalize clean external logics in the same way that following the idea from which we generalized from weak clean to logics of variable implications. Then to model knowledge and ignorance using external weak clean logic. This is something that I've already done, actually. Well, I've already done something on this. And then the project has also application, hopefully, in computer science. A very small advertisement to close. So we will have 2 postdoctoral positions in the project opening soon. So if you are interested in this, or you have students interested in this, please contact me. And well, that's the end. Thank you very much for the attention.
Thank you, Stefano. Very nice talk. Yeah, we have a couple of minutes for some quick questions, please.
Yeah, Stefano, I think I have quite a few questions. Maybe I'll ask the top 2. So one is, you mentioned these J0, J1, and J2, these operators. These are the external operators, if I'm not mistaken, right? Or, yeah.
Exactly.
So is there a translation possible of these to some modalities? Because these kind of sounded like modalities.
Okay, the answer, the real answer is that I don't know, but I have the impression that this, that you're right, because they seems to belong as modalities. But actually there is only, so let me go back to this. So on model logic based on clean external logic, I just know one paper, an old paper by Christer Segerberg from '75, where he does this, and for sure there is a relation, but it's not in the paper. So I think there could be a translation, yes.
Okay, thanks. And the second question is this construction of the Plonka-Sams. So once we go into this infectious element, once we are transferred via the homomorphism to this infectious, you can call it the trivial algebra of the same type as well. we don't have a way to come back, which is why the infectious behavior happens, right? So let's say this half, or this external element half that you attach to Boolean algebras, which takes you from the 0-1 Boolean algebra to the infectious element, there is no way to come back from there. Once you...
Okay.
Am I making sense? So the infectious logics have this property that if you have, if anything gets the infectious value, then the whole formula will get it. Because in the semantics, what's going on is you move from the base algebra to this trivial algebra, which has the infectious element in it. At least that's what happens in PWK. And so my question is, if you, or have you thought about putting some other element which will, or some other process which will let us come back to the base algebra? I mean, it's just a thought. I don't know if it's making sense.
Well, I understand what you mean, but the answer is no. I mean, well, I haven't. Let me go back to this. Okay. So
yes, exactly.
Yeah,
that's where my question
is. So this is what happens in external Bochvar logic, or in, well, there is also external PWK. Okay. So external PWK, well, here we focused on external Bochvar logic, but there exists also external PWK, where you have PWK and you add the external operators. And this logic has been studied again by Christer Segerberg. But no, so, and the idea is exactly this. So you take the Plonka sum, so you have an infectious truth values, and then somehow you have some formulas that can be infected, let me say, and some others that cannot be infected because you plug in the external operators. So maybe it's possible to do what you suggest, so to go on and having another, another trivial algebra here, but I've never seen something like this. So I don't know if this answers the question, but
yeah, thank you very much. I'm sure we can keep talking later.
Okay.
Yeah, there is one more question from Hitoshi.
Hi, Stefano. Thanks a lot for the talk. I like the second part because I know about the first part already, obviously. For the second part, so you mentioned about the Halden's work already, partly in response to Shankar just now. But am I right that you can basically do the same thing? Like, is there going to be the left-right thing going to be producing the Halden's logic and Bochval's external logic? Is that what's going to happen, or is it going to be somewhat different?
Okay, no, well, sorry, it's not Halden, but the paper I was mentioning on PWK external is Segerberg.
No, but I think Halden already had the logic with the partly external connectives. So Halden wasn't really purely PWK, but he already had some additional connectives.
Okay,
yeah.
Cool. I didn't know.
Yeah. Well,
yeah. I think your question is about this. So if there is a way, so if external clean logics are an example of a more general phenomena, right? So this was this. I don't know. I don't know because for weak clean it was easy because there was for PWK there was a theorem by Chuni and Carrara stating the variable inclusion constraint, and for Bochvar there was a theorem by Arcart, if I'm not
that's right. Yes.
Wrong.
Yes.
But I have no idea if this. If there is a connection between external cleaning, so external Bochvar and external BWK, and some sort of variable inclusion constraints.
Yeah, right.
So I cannot say.
I see.
And actually, okay, yeah.
No, that makes sense, of course. Right. Good. And then I just wanted to add one more. So you mentioned about the external Bochvar being algebraizable, right? But then you have the three external connectives, J0, 1, and 2. But 2 and 0 would be enough to define the rest. But the definability...
Only two actually.
Yeah, but then if you only have 1, then 0 or 2 isn't going to be definable. So my question is that expansion going to be already algebraizable, or is that not yet algebraizable? Do you know the answer?
I don't know the answer. Because, sorry, I make more precise what you said. It's true that actually here I'm taking it's true that here I'm taking just for simplicity, I'm taking too much language.
Yes.
Because here I'm just following Finn and Grigolia. It's just enough to take J2 in order to define J1 and J0.
Yeah, exactly.
And so if you take just J2, you have Bochvar external, and this is algebraizable.
Correct.
It's also true that if you have J1, you cannot define J2 and J0, so you have a different logic.
It's somewhat weaker. It's something in between.
So algebraizability is not directly passing through Bochvar external to a fragment. Okay. If I'm
No, okay.
Yes.
You have to let me know.
Because actually, because the translation, the answer is I don't know.
Okay.
Because if you have only J1, this is a linguistic extension of a non-algebraizable logic, which is Bochvar internal. Okay?
Yeah.
And it's a fragment of an algebraizable logic, but algebraizability passes through J2.
Okay. Interesting.
So the answer is I don't know, but anyway, I think that this fragment could be interesting.
Okay, great. I'll shoot you an email later. Thanks a lot.
Okay. Thank you, Hitoshi, for the questions. And
Thank
all
you.
The others, of course.
Thank you, Stefano, for the very wonderful talk. Thanks again.
Thank you. Thank you very much.
Yeah. So where is... Please check. Yeah. Share screen. You would let them share this. Yeah. So. Hello, this is Sujata. I'm supposed to chair this session. So, Professor Sankappana, or can you please share your screen, the slides?
Yes,
Will
please, I can. I can.
Okay. Can you hear me properly?
I think you see me. Yeah, I can see you.
Yeah, I can
properly,
see.
yes.
We can see you.
Yeah. So can I share the file?
Yeah, please.
Okay. And there, something's happened.
Participate.
Hello?
Hello?
Hello? Can you hear us?
Yes, please.
Okay. Yeah, we can hear you, but we cannot see you. Also,
Yeah, one second, I'm just turning the
yeah.
camera on.
Okay. I think
okay,
you
okay.
can see me now.
Yes, yes, we can. And maybe some slides. Will you be able to share the slides now?
Yes, please. 1 second. And there. Come.
Go to the present.
Right.
Yeah. And then go to window.
That-
And
that one.
This one.
Yeah.
No, it's not it.
No? It is. That's the one I had. No? That. You make it larger. That one first. Yeah, you can. I earlier tried. Yeah.
Hold on. Okay, then you do it. Oh, and it's not there, shareable.
No?
That's the wrong thing.
What is happening?
Stop the share.
You want to sit?
No, just
That's the one.
yeah, share that.
Maybe the other one? Actually. Yeah. But is it showing?
It should be.
Okay.
Ask them.
Can you see my file?
Yes, we can see your slides. So maybe it can be made full screen so that.
Sanjay, full screen.
Yeah.
Maybe you can expand this. Yeah?
Right.
Can you see? Hello?
Yeah, we can see it. Thank you.
Did it come full screen?
Is it full screen?
In them.
Professor, did it come full screen?
Lost the- Yeah, can you
Professor, how do you make it
please
full
share
screen in
the
Google Meet
slides?
for you?
Can you please share the slides again? Sorry, something happened here.
We are used to Zoom, but not this one. My son is helping me here.
Professor, is that showing up?
It is showing up. Yeah.
Is it big
But
enough
can you
for you to see?
Can you please make it full screen then?
How do you do that? We're not used to this Google Meets. We're used to
Yeah,
Zoom.
now it's fine.
Is it?
Again, sorry, again you have to make it full screen.
How do you do that?
If I make the full screen, I lose to see you guys.
No, but he cannot see us if he makes. Stefano was not able to see us, so that's.
Can you
They
see?
can yeah, now it's fine.
Now it's full screen?
Yes, yes, now everything is fine, but
Okay.
Okay.
but we can't see this.
Of course, you don't
speaker.
see me now.
Yeah, yeah, that's another problem. Yeah, I
That's
think
okay,
that can
if
still
that
be
is okay
done.
with you.
Let us try. That can still be done.
Okay.
Yeah, pin to screen.
Oh.
That's all. Yeah, perfect now.
Yeah?
Yeah. Okay, thank you. Let's start.
Thank you.
Yeah, so Professor Sankapanavar needs no introduction to this audience, and I wouldn't even dare to introduce him. So it's over to you, Professor Navar.
Thank you so much. And I'm sorry for all this trouble. And okay, now let me start. Okay, let me start by thanking Professor Basu and the other organizers of this conference for inviting me to give this lecture. And also I would like to thank all of you for attending my lecture at this late hour in your time. Okay, here is my quick outline. I will start with regular double stone algebras and regular clean stone algebras. Some of you, I'm sure, have heard these when I gave another lecture at IIT Kanpur. But this will be more an introduction. And then I will go to a new variety called Gautama algebras, which are the common generalization of these two varieties, namely regular double stone algebras and the regular clean stone algebras. And these are named in honor and memory of the founders of Indian logic, namely Medhatiti Gautama and Akshapada Gautama. And then I will go to a recent and further generalization of Gautama algebras, so-called almost Gautama algebras. Then I will give a complete description of the subdirectly irreducibles in that variety and some consequences. And then I would like to find a logic for this variety, but this variety doesn't have the arrow, so I needed to find another nice variety which does have an arrow, and that led us to this variety of almost Gautama hating algebra. And then we will be able to see a logic associated naturally, and you will know what I mean by naturally, with almost Gautama algebras, and also several of its axiomatic extensions corresponding to the subvarieties of the variety of almost Gautama. Every subvariety will have a logic. And then I will mention a few open problems. Okay, here are the definitions. Most of you know this, but I will repeat anyway. An algebra A in this language, where there is a star and a plus, unary operations other than the binary join and meet, is a regular double stone algebra if the star reduct is a stone algebra and the plus reduct is a dual stone algebra. That's why it's double stone algebra. And those algebras need to satisfy an additional identity, which is called the regular identity, introduced by Katrinac, and that was x meet x plus is less than or equal to y join y star. Max the clean axiom type, but in this context it's different. Or equivalently, another axiom, which I call R1 and still call it regular, and that is x meet x plus star plus is less than or equal to y join y star. It is this observation that R and R1 are essentially equivalent here is all the root for all the 3 papers that we have written recently. It is this observation. You will see it comes up quite a bit. And this variety I'm going to call or abbreviate by R for regular, DBL for double, ST for stone. So you can easily remember it, R, DBL, ST. Then the regular clean stone algebra. Again, the star reduct is a stone algebra. and the prime is a clean algebra, prime reduct, and it satisfies this R1 using the star and the prime now, not the star and plus, of course. And we will denote this variety by RKLST again, regular clean stone. So you will remember it. Now let's look at some examples. So start with the 3-element chain, and that let's look at these 3 operations: the pseudo complement, the dual pseudo complement, and the De Morgan operation. There they are. Now if we put the star and the plus, if we expand the distributive lat by this signature plus, and star and plus, you will get this algebra, which I call 3 sub DBLST, and this happens to be, by the name you know, is in fact a regular double stone algebra, and this was actually introduced by Harley. The notion of regularity was introduced by Harley in 1971, and Carter enacted quite a bit of. And then you take the star and the prime, you get regular clean stone algebra, the 3 KLST, and this was first introduced by Romanovska in 1981, and then I wrote some papers later. And before I proceed, just look at the similarity of these 2 algebras in the type and in the definitions. It will play an important role. And let's look at some results that are known for both of these varieties. The simples, the subdirectly irreducibles, the directly indecomposables all coincide, and they just happen to be these 2 algebras. 2 being the 2-element Boolean algebra, by the way. And you can take any type that you want that is convenient and compatible with others. And the 3 DBLST, these 2 algebras are the only simples, only subdirectly irreducible, and only directly indecomposable. And that leads us immediately to this conclusion, namely the variety itself is generated by one algebra, namely 3 DBLST. You might wonder why 2 doesn't appear there. Well, 2 is a subalgebra, so it gets absorbed. By the way, the operator V means HSP. That is the variety generated by whatever goes in the parentheses. And it turns out that this variety is what the universal algebras like is a discriminator variety. It's a very nice class of varieties. I don't know whether I should define it. If in the questions, if somebody asks me, I will answer that. And the Boolean algebras form a subvariety. And that's the only non-trivial subvariety. And going to the RKLST, similar thing happens. The simples, these subdirectly irreducibles, and the directly indecomposables coincide, and they all happen to be these 2 algebras, 2 and 3 KLST. So again, you get the variety is generated by the 3 KLST, and it also is a discriminator variety. It was proved by me some time ago. And BA is the only non-trivial. Look at the similarities of these 2 A and B results, and that immediately makes any mathematician get tempted to see if there is a common generalization, and that's exactly what will happen now. But let's first look at what are the common identities that are true in both these 2 algebras, and hence in both the varieties that they generate. So the language is this for both, and now we will observe that both had the stone algebra redux with respect to the star, and both algebras, of course, the plus and the prime are not the same, but they do satisfy some common identities. Here they are. 0 prime is 1 and 1 prime is 0, and the meet De Morgan law holds, and the weaker join De Morgan law. You have to go to the double prime, and the double prime is less than or equal to x. All these hold in 3 DBLST as well as in 3 KLST. And The regularity also is true in both of these, namely this R1, X meet X prime star prime is less than or equal to Y join Y star. And there is another one more identity. I call it star regularity, and that is this identity. If you apply star and then prime on one side, if you apply two double stars, the two terms happen to evaluate to the same element. So the identity holds. So here is what is common, and that leads us to the new variety. But before I give that definition of the new variety of Gautam algebras, let us look at the identities in item 2, A, B, C, D. They are actually not new. And they had already appeared about 35 plus years ago in 1985 in a paper of mine called Semi-De Morgan Algebras in the Journal of Symbolic Logic. And there is a name for them, so let's do that. So an algebra is a dually hemimorphic algebra if it satisfies the first three conditions of that. Of course, it sits on the lattice, so it has a bounded distributive lattice reduct, and the prime satisfies those three conditions. Then 0 goes to 1, 1 goes to 0, and the meet De Morgan law holds. And if you add the other two axioms, then we call it dually quasi-De Morgan, the subvariety. So those two axioms. Now we are ready to give the variety of Gautam algebras. As you can see, the A is Stone algebra, the B is that second condition, which now has a name, dually quasi-De Morgan algebra. And the third is the regularity, and the fourth is the star regularity. So this is what the Gautam algebra is. And of course, whenever you all know, you define a new variety, of course, the first question to ask is, what are the simples, what are the subdirectly reducibles, and so on. But before that, I will actually give some examples. And let us denote this variety by G. Okay, here are some examples, and important ones too. You will see why they are important. The 2, the 3 DBLST, and the 3 KLST are all Gautam algebras. And hence, the Boolean algebras, the regular double stone algebras, and the regular clean stone algebras are actually subvarieties of this variety. And now, let us describe the subdirectly reducible Gautam algebras. And so you wouldn't be terribly surprised what the result will be. That. In other words, these three algebras that I just mentioned are in fact the only simples, the only subdirectly reducibles, and the only directly, and all those notions coincide on them. And with this theorem, we can actually get some interesting consequences. For example, this variety is actually nothing but the join of those two varieties, the regular double stone algebras and the regular clean stone. That's because of 5. The 2, of course, gets absorbed. So it is the variety generated by 3 and the variety generated by 3 KLST. And to prove this, you will have, use some universal algebraic tools like this congruence distributive and so on. But that is what happens. Okay, and also here is that being discriminator variety continues as we have extended these. So this is a discriminator variety. All these results that I just mentioned about the Gautam algebras and some other consequences are, they have already appeared in a chapter entitled A Few Historical Glimpses into the Interplay Between Algebra and Logic and Investigations into Gautam Algebras in a Handbook of Logical Thought in India, edited by Professor Sarukkai and Professor Chakupati. So it's a very recent publication, last year, end of last year. It is now available. Okay, and now can we generalize the Gautama algebras? And here, Professor Cornejo has done work with me, so it's a joint work. From now on, everything that I say is a joint work between us. So the obvious question is, can we generalize the variety G even further? And the answer is yes. And here is a clue given by this lemma. Just look at that. The variety of Gautama algebra satisfies this identity, which actually is sort of weaker than this star regular identity. Namely, well, apparently it doesn't look, but you can actually prove it. Here is the little proof. So simple proof, so I will prove it. You start with an element A, apply star and double prime, that is the left side of the identity. And now you apply the definition of Gautama, where the star regular identity, apply that identity, you eliminate the first prime. So star prime becomes star star, then apply again. It becomes star star star, and the star being the pseudo complement, it becomes one star. So it proves that. And the second condition is simply, it has something to do with some levels, but this is all I need, so I will just call it level 1 now. And that is, if you take this term, x mut x prime star, you apply one more prime star to it, you get back to the previous term. And if you apply one more prime star on both sides, it is the level 2. If you apply another one, it is the level 3, and so on and so forth. But here we don't need that. It disappeared in some other kind. But anyway, those two identities are true in Gautama algebras. So we will now define the generalization of this, which we call almost Gautama. And this, of course, again, still A is Stone algebra, and the B is still the same, and C is still the same, regularity, but it is the star regularity gets replaced by the weak star regularity, that, the conclusion, first conclusion in the lemma that we just saw, and also the second conclusion in the lemma. So this is now called an almost Gautama algebra, and of course it's clear that it's a variety. For those of you who might be wondering that these are all identities or not, looking at this one, you might wonder, is it an identity? In fact, you can convert that into simply writing x mut x prime star join y star equals y join star, and that definitely. So it's all identities, therefore it's also a variety. And AG denotes this new variety. So again, you look at the examples, and then you look for the simple algebras and so on. So here are the examples. Those three that we have seen, the Gautama algebra, they continue to be in this variety. Then question, if they were the only one, this will be the same as the other one, but obviously I wouldn't be talking about this. So there is at least one more interesting algebra, and that is this one. This one. So here there is a 4-element Boolean algebra with respect to star, and the prime simply fixes the middle element. The A is the same as A prime, and the A star is the same as A star prime. A star prime is the same as A star. So it fixes those two. And with respect to prime, you can check it's a De Morgan algebra, but not Kleene anymore. And with respect to star, it's a Boolean algebra. So you can call it as a De Morgan Boolean algebra on 4 elements. And here are the subdirectly irreducibles, very surprisingly, as you can see. Again, the simplicity, the subdirectly irreducibility, and the directly indecomposability coincide, and the result are these 4 algebras. So the 4 DMBA comes in as a new one. So now that we know the subdirectly irreducible algebra, we can get some interesting consequences for this variety. You can say now that the variety is in fact generated by the two 3-element algebras and the 4-element algebra. And based on that, it is immediate that equational theory is decidable. The reason being, if you give me an identity, I simply check that identity against these 3 algebras. If it is true in all of these 3, then it is true in the whole variety. If it fails in one of them, then it fails in the whole variety. I just gave you the algorithm for the decidability. Okay. And now if you look at the Gautam algebra, they happen to be just the variety generated by the 3DBLST and 3KLST, meaning the theorem that we came up with for Gautam algebra is now a consequence of this. So that is the power of unifying in mathematics. Okay, now let's look at the subvarieties, how many there are, what kind of structure they have. Here I'm only going to look at the non-trivial subvarieties for a good reason, because above the trivial variety, there is only one atom, that is the Boolean algebra. Everything else is above the Boolean algebra. So it is enough to look at the lattice of, it is actually an interval in the original lattice of all subvarieties. And as a special case, you get the lattice of subvarieties, non-trivial subvarieties for G also. And here is the picture. So it is actually an 8-element Boolean algebra, and you can see the 3DBLST, 3 and 4 DMBA, and 3KLST are immediately above 2. They are covers for Boolean algebras. And then you take the joins pairwise, and those are the 3 joins, and then of course their join is the AG. So no complete description of the lattice of subvariety. And it maintains that property of discriminator. So it's a nice variety. And here is a result that I would like to mention now, which also applies to others, but there is a well-known result due to Burris and Werner, which says basically a finitely generated discriminator variety, its first order theory is decidable. And AG fits right into that condition. So first order of AG is decided. First order theory means you look at all first order sentences that are true in AZ, is that set decidable? What we are saying here. Okay, now let's look at the equational basis for the subvariety. If you were looking at on their own, what would be the axiom system for them that characterize that variety? Of course, for Boolean algebras, it's very simple. The star and the prime coincide. And for the 3DBLST, the first identity says that the prime, in fact, is a pseudo-complement, dual pseudo-complement, I beg your pardon. And the other identities also work out. And for the 3-element KL stone variety, that star regular identity holds, and you need this involution axiom, x double prime x. And for the 4, any one of these 3 identity, when you add them to the axioms of AG, you get the axioms for 3ML. And so, for example, take the first one, which is the famous logical thing, the excluded middle. Okay. And the other one is double star is same as that. It's closure with respect to double star and so on. And the join of 3DBL and 3KLST varieties is given by because it's G, and it's just the regular identity, putting that is enough. Whereas this one is a bit, this one meaning 3DBLST and the 4, we have to search for them. And luckily, I had looked at this identity in a different paper for a different reason, and I tried that and it worked for this. So this identity, which I call JID, because the join distributes over arrow. I is the implication there, JID. Of course, it's not in full form because the variable x is primed. This full form is called strong JID. But anyway, so this is JID. And finally, the 3 KLST and 4 DML, all you need is the involution axiom. Okay, so that is the varieties that I wanted to discuss with you. Now the next goal is to look for a logic for this almost Gautama algebra. But unfortunately, as I said in the beginning, the implication connective is missing. So we now consider this language where there is an implication, and we now introduce another new variety called almost Gautama hating algebras. And it happens to be a sub-variety of the variety which you kind of already heard, namely dually hemimorphic operation added, but now to hating algebra. So it is a sub-variety of the variety of dually hemimorphic hating algebras, which have been extensively studied from logical point of view in the following paper, namely a logic for dually hemimorphic semi-hating algebras and its axiomatic extension, which recently appeared in Bulletin of the Section of Logic. I think it's around over 90 pages or something. And it has a lot. So if there is any student who is looking for thesis problems, they might want to look at that. Okay, that's a little bit of pitch. Pardon me. Now let's define this dually hemimorphic hating algebra. So it is in that language, and if you throw away the prime, what's left is a hating algebra. In other words, it has a hating algebra reduct with respect to arrow. I just put in those axioms there to bring to your notice, but this set of axioms has played an incredible role in all of my research, which has led to several new kinds of algebra. Then the operation prime is dual hemimorphism. That means those three conditions that you have seen earlier are true. So that's what dually hemimorphic hating algebra is. And we denote it by DHMH. D for dual, HM for hemimorphic, H for hating. Okay, now we'll look at a sub-variety of that, which, as you would expect, the dually quasi-De Morgan hating algebra, and that may satisfy the additional last two axioms that we had seen earlier, the weak joint De Morgan law and the double prime is less than or equal to X. And this variety would be DQ, denoted by DQDH, D dually QD quasi-De Morgan hating algebra. Okay, so now we can define what is an almost hating algebra. We have all the terminology. So first of all, it should be the DQDH algebra, meaning it satisfies all the axioms of dually quasi-De Morgan hating algebra I just mentioned. And all these axioms, which by now you are familiar, namely the Stone identity, but remember the arrow is a hating algebra. So if you define X star as X arrow 0, and it's well known that star is a pseudo complement. So therefore you can write down the Stone axiom. So it is a Stone hating algebra as a reduct. And it satisfies that regularity condition, and it satisfies the weak star regularity and the level 1. Those axioms A, B, C, D are exactly the same for the almost Gautama algebras, as far as the prime and star were concerned. Here there is an arrow and the prime. Okay, the variety is denoted by AGH, A for almost, G for Gautama, H for hating. And it happens to be by a subvariety of DQDH, as I pointed out in condition 1. Okay, examples. You take the 3-element chain and define the arrow as the hating arrow on the 3-element chain. You all know that the hating arrow looks like what I have written here. And the plus is simply the dual pseudo complement. 0 goes to 1, 1 goes to 0, and A plus is also 1. So that is the uh, dual stone heating algebra. And this also satisfies the regularity and all the other conditions. So it is an AGH. That's one example. And you can now define the 3KLH very similarly. The H, the arrow comes from heating, and the prime is the clean A. The fixed A prime is A, the other to go to each other. And this also satisfies those axioms, therefore it is in this variety. And here is another, but this time you look at this picture not as the star one, but as an arrow. So Boolean algebras can be defined using arrow and negation also. So here, it's the Boolean arrow, or if you want, it's the hating arrow, they are the same. And the prime is the De Morgan arrow. It fixes the two elements. So it's a De Morgan hating algebra this time, or Boolean algebra. Anyway, so you now know the examples, at least some salient examples. Why are they important? You will see in the subdirectly reducibles. So here is a description, very similar to the others, that it worked for this variety, that these axioms are very similar. I mean, these conclusions of the theorem are very similar to the conclusions of a similar theorem earlier, was what was a bit of luck for us. Okay, and in here, if you only look at 3DSTH and 3KLH, that variety was named as GH, or Gautama hating algebras, in the chapter in the handbook that I mentioned just a while ago. These have appeared there, but now this one is a generalization. AGH is a generalization of GH. Okay, so that also is a discriminator variety. And the first order theory is decidable for the same reason I told you earlier. Okay, now this theorem is crucial for us to bridge between logic and algebra. Why? Look at this. The varieties AG and AGH are term equivalent. What does that mean? Four things must happen. If you give me an algebra in AG, then I will define an algebra in AGH by defining an arrow, and the arrow is a very complicated formula. X arrow Y is all of that. And I don't take the credit for that, by the way. The credit really for this amazing formula goes to Kaczmarek. And Kaczmarek was the first who found this in the context of regular double stone algebra, or double P algebras for that matter. But his was slightly different. The difference was, can you see me the cursor here? Anyway, this prime star prime, he had put in there the dual pseudo complement plus, and of course we don't have the dual pseudo complement, but its equivalent expression works, and that was a bit of luck for us, and that allowed us to go from an algebra in AG to an algebra in AGH, and the reverse is simpler. If you give me an algebra in AGH, I can give you an algebra in AG simply by defining the star as X arrow 0. And that happens to be AG. And these two operations, these two conditions say that they are in fact inverse processes each other. So that is what we mean by term equivalent. In other words, you have clear-cut translations going from one to the other and go backwards. So basically they are the same in that sense. Okay, now we are ready to define the logic corresponding to almost Gautama hating algebras, but that requires a lot of logical machinery. So I'm going to review some stuff very quickly, and I think most of you know them, and hopefully all of them know. Okay, so this is a language for us throughout the rest of the talk, as has been before. and you know the set of formulas how to define, and which is denoted by FML. And this is an important observation I want to highlight, namely, this set can be turned into an algebra formulas denoted by the bold case FML. And this goes back to Lindenbaum-Thursky, and that is when I would say the really modern algebraic logic took off. And this has gone quite far, and I will touch upon how far it has gone and even further in a few minutes. Okay, so the gamma is a set of formulas, and the lowercase Greek letters are single formulas. Now, because FML is an algebra, now we can use the algebraic concepts and talk about homomorphisms from this formula algebra into any given algebra of the same type of. All algebras considered here are of the same type. And those homomorphisms, an algebraic notion, are now called the interpretations, the logical notion. And the substitution, okay, this set of homomorphisms is denoted by the HOM, standard notation. And if H is a homomorphism or an evaluation or an interpretation, then H of alpha is in A, and that's the notation. But I just want to point out this other notation. H bracket gamma is the set of all images of H of all the members of gamma. That is a very useful shorthand notation. And substitution is simply a very special homomorphism from the formula algebra to itself. So again, substitution becomes an algebraic notion. And here are some very important basic logical notions. I think all of you know this. The consequence relation on the formulas, set of formulas, is a binary relation between sets of formulas and single formulas that satisfies the following three conditions. And I don't even read them because I know you all know. A consequence is finitary if there is a finite subset of gamma that does exactly what gamma does, proving phi. Now, the structural consequence relation, I do want to point out, a consequence relation is structural if it is a substitution invariant. What does that mean? If gamma proves phi, then sigma of gamma proves the sigma of phi. So if you apply substitution, the behavior, early behavior doesn't change. And of course, substitution, as I pointed out, is a homomorphism from that to that. Okay, now this enables us to define a notion of a logic, which we have already seen in the talks earlier. A logic is a pair consisting of the language, L, capital L, boldface L, and a structural finitary consequence relation. You might ask why finitary, just for my talk, because that's all I need. There are logics, where you don't assume finitary nowadays. Okay, we know the notion of logic. And using that, we can define what is called relative equational consequence relation. And for that, we need some terms also. Identities are nothing but pairs of formulas, but we write them in this form, formally, when there is no interpretation whatsoever. And if X bar is a finite sequence of variables, and if you apply an interpretation to it, then we write the values, the sequence of values as A bar for convenience, instead of writing H of X. And here is the universal algebraic definition of what is a satisfaction of an identity. An algebra A satisfies an identity if and only if the interpretation of alpha in the elements are in the sequence of elements A bar, which will be an element of A, and similarly you interpret the B using the A's, you get an element in A, and those two elements must be. And such a situation must happen for all evaluations, for all sequences A bar. That's what satisfaction is. by an algebra. So now we can extend that to a class of algebras, and that's pretty simple. K satisfies alpha equals beta if and only if every algebra in the K satisfies. This is the relation I wanted to come to, relative equational consequence relation, that is satisfaction modulo K. This is a relation between a set of identities and a single identity, and it's defined as follows. It has a lot of universal quantifiers. Now, the set of identities delta satisfies the identity alpha equals beta if and only if for every algebra in the class K and for every interpretation A bar of both the formulas, both the identities in sigma as well as the alpha equals beta, then for that interpretation, if the identities in delta are all true, then for the same interpretation, alpha equals beta also. So it is evaluation dependent. Each evaluation, the if condition must hold. And if that happens, then we say delta satisfies alpha equals beta relative to K, and that is the equational consequence relation. And here is kind of, again, the logic meets algebra. Okay. Now, we will come up with a class of logics that were studied by Razyova in the 60s, and they have turned out to be very important and useful. What is an implicative logic? Called a long name, but people have abbreviated into implicative. So let L be a logic in the language board space L that includes a binary connective arrow, either primitive or defined by a term. By the way, here formulas and terms are the same. It all depends on where you are. If you are in the logic side, you call them formulas. If you are on the algebra side, you call them terms. However, the roles in the logic and the roles in the algebra are different. Okay, L is an implicative logic with respect to this implication if the following conditions are satisfied. Those 5 conditions, I won't go through all of them. For most of you, they are well known because they were done in 1960s. And to save time, I'll just show them to you here and then continue. Okay. And she also defined a very special class of algebras that goes with this implicative language. And that's the definition. And L algebra is an algebra A in the language L that has an element 1, which could be defined by a term with the following properties, namely LALG1 holds and LALG2 holds. LALG1 is essentially the completeness statement. And the 2 simply says if arrow is one in one direction and also in the other direction, then the 2 elements are the same, A and B. Okay, so such algebras are put together in a class and we call them Al star L. From now on, Al star L means this class. For every logic, implicative logic, you associate this. Why are they important? Well, because of this theorem. Razyova proved this theorem. If L is an implicative logic, then L is complete with respect to this class. And that, it's almost direct, in the sense that you know what the class you should be looking for if you are working with an implicative logic. She told so what it is. Okay, so now we are going to start the logic that we are after. And that is the logic called DHMH. The name is very suggestive because it's going to, in a few seconds, it's going to correspond to the variety DHMH, the variety of dually hemimorphic Heyting algebra. And the language is this, and the axioms are 2 parts. the first set of axioms is simply nothing but the intuitionistic logic axioms. And I'll just put them here, taken from Razio Zikorsky's book. There's nothing, you can use any other set. Right? And to them, you add these additional axioms. These are motivated by those additional axioms of the dually hemimorphic algebra, that prime algebra property. Okay, so, and what are the rules? Of course, we do need modus ponens. That's not enough for us. We need what's called contraposition. From an implication phi arrow gamma, you deduce the negation gamma arrow negation. It's not the star negation, it's the other negation. So that's the contraposition. With these, because we know that the intuitionistic logic is implicative, we get immediately that the logic DHMH is implicative with respect to this. And here is a quick proof, so to speak. The proof is because of the implicative, the intuitionistic logic and the contraposition. The contraposition is needed to verify the axiom 3 there, the condition 3 in Razio's axioms for the implicative logic. Okay, so the DHMH is implicative, which means it's a nice one, logic. And immediately we know the completeness by Razio's theorem, namely that it is complete with respect to not the variety of dually hemimorphic Heyting algebra yet, but it is with respect to its class as an implicative. That is Alex star of it. So to come to our desired completeness theorem, we need to prove this lemma. Alex star of the logic is the same as our variety that you have seen just a few minutes ago, dually hemimorphic Heyting algebra. And I have a proof, but that's long and it will take a long time, so I will skip it. So can now make the final conclusion about completeness, namely the logic is in fact complete with respect to the corresponding variety that we are. So we now have a logic that corresponds to that for now. And we can say more about this logic in a minute or two. And the proof is essentially that lemma and the Razio's theorem. Okay, again back to some background. And this time it's a bit stickier one. It's the abstract algebraic logic notions. And I cannot give you all the details, but I will just give you enough definition so that at least those of you who have seen it before will know, oh yeah. But the others, you may get it, you may not. Then you may have to go and read Font's book on this. It's a nice book. And also the original paper by Bloch and Pigozzi, still classic. Okay. Now you have a class of algebras and a logic. This time it doesn't have to be implicative now. It's more general. Bloch and Pigozzi actually looked at the implicative logics, proved a very important theorem, which maybe I'll say it a little later, that actually allowed them to get to this more abstract notion of equivalent algebraic semantics. So let me quickly say something about this. But first we need to define what is an algebraic semantics. Okay, you are given a class of algebra and a single logic. The class K is called an algebraic semantics for that language, logic if there exists a formula identity transformer tau. What does that formula identity transformer mean? The tau takes a formula and converts it into a set of identities. A set of identities, not one identity necessarily. It could be one, but in general, it could be a set of identities such that this following equivalent condition holds. Namely, if you can prove alpha from gamma in the logic L, you can translate that and prove the corresponding identities, namely the tau of gamma, and they actually imply the tau of alpha modulo K in the sense that I just defined a moment ago, the relative satisfaction. So that is what algebraic semantics means. Simply put, it allows us to go from the logic to the class of algebras. And the second one is actually says to the effect that you can go backwards. Not only you can go backwards, but the processes are in fact inverses of each other. There are actually 4 conditions to say what I just said in words, in symbols, but turns out 4 of the, in those 4, 2 of them happen to be consequences of the other 2, and only those other 2 are used as definition now, and that's what you are going to see here. And the first one being alg1 that I just told you. Now, an algebraic semantic K for L is said to be an equivalent algebraic semantic if there exists a different transformer, this time a reverse way. Identity formula transformer. What does that mean? It takes an identity and converts it into a set of formulas. And here you need 2 variable formulas, whereas in the first condition, alg1, you need 1 variable identity. Okay, so the identity formula transformer rho, that is the inverse function of the transform tau. And that's basically is implied by one condition like this one. Namely, if you give me an identity, I convert it into sets of formulas using rho, and then convert back into a set of identities using tau. Now you on the right side, you have a bunch of identities, and they must be implied by this single identity, and the reverse also must. Conversely, this right-hand side must imply the left-hand. So these 2 conditions for a logic L, if you can find the rho and tau, makes the algebra, makes the logic algebraizable and the K equivalent algebraic semantic. We will simply apply these actually. So here are some consequences of this definition, again proved by Pigazzi, Bloch and Pigazzi in 1989 paper. That's what started the abstract algebraic logic in a very strict sense, in my opinion. Anyway, every implicative logic is algebraizable in the sense that I just defined with respect to the class alg star L, and the algebraizability is witnessed by those 2 transformers, namely tau of x takes to a singleton equation, namely
Hello?
using the same variable x
Hi,
equals
sorry
x
to disturb. You have 5 more minutes.
Okay, I should be able to finish. Thank you. X equals x arrow x, and the rho takes 2 variables and gives you 2 formulas, x arrow y, y arrow x, and that is basically the by implication motivation comes from this. Anyway, so that's all the tools that we need. Now we're coming back to the logic. Because it is implicative logic, by the above theorem, DHMH is algebraizable, and the variety DHMH is the equivalent algebraic semantic. And the rho and the taus are the same. So now we got a logic really corresponding to DHMH in the most strictest sense possible. So now let's look at some properties of algebraizable logics. And axiomatic extension, I think everybody knows. It simply means you add the axioms but no rules. And all the axiomatic extensions of a language for of a logic form a lattice. So ext of L is that lattice of extensions, and L sub V of K is the lattice of subvarieties of the variety. And the Bloch and Pigazzi proved this incredibly important theorem, in my view, that extension, the X of L is a dually isomorphic to the lattice of subvarieties. And this is really a bridge between algebra and logic. Anyway, if you apply that, and one more property, by the way, I need, and that is any axiomatic extension of an algebraizable logic continues to be algebraizable. Okay, so let's apply that to our logic and our class, namely DHMS. So the lattice ext is a dually isomorphic to the lattice L sub V of DHMH, and the every axiomatic extension is also axiomatic, is also algebraizable. And finally, here is the logic, almost Gautama, and you can see it has all the intuition axioms and the DHMH axioms that we talked about earlier, and you add those axioms kind of corresponding to the stone axiom and the regularity and so on. So those are these axioms. It's a very nice translation you can do from axioms of one algebra to axioms of logic if you have an implicative logic, especially, and if you have an algebraizable logic. Anyway, so the modus ponens and the contraposition, and the other axiomatic extensions can be again written down by using the translations of the axioms that we looked at for the subvarieties. So I'm not going to read them out, and there they are. And they all happen to be algebraizable also and correspond to the corresponding variety because of the dual isomorph. And so I will skip all of that. I just said it more. Okay, yes, there's one point now about decidability of these logics. They are all decidable because their corresponding varieties are finitely generated, and you can test it there by using the translations. Okay, I will end the talk with some open problems. There is is there a Priestley type duality for the variety AZ or AZH or G? And another one, there is a representation of regular double stone algebras in terms of rough sets. There have been several talks on rough sets. So somebody might be interested in this problem. Is there a similar representation for the variety AG or AGH or G or GH? Pasternak has given a triple construction for the regular double stone algebras. Is there a similar construction? Thank you very much.
Thank you, Professor Sankapanawar. So, questions?
Can I take this off now?
Yeah.
Okay, now I can see, yeah.
Yeah. So, there is one question from online participants, Parthopratim Ghosh. Okay. He is asking that usually the implication in hating algebras is the right adjoint of meet. Here, is it also the case?
Yeah, for the hating operations, yes. But we have an additional unary operation.
Okay. Any other question? Yeah.
Yeah. Hello, Professor Shankapanava. This is Mohua. Yeah. So that was it was a wonderful talk. Thank you. So I'm just curious that you said this whole exercise of getting the logic for AG through this going to the hating class and then this later part was because the implication was absent in the original one, right?
Yes, yes. So because the original variety is term equivalent to the AGH, so you might as well simply think of this as the logic for AG.
You could of course have a sequent calculus there itself.
Yes. You know, I don't know the answer, but my hunch is you may have to do the sequent calculus for the AGH.
I see.
And then use the fact that they are term equivalent and say that it is the logic for the other one.
I see, because usually
that's my impression, but I'm, I can't be 100% guaranteed.
I see. Okay, because usually that's the approach we take when an implication is absent. We say that there is at least a sequent calculus available.
Okay.
I see. Okay.
Maybe I think that might happen. I don't know for sure. Yeah.
Okay. Yeah. In that case, it would maybe interesting to check the relations between what
Yeah,
we have
yeah.
obtained after introducing the arrow and that. Yeah. Okay.
Yeah,
Yeah.
I know. I'm really interested to see the rough sets coming into this
Yes,
regular double.
yes, that caught my attention too. Yes,
Yeah, yeah,
I'll certainly
yeah.
pass this on. Yeah, thank you.
Yeah.
Yeah, thanks.
And by the way, the Gautama, this whole talk about almost Gautama algebra is also published now. It is available if anybody is interested. I will be happy to send it.
Okay, yeah, one more question.
Okay.
Yeah.
This is not a technical question, but since you called these Gautama and almost Gautama, I'm wondering whether there is some connection to the ancient philosopher Gautama. I mean, what was the inspiration? I mean,
Well, oh, you mean, for their work, I doubt it.
okay.
My motivation was simply, we read so many, so much about the Western names that have contributed in some form or the other. So I thought it might be a nice way to recognize them and remember them.
Oh, okay. Yeah.
And that was my personal interest motivation. Since I was free to name them anyway I wanted,
Okay.
I
Wonderful.
thought that was the best way that I can do.
Thank you. Thank
But
you.
I don't think there is any connection between their work and these algebras named after them, except I would say one observation historically, which perhaps all of you should know, that is the De Morgan operation, the laws of De Morgan, so-called, they were actually known for the logicians of Navenaya.
Yeah.
And, so in that sense, you might say, they have some relationship, but
Okay.
I wasn't thinking of that
Okay.
direction at all.
Thank you.
It was purely my own personal liking or interest because I wanted to make those names known worldwide, as it were.
Okay.
So I don't know whether I will achieve that, but at least I have done my part.
Any other
Thank
question?
you for asking that. Thank you.
Yeah. If not, Professor Me Chakraborty would like to say.
Oh, okay.
Shankar, I am here. Shankar, do you see me? Do you see me?
Nice hearing your voice.
Oh, I think.
Yeah, please.
Okay. Now, do you see me? Here.
Go closer to the screen. Go a little closer to the screen.
Do you see me? Do you see me now?
I'm seeing half.
Half.
Go
Okay.
further.
Okay, all right. Now I'm full.
Now I can see.
Okay. Thank you very much. Shankar, actually, I'm very happy to see you, of course, on the screen. And I hope you are quite well. And I saw your son also there. However, about Ramanujam's question, I just remind you, maybe you have forgotten or you might remember also. You asked me whether there was, what is the first name of Gautama?
Yes.
You remember that? And I said that there are two Gautamas, one Medhatiti Gautama and the other is what is the other one? Akshapada Gautama and Medhatiti Gautama. And so you decided that you will put the name Gautama without entering into Akshapada. Thank you very much. Thank you very much for being with us and delivering this wonderful talk. Thank you.
Thank you so much.
Yeah.
And I thank all of you because I know all of you almost, especially most of you. I wish I were there. I really wanted to come, but some personal situation could not let me. And my apologies for that. Thank you so much.
Yeah, let's thank Professor Sankapanna.
Thank you.
Thank you.
Thank you.
Yeah, now I would like to request the organizers to say something about what's following.
Hello, everybody. Actually, we now have a tea there with singara. And oh. Actually, after that, we have a photo session.
I messed it
And
up.
then we have a film, short film on Zero, in brainchild of our Parthoda, Parthosarathi Mukhopadhyay. And then we move to the fourth floor, where the actual Zero Gallery is. And to say something to Parthoda.
Yes, Shingara is important, so everything after Shingara. Actually, the idea is the Zero Gallery that has been established here, as I was mentioning the other day, that it actually showcases the history of 5,000 years of human civilization across all the ancient civilizations, not just India, trying to showcase their enumeration pattern, their systems of enumeration, whether they had their own zero or not. And this will be a precursor, this film, this a documentary film made with respect to that Zero Gallery, and it was already shown in 2021 December at the Goa International Science Film Festival. It's exactly 40 minutes. So that will be something that will help you to understand the exhibits over there. I'll be there personally, of course, to explain anything if you are interested to know more about it. But after listening to it, I think it'll be easier to go and watch the presentation over there. Thank you very much. 40 minutes.
स्वरूपिणे अवतार वरिष्ठाय ॐ स्थापकाय च धर्मस्य सर्वधर्मस्वरूपिणे अवतार वरिष्ठाय रामकृष्णाय ते नमः. Ramakrishna Mission Residential College, Autonomous Narendrapur, is a premier institution of higher learning. Established in 1960, the college has traversed a long way of 60 years and is now celebrating its Diamond Jubilee. This college has been established to nurture the epoch-making educational ideology preached by Swami Vivekananda. The Department of Mathematics does not only offer an honors undergraduate program, but the faculties of this department are also engaged in higher research in mathematics. Professor Parthasarathi Mukhopadhyay, Associate Professor of this department, has been researching on the origin of zero for almost 2 decades. And this research is certainly a pride point of this institute. In collaboration of the BITM, the Department of Mathematics and the college as well has established a panel exhibition based on the research activities of Professor Parthasarathi Mukhopadhyay. We certainly hope that Professor Mukhopadhyay's long-time research will be able to generate new debates, new arguments, new horizons in this field of zero research.
Zero. No single mathematical creation has ever been more potent for the general on-go of intelligence and power. But in which culture did zero originate? Well, interestingly, there is no one-liner as an answer. And any attempted answer generally depends on the perception of the seeker, as the connotation of the word zero can be perceived in several different but interconnected perspectives. Many ancient civilizations have their own different version of nothingness, represented by various zero-like concepts. But except in India, nowhere else these early and somewhat hesitant concepts bloom into their full potential as a number in its own right. Zero has always been with us from the ancient times. Although its somber discourse differed across paradigms, all recorded avatars of zero, dissimilar in rank and role, are gathered here in this hall to help you take a stroll through the winding roads of history to the bend of the recent past, when Indian zero gets accepted by all as a mathematical first. In this engaging tour of pictorial history, the journey takes us through the Egyptian hieroglyphs, Inca quipu, Babylonian clay tablets, Mayan glyphs, followed by the great Greek civilization, the mighty Roman Empire in the West, whereas we also come across the Chinese rod numerals, the lofty philosophy, embracing the concept of nothingness by the ancient Indian seers, which gradually paved the path for emancipation of zero as a number in its own right, till the Arabs in the East, and through them it went to Europe. Touching all these cornerstones, this bilingual panel exhibition tries to place the true genesis of our modern zero in its proper footing, an ode to nothing that is. Egypt, the land of Nile, once it cradled one of the earliest human civilizations. Their pyramids the burial chamber of their pharaohs, those attest to their unbelievable engineering skill. The hieroglyphic enumerations, that was decimal but additive in nature. That means you have different numerical symbols representing higher and higher powers of 10. Those are placed side by side, and to get the number they represent, their values have to be added. In the later hieratic numeral, as found in the Rind papyrus, this basic principle is essentially the same. Such a system does not require 0. But larger the number, you require more and more symbols to represent it. Later on, Egyptians sometimes used a particular hieroglyph, NFR, which means beautiful, to indicate the fixation level of the base of the pyramid, to save its burial chamber from the recurrent inundation of the Nile. The height and the depth of the pyramid were then decided in two opposite directions, in cubits. Some scholars want to see this as a budding number line-like concept, with NFR playing the role of 0 in it. But of course, it is a minority view, as the Egyptians never used this NFR as a number in its own right. Around 400 long years before Christ came along, 0 had made its presence felt in the mind of Babylon. But besides being in the medial position, could it appear alone? No. It filled a gap between numbers, as we have now known. Babylonians, they used a 3-sided stylus to incise on a wet lump of clay 2 particular marks for 1 and 10. They had a sexagesimal, that is a base 60 place value system. But their numbers from 1 to 59 were represented by additive principle made with those 2 basic symbols. For over 1,000 years, there was no 0 in this system. To represent the absence of a digit in the median place of a number, they used to leave a gap at that position. Naturally, that created a lot of confusion. From around the Seleucid period, they started using a particular double-wedged shape to denote the number 0, a placeholder 0. This symbol is considered as the oldest known written symbol of the placeholder 0 in human civilization. But they failed to conceptualize this 0 into a full number in its own right. This has been categorically shown with examples by Ifra in his famous book, The Universal History of Numbers. There's example aplenty on Mesopotamian earthen plates. Zeros engraved there are gap fillers, a fact which indicates that the Babylonian 0 was a number in an unavoidable plight in status much below the Indian 0, a number in its own right. Mayans from the Yucatan Peninsula, they used number 0 in their base 20, that is vigesimal system, using only a dash and a dot, a rare economy of symbols indeed. Their 0 was not a mere placeholder. Indeed, it was a pure number in its own right. They had at least 8 different glyphs to represent their 0. For example, a tattooed man with necklace and the head thrown back, or a seashell, usually colored red, the most common symbol used by the Mayans. They developed some very advanced calendar. Their civil calendar, called Hub, that had 18 months of 20 days each, and then an additional month of 5 days. Interestingly, the first day of every month was reckoned as the day 0. But in their long count calendar, while trying to keep the number of days in a year as close to 365 as possible, they had destroyed the pattern of the base 20 system by putting 18 into 20 in the third place instead of 20 into 20 as it should have been in a proper vigesimal system. This caused a serious drawback in their computational aspect of 0. The Mayan long count number 100 became equivalent to the decimal 360 rather than 400 as it should have been in a correct base 20 system. Hence, in spite of a bold and ingenious presence of 0 as a counting number, nowhere else seen in any other ancient civilization, still, for this deficiency, Mayan 0 cannot be considered as the true predecessor of our modern 0. The Inca Empire was plundered and destroyed by the gold-hungry Spanish conquistadors. But before that, they ruled Peru with a brilliant efficiency. Rigorous record-keeping of the taxes received was done through multicolored knotted strings called quipu. It was a decimal plus value representation of numbers by means of 3 different kinds of knots. A 0, in the sense of absence of a knot in the requisite position of the particular place of the string, can be seen. Clearly, it was a primitive placeholder avatar of the 0. They did not have a known system of writing, so there was no need for an independent number 0 in their system, nor was there any natural scope of evolution of any such possible relevant symbol. For every branch of human knowledge, Europe owes a lot to Greece, the home of Euclid, Pythagoras, and of course, Archimedes. Greece. Many scholars consider Greece as the cradle of our modern civilization. But this civilization, their numerical system was alphabetic. It was not a positional system, additive in principle. They used their alphabets like this well-known alpha, beta, gamma, etc. to represent their numeral symbols as well. The difference is, for a number to be represented by these symbols, they used to put a bar on top of it. Like here you see 241 is being represented by 3 symbols. Their values are being added, 200, 40 and 1. And there is no need for 0 in such a system. But for a long time, they could represent the largest number by this system as a myriori, only 10,000. And you see here, letter Omicron is a Greek word, Orden. It means nothing. And it begins with this letter Omicron, which resembles our modern day 0. But as you can see here, in this alphabetic system, Omicron used to stand for 70. The Greeks had a penchant for geometry. Their numbers were geometrical in shape. Every number had one or more than one shapes. It's called number-shape duality. Just like here you see, some numbers are squares, rectangulars, pentagonals, and so on and on. And that led to the confusion about 0. If 0 stands for nothing, then what shape can nothing have? How can nothing be represented by something? And with these philosophical conundrums, the Greeks, the natural inheritors of the Babylonian place value system with 0, they decidedly, consciously shunned 0 as a numeral. And this is due to, philosophically, the Aristotelian doctrine that preached that nature hates vacuum. There is no 0, there is no infinity. Aristotelian version of universe was a finite nutshell universe. And also, this idea of 0, if accepted as a number, it messed up with the neat Pythagorean doctrine of ratio and harmonics, and hence it could not be tolerated. In a Greek text of 100 AD, we find nothing and nothing added together make nothing. But alas, in the same text, within a few more pages, the author declares, 1 is the beginning of the numbers. In a later French edition of Ptolemy's Almagest, there is a embellished Omicron-like symbol denoting placeholder 0. This is usually referred to as the Hellenistic 0 in the literature. But it was not used alone as a number in its own right. Philosophically, 0 in ancient Greece was considered to be an evil idea. Aristotelian doctrine was then to be followed in Europe for about 2000 years as church embraced this doctrine. Contesting Aristotle thus became tantamount to challenging the authority of church in Europe. And in medieval Europe, this could easily have cost one's life. It is said that most of the great discoveries and inventions of which Europe is so proud would have been impossible without a developed system of mathematics. And that in turn would have been impossible had Europe been shackled with the unwieldy system of Roman numerals. Romans were more concerned with soldiering and politicking. Mathematics was not considered worthy of a noble Roman to pursue. Great Archimedes was killed by a Roman soldier. Hypatia tortured to death by Roman mob. Their clumsy enumeration system was additive in principle and also subtractive sometimes. There was no zero in it. That made even an ordinary arithmetic calculation in abacus to be a specialist job. To fix the year of birth of Jesus Christ, the Roman monks fused the 354 days Jewish calendar with the 365-day Roman calendar. But as they were unaware of the number 0, they put 1 BC directly before 1 AD, skipping over the year 0, thereby causing ever since the millennium problem. Along the banks of Yolo River prospered a great civilization, which grew gloriously forever and ever with its unique orientation. China had advanced in commerce with the furthest nook of the world. Nevertheless, they didn't have a 0, as their history has unfurled. The construction of all Chinese numbers did mostly depend upon adding and multiplying of them, and arguments strongly drawn. They resorted to decimal system with all accompanying thrills, but the absence of 0 reduced it to a Ferrari without the wheels. To write 22, what would a Chinese gentleman do? He would insert a sign of 10 just between the two twos. Pieces of small green bamboo sticks as rod numerals were kept. They implied rising powers of 10 in columns from right to left. You can surely Google it later. For now, just think of 506. Place 5 rods and 6 rods apart and give a gap inserted betwixt. This gap would then be called a Kong. You please be attentive here. Kong stood for just any number of gaps. Isn't it a bit unfair? Indian Buddhist monks reached China 1200 years ago to help them chance upon their Hindu 0. Learn it duly and follow. Shunya in Arabic was Sifra, and in French was chiffre. But what's really in a name? In Fibonacci's Livere Bacchi, written in Latin, Zephyram it became. Zephyram got changed to Venetian Zefiro, and then to 0 as it's now. Thus, the West begot their 0 from India through events that helped somehow. It is generally accepted that the peerless concept of decimal place value system in tandem with zero evolved in ancient India. Initially, during its early period of oral tradition, the concept of void was philosophically nurtured and analyzed by several different schools of thought. Eventually, at some point of time, the concept reflected in the Sanskrit word shunya was transformed into a numeral for mathematical expression of nothing. At a later period, it bloomed in its full potential as a number kho in its own right, an integer on which mathematical operations can be done. Indeed, this unique feature makes kho, the Indian zero, as the true progenitor of our modern mathematical zero. Indian seers from every school seem to have toyed philosophically with the concept of vacuum and nothingness, and they embraced the idea, unlike Greek scholars. In the Tantra, one finds the eternal divine creator Nishkala Shiva, undifferentiated formless God Shiva, who creates this universe from void and destroys it into void again and again. Nashadiya Shukta of the Rig Veda. Nasadasinna sadasit tadanim, nasid raja na voma paroyat. It portrays the vacuity before the creation. Shunyavad, Mahajan Buddhism doctrine of devoidness. It preaches about emancipation, nirvana, as the perception of everything phenomenal as shunya, the void. It appears very likely that the thread of rich philosophical and socio-academic ambience of Indian antiquity was quite pregnant with the immensity of the concept of shunya, a dichotomy as well as a simultaneity between nothing and everything, the zero of void and that of purna, an all-pervading, fathomless, infinite. However, the exact time frame of this gradual evolution of a concept into a number is still hotly debated. One recent controversy in this direction is the suggested 3rd century dating of the famous Bakshali manuscript by the Bodleian C14 test. This birch bark manuscript is replete with amazing calculations in decimal system with bold dots, the initial written form of Indian zero. A 7th century stone inscription of this symbol can be found in Cambodia, a place that was under religious influence of India at that point of time. At Gwalior Fort in India, one can find a 9th century stone inscription of Mihir Bhoja, where you can see a modern zero engraved in Nagari numeral. There are few others of earlier period engraved in stone or in copper plates, but experts do debate their authenticity. Oral enumeration system does not require zero in it. In Rig Veda, number names in Sanskrit are decimal in principle, but there is no zero in it. Placeholder zero was needed when India started writing in decimal system. Before that, neither in Brahmi nor in Kharosthi you find the number zero. Those were additive systems. A mere slavish replacement of the Sanskrit number names by symbols. Way back in around 5th century BC, a grammatical ancestor of zero, in the sense of vanishing, called Lopaha, is found in the Ashtadhyayi of Panini. In 2nd century BC text of Prosody by Pingala, the Pingala Chanda Sutram, there are explicit mention of zero as shunya in a calculation which leads to a combinatorial algorithm. Much later, in 5th century AD, we find Aryabhata enunciating the decimal principle of place value system in writing. Brahmagupta in 7th century stated the principle of operation with the number 0 and on the number 0. Dhanayor dhanam, rinam rinayor, dhana rinayor antaram, shamaike khom. It states that when a number is added to its negative, it gives 0 as an outcome. A clear assertion of the numberhood was thus bestowed on 0. Is 0 only the nothingness forever so present with us? It's boundless too that our rishis felt, the ananta, the infinitas, a singularity containing the entire creation before the elemental spark, the brightest light of our consciousness and the darkest of the dark. It has no beginning, this shunya, and in a sense, it doesn't have an end, open only to our perception. Its disposition is cryptically explained in the Nashadiya Shukta of the Rig Veda, serving as a lighthouse on the shore, on the ocean of the wisdom, to all our naive navigators, now, after, or before. Around 770 AD, the Indian decimal system, along with 0, reached the court of second Abbasid Caliph Al-Mansur at Baghdad through a Siddhanta text, most likely the Brahmasfuta Siddhanta of Brahmagupta, which was translated by Al-Fazari as Ziz al-Sindh-Hind. Around 50 years later, in the court of Al-Mamun, Al-Khwarizmi translated this book with some original work. That Arabic text is lost, but one later Latin translation by Adelard of Bath by the name De Numerandoram is extant. Later, Al-Khwarizmi wrote that famous book, Al-Jabar wal Muqabla, in which he translated the Sanskrit term shunya as sifr, a mere nothing. The book was introduced in Europe by its Latin translation in 12th century and eventually got spread throughout the world. Today, these numbers, the decimal numbers along with 0, are recognized worldwide as the Hindu-Arabic numerals. Zero, rejected by the church, kept getting back to use for commercial needs. It wasn't easy to ignore the trend, and serendipity did give a few leads. Working with mercury filled in a tube, Torricelli came up with a steady vacuum to show that nothing could rightly exist defying Aristotle's shallow dictum. Descartes put zero at the center of his plan, and geometry acquired algebraic wings. Zero was an idea whose time had come, a permanent conceptual leap to bring. From Arab's exposure to Shunya, to the decimal subjugation of pre-modern Europe, it was a wait exceeding 500 years, with deadening stops and abiding hope. Historical reconstruction of mathematical knowledge of ancient period is much like arranging pieces of an enormous jigsaw puzzle. Unfortunately, some of the pieces of which have gone missing. There are historians of mathematics all over the world who are trying to arrange the pieces, of course, according to their own stance, so as to make a pattern out of it. And the job is anything but easy. Often, the preconceived ideas come in the way of scholarly acumen. But of course, there are people who are trying to analyze the available piece of information and even lack of information with an obvious intention to try and make a pattern out of it. With every new piece being found occasionally, it destroys the existing pattern, and the journey continues. Where have the rest of evidences gone? Will our search ever find anything new? These questions you have inherited now, and the history of zero continues with you. History of zero continues with you.